Before we start talking about the benefits of Six Sigma, let's start with the basics and spend a minute talking about what exactly Six Sigma is. Six Sigma actually has several different facets to its meaning. First, if we look simply at the term Six Sigma, Sigma represents standard deviation, which is a universally accepted metric that allows us to calculate how much variability there is within a process. We then can use this information to determine if that process is able to stay within the established quality limits that have been set by our customer. Organizations use Six Sigma as a way to then measure the quality and performance of their processes. The Sigma scale measures defects per million opportunities, or DPMO, and Six Sigma equates to 3.4 defects per million opportunities, which is an extremely high level of quality. In addition to being a metric, Six Sigma is also a 5-phase continuous improvement methodology. The methodology follows the define, measure, analyze, improve, and control, or it's called by its acronym, the DMAIC methodology. This methodology focuses on identifying improvement opportunities, analyzing current processes, and then finding different improvement solutions, implementing them, and then maintaining control of those improvements. Finally, Six Sigma is also an organizational system that's used at a strategic level. Six Sigma is more than a set of metric-based problem-solving and process improvement methodologies. It's a continuous business improvement process that focuses on 4 key areas. Those are understanding customer-driven improvements, analyzing those current processes and services, aligning those processes to achieve those customers' requirements, and then finally, ensuring stability and sustainability of quality in the processes. It's important to also understand why, as an organization, you should invest in the Six Sigma methodology. And so there's several different reasons. First, as a methodology, Six Sigma aims to reduce mistakes and defects that occur within your processes. Six Sigma also has a proven track record. It has been globally accepted as a profitable and winning business strategy. More and more companies globally are embracing Six Sigma when they need to become more competitive or the markets are sluggish. It helps to improve operational efficiency and quality, often at the same time. In fact, you'll learn that without improving quality, it is often impossible to be more efficient. Six Sigma was first formalized by Motorola, a giant electronics corporation. While Six Sigma started in the electronics industry and gained momentum in the automobile industry, Six Sigma is a methodology that can be applicable to any organization, small or large, because it's a business initiative that can help all organizations become better than they currently are. Since the development of Six Sigma, it has been deployed in banking and financial services, information technology, healthcare, customer service, government, hotels, in the hospitality industry, and virtually all other business sectors. As a methodology, Six Sigma focuses more than just on error and variation reduction. Six Sigma is a business initiative that must be taken on by all employees throughout the organization. And for Six Sigma to be truly successful, all employees within the organization need to adopt the Six Sigma principles. And while Six Sigma can be used as a measure of quality, it's not strictly a quality initiative. A large part of Six Sigma initiatives focus on how to improve a process. And as you do this, defects are reduced and quality is improved. The organization realizes many other benefits. One of the main benefits of applying Six Sigma is that it creates an environment of sustained success. Six Sigma is not just a one-time fix. It's a methodology that needs to be implemented. During implementation, it should become permanently adopted by the organization. It changes the structure of the organization for the better. Six Sigma also provides realistic performance goals that are common across all processes and systems. The goal of reaching 3.4 defects per million opportunities is critical. Another key benefit of Six Sigma is that as the quality of products and services are improved, those services and products have enhanced value to the customers. This enhanced value helps to capture larger sections of the market and increases revenue for the organization. In addition, Six Sigma helps to facilitate rapid change and improvement within the organization, rather than just doing continuous improvement with gradual incremental change. What this means is that the rate of improvement is enormously increased in organizations that are applying Six Sigma. With this environment of rapid change, the Six Sigma practitioners are working together with the cross-functional teams, which helps to promote learning new skills from the Six Sigma methodology. It also helps to cross-pollinate these improvements between different areas of the organization and strengthens all of the departments and processes that are involved. Finally, by applying Six Sigma, it helps the organization execute strategic change within the organization, which helps to move the company forward. When management decides that a change is needed within the organization, Six Sigma is a way of bringing about the necessary changes to both the actual processes and the strategic direction of the organization. This is where Six Sigma really helps an organization place themselves in a position where they're poised to succeed on a new strategic path forward. Six Sigma is a business initiative that uses continuous improvement tools and methodologies to focus on achieving near perfection in products and services. This is supported by a 5-phase approach that follows the define, measure, analyze, improve, and control, or DMAIC methodology. During the define phase, Six Sigma team members define the improvement opportunities. They identify such opportunities and define context and process objectives from the customer's point of view. Quality tools such as brainstorming, flowcharts, and surveys can be used to collect data for defining objectives. During the measure phase, a Six Sigma team measures and evaluates how a process is currently performing to determine gaps and corrections required. Team members also choose the metrics to measure the process by during this phase. During the analyze phase, Six Sigma team members analyze process problems to identify root causes and to understand the cause and effect relationships that result in the observed problems. Managers also pinpoint opportunities for process improvement during this phase. During the improve phase, Six Sigma team members identify improvement solutions and strategies and improve the process through planned process modifications and specific project solutions. During the control phase, Six Sigma team members control the new and improved process through monitoring. They also establish a procedure to ensure that the improved performance is sustained for the foreseeable future. Sigma, or standard deviation, describes quantitatively how a process is performing. Statistically speaking, a Six Sigma process has a performance level where even the data points as far as Six Sigma, in example 99.9997% of all data points, from that target or mean value fall within the specification limits. In other words, as many as 99.9997% outputs are defect-free. A process like this will have only 3.4 defects per million defect opportunities or less. One aspect of the Six Sigma methodology involves reducing the number of errors in a process by minimizing variation. When a process is repeated many times, the outcome will differ slightly with each repetition. This is called variation. For example, each time a piece of fabric for a shirt is cut using a pattern, it comes out slightly different, a little narrower in places, or with a different curve. The end product is still a shirt, but each one differs slightly from the next. With variation comes the opportunity for error, products going outside of the specification limits. The Six Sigma methodology aims to reduce this variation so that the opportunity for error is reduced, thereby increasing quality and productivity. Process outputs can be plotted as data points on a bell curve around a mean or target value. The deviation or variation of these data points from the target value is measured as a standard deviation, such as a positive 1 sigma, 2 sigma, and so on the right side, and negative 1 sigma, 2 sigma, etc. on the left side. The further the point is from the target, the higher the sigma value it will have. From this information we can gather plus or minus 1 sigma, 2 sigma, 3 sigma, and so on. The further the point is from the target, then the higher the sigma value will be. Let's take a look at what Six Sigma means to an organization by comparing what 3 sigma means versus 6 sigma. For example, if we have a process that's at 3 sigma, that would mean 20,000 items of mail are lost per hour versus a 6 sigma process that would be 7 items of lost mail per hour. In addition, a 3 Sigma process would mean 5,000 incorrect surgeries performed per week, versus a 6 Sigma process of 1.7 incorrect surgeries per week. Another example of a 6 Sigma process is no electricity for almost 7 hours a month, versus a 6 Sigma process where there's no electricity for 1 hour once every 34 years. 3 Sigma would also mean 54,000 wrong drug prescriptions per year, in contrast to a 6 Sigma process of 1 wrong drug prescription every 25 years. A final example of a 3 Sigma process would be 5 or short long landings at one major airport in the United States every day, versus a 6 Sigma process of 1 short or long landing at all U.S. airports in 10 years. The formula of y equals f times x is commonly known as a transfer function, and the transfer function is used to illustrate the concept that important process outputs, also known as our y's, are a result of the drivers or inputs, also known as our x's, within our process. This gives us our equation of y equals f times x. So now let's take a look at the equation a little bit closer. With this equation, y isn't dependent on each output variable, which means its value depends on the value of x. X is an independent or input variable, and each x represents an input factor that determines the effects on y. The f indicates there is a relationship between the two variables, in which one variable depends on the other variable. Within 6 Sigma, the transfer function relates to the inputs of a process to the outputs of the process. And within an organization or department, a process has a measurable and therefore controllable output. This output from a process becomes input as it flows into the next level of the organization, along with the output from other processes. This enables departmental or organizational level outputs. It's important for 6 Sigma professionals to understand the relationship between the X's and the Y's, and how the outputs of various smaller processes lead to organizational outputs. This is how all process inputs and outputs are aligned. This information can then be put into a functional graph that identifies the inputs, outputs, and processing tasks that are required to transform the inputs into the outputs. The inputs represent materials, information, and the tasks that are accomplished by people using machines or equipment. The processing step includes all the tasks that are required to effect the transformation of the inputs into outputs. Finally, the outputs are the products, services, information, data, or material that's used in the next step of the process. Every process within an organization has inputs and outputs. These are arranged in such a way that the output of one process becomes the input of the next process. As we look at this a little closer, the key input variables are those key process inputs that have a strong potential to impact process outputs. Therefore, it's important for the team members to have direct control over these key input variables. And when a change is made to a key input variable, it usually affects at least one key output variable. The key output variables are also referred to as the big Y's. These are many process outputs that fulfill to lead to the fulfillment of the 6 Sigma deployment goals. It's important to also note that there are usually fewer big Y's than the key input variables, but there's always at least one key output variable for each process. Also, the big Y's often include very significant functional goals that directly influence an organization's key objectives that relate to customers' profitability, or efficiency, quality, and productivity. From this perspective, those big Y's are most important for 6 Sigma professionals. The transfer function illustrates the idea that the key output variables of those big Y's are a result of those key input variables, the X's within processes. The goal of 6 Sigma is to identify which vital few input variables influence the desired output the most. Each phase of the DMAIC methodology can be described by how it contributes to this goal. So if we look at the first phase of define, the purpose is to identify and understand the big Y, and possibly the potential X's. The purpose of the measure phase is to measure those X's and the big Y and begin to prioritize the vital X's. Within the analyze phase, 6 Sigma professionals test the XY relationships and verify or quantify the most important X's. In the fourth phase, the improve phase, this is where the Six Sigma team begins to implement solutions to improve the big Y and the important X's. And finally, in the control phase, the Six Sigma team monitors the performance of the important X's and the big Y over time. Within Six Sigma, it's also important to understand the leverage principle. The first aspect of the leverage principle is to understand that all input variables are not equal, and some of the input variables affect the output more than others. Within Six Sigma, the leverage principle refers to applying changes to those vital few X's that have the greatest impact on the big Y. A major part of this leverage comes from a surprisingly small number of contributors, or X's. Improving the outcome comes down to finding those critical few inputs that give you that leverage. This concept of the vital few versus the trivial many comes from the work of the early 20th century Italian sociologist and economist Vilfredo Pareto. The Pareto principle is also known as the 80-20 rule, where 20% of the inputs in any process account for 80% of the influence on the outputs. As a Six Sigma professional, it's important to strive to find those vital few. In order to look for leverage, search for the few variables that are most influential in solving problems in operations, assembly, distribution, and other areas within your facility. The way to find the vital few is to follow a structured process for analyzing the cause and effect relationships. Continuous improvement methodologies have evolved over the years. Mathematician Carl Friedrich Gauss was the first to determine sigma as a statistical measure. He used it to describe the standard deviation from a central value, such as a mean. The first use of sigma as a metric or standard for evaluating quality has been traced back to the 1920s. Six Sigma was developed by Motorola and others in the 1980s. And at that time, Motorola was experiencing significant quality problems and was struggling to compete in an increasingly competitive market. Six Sigma was a result of the need for Motorola to turn the company around. The Plan, Do, Check, Act cycle was developed by Walter Shewhart in the 1920s. It was later improved by Deming. The Plan, Do, Check, Act cycle is an iterative problem-solving loop that's the basis for nearly all continuous improvement approaches. Statistical Process Control, or SPC, is a method that uses statistical tools and techniques to manage and improve processes. SPC originated from the work of Walter Shewhart, who was a physicist working at the Western Electric Bell Laboratories in the 1920s. Shewhart control charts were invented later as a way to control process variation. Engineers at Toyota devised a methodology known as a Toyota Production System between 1948 and 1975. This was a forerunner of lean manufacturing, which is a system that focuses on eliminating waste, reducing inventory, and reducing processing time. Toyota engineers also invented quality circles, which are independent teams of 6 to 8 workers who meet periodically to identify opportunities for improvement and then submit those ideas to management. Total quality management was invented in Japan in the 1950s. However, it did not achieve prominence in the U.S. until the 1980s. Total quality management is a comprehensive set of management practices and tools that focus on meeting or exceeding customers' expectations. It emphasizes process measurement and controls, and its aim is to involve all employees in process improvement throughout the organization. ISO 9000 is a set of standards that helps business organize in order to produce high-quality products and services. Companies that are certified as ISO 9000 compliant can conduct business locally and internationally with assurance of meeting agreed-upon quality levels. Both Total Quality Management and ISO 9000 help companies to trim the fat and improve their quality. However, at that point, there were still many U.S. companies that didn't want to spend the time and the money on improving quality and efficiency. And this is when the U.S. Congress established the Malcolm Baldrige National Quality Award as a way to inspire companies to achieve that higher level of quality by giving them this recognition. The criteria for this award are published by the National Institute of Standards, or NIST, to help provide guidance for companies that seek to establish excellence in performance management. Benchmarking and reengineering were also developed during the late 1980s and 1990s as work in quality sciences intensified. Benchmarking is a strategy to improve the organization by adopting best practices of industry leaders. Benchmarking helps organizations identify what it does well and what it does not do so well. Benchmarking also helps companies emulate and adapt the leader's processes in order to achieve superior performance levels. While benchmarking did not influence the evolution of Six Sigma directly, it has been widely accepted as a methodology within Six Sigma in order to set improvement goals and identify best practices and improvement solutions in order to deliver superior products and services. Reengineering is a method for streamlining the organization. In the 1990s, many companies have built their organizations based on the traditional pyramid structure, and this meant they were top-heavy and populated with turf-guarding and empire-building executives. This led to very rigid divisional boundaries that protected the status quo and prohibited innovation. The Six Sigma methodology has evolved directly from mainstream quality control methods. In the 1970s, a Japanese company took over a Motorola plant that produced televisions. These Japanese corporate leaders changed the management workflow, but they retained the workforce technology and designs. This time, Motorola realized that in order to survive, it had to change. In the mid-1980s, Motorola's CEO Bob Galvin launched the initiative known as Six Sigma, which was used to turn the company around. Six Sigma enabled Motorola to reduce product defects and returns to 1/20th of the previous numbers. They also achieved a 5-fold growth in sales, with profits climbing nearly 20% and a cumulative savings of $16 billion. The stock price gains compounded to an annual interest rate of 21.3%, and Motorola won the prestigious Malcolm Baldrige National Quality Award in 1988. In 1995, Jack Welch converted General Electric into a Six Sigma organization, and they achieved legendary results. General Electric estimated benefits on the order of $10 billion during the first 5 years of deployment. After the results at Motorola and General Electric, Six Sigma's popularity really took off, resulting in organization-wide deployments in Global 2000 companies, in both manufacturing and service sectors alike. Six Sigma incorporates concepts and tools from proven continuous improvement methodologies. So let's take a look at some of the Six Sigma characteristics. Six Sigma emphasizes the define, measure, analyze, improve, and control, or DMAIC approach to problem solving. The DMAIC approach is based on the Plan, Do, Check, Act improvement cycle. Six Sigma also focuses on the rigorous application of statistics. The methodology uses statistics to control processes. This approach to using statistics to control processes originated with statistical process control, and it's also done in total quality management. Six Sigma also promotes the use of proven tools and techniques to reduce defects. Six Sigma uses many of the same tools within total quality management, but is typically a smaller subset. Six Sigma also promotes the use of well-trained, independent teams to handle well-defined projects. The use of independent teams and worker participation was pioneered by the Japanese with quality circles and the Gemba. Going to Gemba means going out to the place where the operations are occurring to look for improvements. And finally, Six Sigma also promotes reorganization to focus on the processes and quality rather than using functional silos. Reengineering, TQM, and ISO 9000 all advocate a process-oriented approach to organizing for quality. Six Sigma and Lean are both methodologies that focus on continuous improvement, although they have slightly different aims. Lean is a continuous improvement initiative that streamlines and improves processes by reducing waste and cycle time. Six Sigma focuses on reducing defects and variation within processes. While Lean and Six Sigma originated as two different strategies in two different environments with different tool sets and methodologies, they are increasingly being seen as complementary processes to reduce waste while reducing variation. From this perspective, the combined methodologies are now referred to as Lean Six Sigma. And while each methodology has a different focus, each brings different strengths to the union of the two methodologies. Lean focuses on increasing the velocity of processes by eliminating barriers and waste, speeding up the production processes, and eliminating non-value-added activities. While Six Sigma focuses on eliminating defects through variation reduction and improving customer satisfaction. Six Sigma aims to understand process variation and bring it under control by applying the DMAIC methodology and sophisticated statistical tools. By combining Lean and Six Sigma, organizations are able to impact the bottom line and enhance the customer experience. There are several key pioneers that play pivotal roles in developing the quality theory upon which Six Sigma is based. Some of the most well-known pioneers are noted for their significant contributions toward developing the foundation of Six Sigma. And some of these individuals include Joseph Juran, W. Edwards Deming, Walter Shewhart, Karu Ishikawa, and Genichi Taguchi. Dr. Joseph Juran's ideas were instrumental in the development of total quality management, or TQM theory, which are now a well-known base for quality initiatives. Dr. Juran's work, the Quality Control Handbook, was first published in 1951, and it quickly became the reference for quality managers. It remains a key reference today. One of Dr. Juran's most notable contributions was that he was one of the first people to recognize that the Pareto principle, which states 80% of the problems are caused by 20% of potential causes, applies to quality management and process improvement. Dr. Juran played a key role in developing the Japanese economy during the 1950s, and his Juran Institute has also influenced top management in the U.S., just as he did in Japan. In addition to Dr. Juran's other significant contributions, he also developed the Juran Trilogy for quality management, which consists of three basic principles: quality planning, quality control, and quality improvement. W. Edwards Deming was a leader in the field of statistical methods of quality control. Like Juran, he was influential to the Japanese, where he taught statistical methods to the members of the Union of Japanese Scientists and Engineers, which is commonly referred to as JUSE. However, Deming only became popular in the U.S. much later in his career when he proposed his 14 points and 7 deadly diseases of top management guidelines. These guidelines aim to create a constancy in purpose. What this means is that an organization's quality effort must be focused on a single goal. This is similar to the major feature of Six Sigma, in that there is a single performance goal that all employees must strive towards. One of his most notable contributions was his support of the Plan, Do, Study, Act cycle as a method for system improvement. This method is still used today and is similar to other process improvement tools used in Six Sigma, such as the DMAIC methodology. Another key pioneer was Walter Shewhart, who led the way for the use of statistics for quality management. Shewhart noticed, while he was working at the Western Electric Company during the 1920s, that engineers needed to reduce the rate and the occurrence of failures. This was necessary in order to improve production processes and make them more economical. Shewhart decided to describe the program of reducing errors in a process in terms of process variation, which is also the deviation from the mean called sigma. Shewhart described process variation as one of two types: assignable cause and chance cause variation. Assignable cause variation is variation that can be traced back to a specific root cause. On the other hand, chance cause variation is variation that cannot be traced back to a specific cause. The idea of reducing variation through the application of these statistical methods was the basis for statistical process control, or SPC. Shewhart was the first to use control charts to indicate where variation occurs within a process, and then when you should act on it. Control charts are used in a similar way and form the basis of statistical process control. Shewhart also made noteworthy contributions to the development of the Plan, Do, Check, Act cycle popularized by Dr. Deming. Dr. Kaoru Ishikawa is considered the father of Japanese quality control, and he was involved in the Japanese quality movement since its earliest days. Dr. Ishikawa was able to distinguish the Japanese approach to total quality control, which he referred to as company-wide quality control, from the Western style. Western managers quickly realized the value of his ideas and adopted them within the United States. Dr. Ishikawa's ideas are evident today in quality management, such as the concept of quality circles and next operation as customer. One of Dr. Ishikawa's major contributions to the development of quality management theory and its base for Six Sigma is a development of the cause and effect diagram. The cause and effect diagram is a very simple method and a graphic that's used to identify root causes that are underlying process problems without the use of complicated statistics. The cause and effect diagram is also commonly referred to as Ishikawa diagram in his honor. Dr. Genichi Taguchi is known as the father of quality engineering. Taguchi was instrumental in developing quality engineering and techniques to reduce cycle time, which is a large part of the Six Sigma process improvement methodology. Taguchi came to the U.S. to help industries with quality initiatives, and companies such as Ford and Xerox quickly recognized the value of his ideas and began promoting them. Taguchi is well known for his theory that manufacturing processes are influenced by external factors that he referred to as noise. Taguchi said that in order to improve a process and reduce the costs that are involved, managers need to identify and eliminate the noises from the process signal, because these are the vital elements of the process. Taguchi's theory for quality management consists of two parts. The first is a quality loss function, which is an equation that's used to calculate how much money is lost due to the variability in a process. The other part is design robustness, and this requires a process to be able to produce high-quality products consistently regardless of external factors. Six Sigma initiatives start with an organization deciding that they will need to change and improve. At this point, small improvement projects where there's opportunities for improvement are identified and launched. These small initial projects are typically 3 to 6 months in duration, and they're often headed by a black belt, although sometimes Six Sigma green belts might need to implement smaller improvement projects. These projects go through the DMAIC stages, and their focus is on reducing cycle time, errors, costs, or improving a process in other ways. So now let's take a look at an example of 7 different projects and what their savings and benefits were. And for example, the average project value for these 7 projects was $605,785, and the number of projects per year per full-time black belt was 3 projects. The average investment per project was $125,000, and the return on investment was 485%. As organizations start implementing Six Sigma, there are several considerations they need to take into account. First, it's critical that top management has bought into the strategic and operational goals of Six Sigma deployment within their organization. If Six Sigma has been chosen as the path forward, then management needs to choose the most appropriate projects from those currently within the organization that link to those strategic and operational goals. Note this: Six Sigma initiatives may not always be suitable for all improvement projects within the organization. The best Six Sigma projects are those that are linked to the organizational goals. These are the projects where the benefits of applying Six Sigma will be the greatest, and they're the most influential. Another key consideration is that implementing a Six Sigma initiative is a very large undertaking, and management may want to start with a few smaller projects before implementing the initiative throughout the organization. This will also help grow momentum as people see the success of those small improvement projects. And then, after your organization has analyzed the need for change and you've decided upon a revolutionary approach, you will most likely start considering implementing Six Sigma or a combination of Six Sigma and Lean. When implementing Six Sigma, it's also important to realize when you should not use Six Sigma. Not all projects are appropriate for Six Sigma. For example, when you have another process or quality improvement strategy that's being applied to a certain project, then applying Six Sigma to that same project may cause a conflict of application. and it may not be possible to conduct the two simultaneously. Another example of when you should not apply Six Sigma is when the current changes that are being implemented in the project are too overwhelming to handle. By adding the additional demands of the Six Sigma initiative, it may place too much strain on the resources and the staff members who are assigned to the project. Another reason for not starting a Six Sigma initiative is when the potential gains of doing so are not worth the costs that are involved. Six Sigma is not something to be taken lightly. It requires a complete transformation within the organization. This means that it could be very demanding of time and can also be very expensive. And therefore, Six Sigma should only be applied where the costs can be justified by the benefits. This is most likely to happen in projects that are fundamental to the organization because they're linked to the strategic or organizational goals. Before proceeding with the Six Sigma implementation, the organization should also do a readiness assessment to determine whether Six Sigma will yield the improvements that are necessary and whether the organization is ready for Six Sigma. The purpose of this readiness assessment is to make a strong strategic case for Six Sigma based on demonstrated need that can't be filled by existing organizational strategies. There are three key steps with assessing an organization's readiness. The first is to assess the organization's outlook and future path. The question to answer revolves around: is change a critical business need now based on bottom line, cultural, or competitive needs? Some of the additional questions that you should ask in this step include: does the organization have a clear strategic course? And if so, what is that course? Are we likely to meet our financial and growth goals? Or do we need to respond efficiently and effectively to changing circumstances? The second step is to evaluate the current performance. And the key question to answer here can be this: is there a strong strategic rationale for applying Six Sigma to our business? It's important for organizations to choose the best strategy, and it's dependent upon the organization's current performance level. A pure Six Sigma approach achieves the best results when it's implemented by a high-performing organization. Medium-performing and low-performing organizations should probably implement more basic techniques first to improve the performance before moving into Six Sigma. And low-performing organizations are generally not good candidates for these revolutionary approaches. It's critical for management to ensure that the performance level of the organization or department is high enough to warrant a Six Sigma initiative. And finally, the third step is to review the systems and the capacity for change. The key question here is: can existing improvement systems and capacity for change achieve the degree of change that's necessary to keep us successful and competitive? A few additional questions that are critical in this step are: how effective are the current improvement strategies and change management structures? Are we meeting our performance measures, integrating between initiatives, and do we have an improvement culture? How well do we manage cross-functional processes? We should also ask: is there interaction between the divisions? And finally, we should ask: how might other initiatives or activities conflict with or support a Six Sigma initiative? When determining which projects are suitable for Six Sigma projects, there are four key considerations. The first is to consider whether or not the project is important to the organizational goals. The second consideration, after you've ensured that the projects are linked to organizational goals, is to prioritize the project portfolio. Typically, within an organization, there are many projects that have been chosen to make up the organization's Six Sigma portfolio. They all have Six Sigma methods that could be applied to them, but you can't focus on all the projects at once. Therefore, the projects need to be prioritized. The third consideration is that Six Sigma teams need to consider the appropriate methodologies that they should apply to their project. This means determining which approach they should use in the Six Sigma initiative and which tools to use. And the final consideration is determining which team the Six Sigma project should be allocated to. Let's look at the first consideration for whether or not the project is important to organizational goals. Managers need to make sure that the department that's running the project is a high-performance department. This is because Six Sigma projects work best in high-performing environments where employees are goal-driven and very ambitious. A good indication is the previous results from similar projects. Once it's been established the department has a suitable performance level, then managers can make sure that their project is linked or can be linked to the organizational goals. The purpose here is to make sure that the eventual benefits that are realized will be large enough to warrant the time and resources involved in the project. In addition, when you're considering how projects are linked to the organizational goals, managers should also consider how implementing Six Sigma in the project may affect the achievement of those goals. For example, a manager could ask, how will processes be impacted, and how well is that project design suited to Six Sigma? The answers to these questions have a direct impact on the ability to meet the desired goals. Now, let's look at an example. Let's consider that we have a manager carrying out the first step in choosing a project, examining an existing project. She knew that the department running the project had the goal of increasing its market share by 5% during the financial year. Achieving this means keeping existing customers happy, because satisfied customers are the best advertisement, and they're a positive reference for your organization. So when deciding whether the project was suitable for Six Sigma, she made sure that it was linked to this major organizational goal. What this means is that the project had the goal of maintaining customer satisfaction, and that the manager considered the impact of Six Sigma on this goal by asking, how will the customers be affected while changes are being implemented, and how does this impact the organizational goals? After ensuring the projects are linked to the goals, the second consideration is prioritizing the projects. There are several common criteria used to prioritize projects. First, managers should determine whether a project aligns with the high-level business strategies. The priorities based on the associated goals will indicate what priority should be assigned to each project. Urgent problems are given a higher priority than less urgent problems, and projects with large problems or problems that have been around a long while are given a higher priority. In addition, if there is a significant problem in the project that has meant financial loss or wasted resources, it is given a higher priority as well. Managers should also evaluate the risk and the impact of not doing anything to fix the problem. In doing this, they should examine what the impact would be if the problem was given a low or a high priority. In addition, managers should determine the level of difficulty for the project implementation and what gains are to be had by this project implementation. Easier the project, the higher their priority, because easier projects can be completed quicker. Finally, managers should also determine what resistance could be encountered when applying Six Sigma to a project. The more resistance there is, the lower the priority. So now let's take a look at this with an example. Let's consider a manager that has examined a project with a single large problem. The problem has been around for some time, and has resulted in downtime in several instances. However, there could be a relatively easy fix to the problem if the right resources are properly focused. The manager also looked at a second project. This project was newer and had many small problems. The project was made up of processes that were established a long time ago. Because of this, there might be considerable resistance because employees were used to the old way of doing things. Because of these elements, the manager gave the first project a higher priority for the application of Six Sigma over the second project. It's also important to note that both projects were suitable, but the first project was easier to implement than the second project. The third consideration is determining the most appropriate method. Within Six Sigma, there are two main methodologies. The first is Design for Six Sigma, or DFSS. Design for Six Sigma is a methodology that's used when designing new Six Sigma projects. Design for Six Sigma is used to create processes within projects that are compliant with Six Sigma methods and metrics. It's also useful for redesigning existing projects in an entirely new way when they're not meeting current customer expectations. Design for Six Sigma involves identifying the need for the project, making sure it aligns to the strategic goals, and then designing it, optimizing it, and validating the results for the new process. The second methodology is the Define, Measure, Analyze, Improve, and Control, or DMAIC methodology. Six Sigma is used when you're interested in improving your existing processes. However, if you need to design a new process that's compliant to Six Sigma, then Design for Six Sigma is the most appropriate. And finally, the fourth consideration is to determine which Six Sigma team the project should be allocated to. It's important that the Six Sigma team has the appropriate level of expertise. However, black belts lead most critical projects. Six Sigma projects should be continuously monitored for alignment with the organization's goals. To ensure that alignment, a Six Sigma team should ensure full support of the leadership team, ensure change management and communication, continuously review progress and alignment of the project metrics to the organizational goals, organize an adequate team, and put a support system in place, and then conduct Six Sigma training. Let's look at the first aspect of ensuring full support of the leadership team. It's critical that the executive team is involved in and actively endorses all of the key decisions. This is important because Six Sigma projects and the decisions involve time and money, and therefore leaders should be directly involved to make sure that the focus is truly aligned with the needs of the organization. In addition, involving the corporate leaders helps to keep them in the know and provides them a learning opportunity. Also, the active participation of leadership and their commitment to the Six Sigma project ensures that actual and perceived urgency and importance of the project is provided to all of the stakeholders in the organization. And this includes the enterprise leadership team, leaders of the business units, members of the improvement project team, and employees at the team level. The next key aspect is change management. It's important to ensure that you're taking change management and communications into account with your Six Sigma project. To do this, it's important to make sure that all employees and stakeholders that are affected by the Six Sigma project are communicated to, and they're helped through any changes that might affect them. So you should consider, how do you introduce the plan to ensure it's a positive reaction? We want to make sure that the communication is two-way between management and providing a message and employees providing feedback. With that, we want to make sure that the message is tailored to different groups. In addition, with the communication, you should think about the media events and similar activities that are appropriate to further communicate the plan. Finally, it's important to create a plan on how you will, as a team, deal with any negative reactions. The next aspect that's important is looking at the review of the continuous progress of the project and measuring the project performance metrics. When we look at this, it's important that the metrics are reviewed at a regular basis against target values for the project, and they're also reviewed against the organizational goals. In addition, a key part of this is making sure that the metrics are stated in a way that's clear to all stakeholders. As part of the Six Sigma initiative, it's also important to make sure that you have an adequate team and a support system in place. The Six Sigma initiative should be supported by a project team, a champion, a Six Sigma Master Black Belt, and a Six Sigma Black Belt, with the appropriate executive leadership. Once the project team is identified, it's important to define the appropriate roles for the project team members and clarify their responsibilities. These decisions are driven by a variety of factors, including the Six Sigma objectives, the implementation plan, budget, and existing staff and resources. The typical roles within a Six Sigma team include the sponsor or champion or process owner, the implementation leader, which is typically the Master Black Belt, the Six Sigma director or quality leader that could also serve as the coach, such as the Master Black Belt or Black Belt, the team leader, which could be a black belt or a green belt, depending on the level of difficulty of the project, and then the team member, which could be a green belt or a yellow belt. The final key aspect is to ensure that you're delivering timely and appropriate training within your organization on the Six Sigma tools and techniques. A continuous improvement initiative requires that the members and stakeholders have the necessary information and skills to constantly gain new insights. A few of the essential requirements of Six Sigma training involves delivering hands-on learning by putting concepts and skills into immediate practice and application by providing relevant examples and links to the learning that reflect challenges that are affecting your business, catering to a variety of different learning styles, adapting the Six Sigma rigor into training modules that your employees can easily digest, creating champions and ambassadors for your project out of these training events, and then finally, considering ongoing training to keep everything fresh and relevant within your company. The focus of any continuous improvement effort is on the process. It's the building block of an organization. Dr. Joseph Duran defined a process as the logical organization of people, materials, energy, equipment, and information into work activities designed to produce a required end result, a product or a service. Business processes have three main characteristics. First, there are a series of events that produce outputs. Processes are also defined through numerous steps, and the beginning and endpoints of a process are marked by boundaries. Processes are linked together in a business system. The business system is the overarching method or procedure for process execution. It ensures that the process receives the resources it needs at the right time. The process is the heart of the system, and it's the focus of Six Sigma continuous improvement. A process can then be further divided into sub-processes, and those sub-processes can further be broken down into steps. A step is the smallest unit of work that can be measured. The SIPOC diagram is a way to identify various components of a process in an organization. The acronym SIPOC stands for Suppliers, Inputs, Processes, Outputs, and Customers. The components of the SIPOC diagram provide a high-level view of the process, showing all of the components and the boundaries. This helps the Six Sigma teams identify areas that require improvement. The first step of the SIPOC diagram is to identify the suppliers. The suppliers are the people, departments, or organizations that provide materials, information, or resources that are worked on or transformed within the process. The inputs are the materials or information that are provided by the suppliers. These inputs are transformed, consumed, or otherwise used by the process. The process is a series of steps that transforms those inputs into outputs. When you're diagramming using the SIPOC method, you should not have more than 7 or 8 steps within the process. If you have more than 7 or 8 steps, it's typically an indication that you have too much detail, or that you're including the sub-process steps. The outputs are the products or services that result from the process that was performed on the inputs. And then finally, the customers are the people, departments, or organizations that receive the outputs from the process. Let's take a look at how the input, process, output feedback system works. The inputs are the data, opinions and ideas, or orders that come from your suppliers. These could come in the form of raw materials that are needed for your next step, which is the process. The process should include those 7 or 8 steps that transform the inputs into the necessary outputs. The outputs are the products, services, or training or designs that your customer has requested. With the input-process-output diagram, there's also a way for feedback to come from your end customer back to your outputs or your inputs, and also feedback from your outputs to go into your inputs. This feedback loop is an essential step of the input-process-output diagram to ensure that you get the information from your products and your customers to further improve your process with your inputs. In this topic, we're going to compare core and support processes. Core processes are those processes that are essential to creating value for the business. All other processes are considered support functions, which provide vital resources or support to sustain those core processes. Processes that are classified as core processes can vary from organization to organization. However, there are some processes that are considered core in the majority of organizations. Those include marketing, sales, service, product development, and product creation. All other processes are considered support processes. The support processes provide vital resources or support in order to sustain these core processes. For example, purchasing and human resources can serve the entire supply chain or a large portion of it, but they're not the main business of the organization. Identifying core processes is a major step in process improvement. Six Sigma is typically only applied to core processes or a combination of core and support processes. Improving the wrong process can result in a waste of time and money. A process is generally core if you can answer yes to three key questions. The first question is, does the process cross multiple departments? Core processes use the talents of people from different departments in order to produce the desired output. Support processes, however, generally only occur within a single department. The second question is, does the process generate revenues for the organization? A core process has the potential to generate money for the company. A process may also be core if it helps to retain customers, or if it produces a product or service. The final question is this: is the process customer-focused? A core process is focused on the external customer. Customers may be either companies, distributors, or end consumers. In this topic, we're going to talk about process interactions. When analyzing processes for improvement opportunities, it's important to stay focused on the goals of the organization and the core processes. When a company loses sight of the big picture, they may improve the wrong processes and find themselves in trouble. Let's take a look at an example. To accomplish the goal of speedy delivery, a company that specializes in partial delivery is divided into 4 functional areas or business units. Delivery trucks pick up packages from homes and businesses and deliver them to local warehouses. The partials are then sorted at the local warehouses and sent by truck or airplane to central distribution points all over the world. The packages are again sorted at the central distribution points and distributed to local distribution points. And from local distribution centers, the partials are trucked to their final destinations. Each functional area in this example has its own vice president and internal infrastructure. The company encourages these business units to make their own decisions and set their own team goals. In time, the business units start to act as silos and operate almost like separate companies. The vice president in charge of dispersion determines that he can reduce overseas delivery times by 40% by reducing the fleet of planes with faster, larger airplanes. Unfortunately, the overseas distribution centers cannot respond quickly enough to the change, and they soon accumulate a sizable backlog. The company's much advertised and much coveted delivery time of 3 days to anywhere in the world increases by as much as several weeks on some routes. The competition moves in quickly and takes over some of the key delivery routes. Here, we want to look at how core processes interact with each other and with support non-core processes to create value for the customer. This process map shows how processes are performed across all functional lines or business units. External suppliers provide raw materials for product creation processes, and then employees in the product creation processes receive the raw materials from suppliers and exchange information about customers' wants and needs with the marketing staff. And they also exchange information about product features and functions with the product development personnel. Marketing is a key portal. It's how important information on customers' wants and needs enter the organization. It's also how information about the organization's products and services reach the customer. Marketing information is an input to all of the other core processes, and marketing personnel receive output directly from all other core processes. Sales and service is a key portal for the direct exchange of information with customers. The sales and service personnel interact with the marketing staff and with the product development personnel. And then finally, the product development personnel interact with employees in all of the other core processes. Information is exchanged about products, services, features, and functions with personnel in product creation, marketing, and sales and service. An organization's business drivers are those driving forces that influence every aspect of work that is done by an organization. Business drivers are the highest level of performance measured within an organization, such as financial or performance measures. Business drivers form the backbone of any business effort to improve customer, operational, and financial performance. Business drivers are essential to the success of an organization. Without them, work can become unfocused because there are no motivating goals driving progress within the organization. Business drivers drive everything in the organization from management decisions to employee actions. This is why business drivers are such an important part of Six Sigma. Organizational improvement efforts should be driven by the business needs, not by the improvement strategies themselves. It's important to note that business drivers are not organizational goals, but they are strongly linked to them. Business drivers spur growth in the areas that are most important to the organization's overall success. Having business drivers in sight helps the Six Sigma team select the right projects and align their projects to support one or more of these drivers. Some examples of business drivers include profit, market share, customer satisfaction, efficiency, and product differentiation. So let's talk about each of those in a bit more detail. Profit is shown as net income on the income statement. It's a measure of all transactions, even those which have not yet had cash collected as a revenue or paid as an expense. Net profit is gross profit minus the expenses the organization has incurred during the business operations and the taxes it owes. Market share is a portion of sales of a certain product or service in a given region that's controlled by the company. While revenue growth allows a company to calculate growth internally, market share gives an indication of how a company is doing in comparison with similar entities. Market share accounts for the market variables and performance from year to year. Market share can also provide information about the financial health of the organization. Market share is calculated by dividing the company's sales revenue by the total revenue produced for a product or service in the entire market, and then multiplied by 100 to express market share as a percentage. It's been shown that keeping existing customers is more profitable than winning new ones, and the longer that you keep customers around, the more profitable you become. This is why customer satisfaction is one of the key business drivers within Six Sigma and other continuous improvement initiatives. The best way to keep customers is to meet or even exceed their expectations. One of the typical first steps within a Six Sigma improvement project is developing an understanding by the team of a customer's requirements and expectations. This allows the team to determine how the company can meet those needs. Six Sigma organizations continuously measure customer satisfaction. This helps these organizations manage their customer relationships and use this measure to achieve continuous improvement. Organizational efficiency represents how well a company uses its resources to achieve their strategic goals. In financial terms, organizational efficiency lies in an organization's ability to optimize its bottom line based on capital required, either through equity or debt. Improved organizational efficiency usually results in lower cost, optimal resource allocation, and greater agility and sustainability of the organization. There are several ways to improve organizational efficiency: by developing quality systems and by implementing process improvement and continuous improvement efforts. Product differentiation is a business-level strategy that's intended to increase the perceived value of products or services compared to the value of your competitors' products or services. This creates a customer preference for your organization's product or services. Factors that can provide differentiation include product features, superior quality, a refined delivery channel, and a specific marketing approach. Organizations that use product differentiation as a driver typically seek to be unique in the industry, along all of the dimensions that are widely valued by the customers. If an organization can exploit its advantage effectively, then customers may be willing to pay a premium for that uniqueness, which results in increased profitability for the organization. In this topic, we're going to discuss organizational metrics. There are numerous possibilities when choosing the right metrics to evaluate a process. It's important, though, to choose the most appropriate metric for a specific project or process, because time can be wasted collecting data for metrics that aren't really useful or appropriate. Different metrics may be more appropriate for use at different levels of the organization or for specific processes. However, there are several characteristics that good metrics have in common. For example, all good metrics are developed in conjunction with the employees who have the best knowledge of the process that you're measuring. Metrics should also be linked to organizational goals. Different types of metrics are used to address different goals at different levels in an organization. The types of metrics fall into three categories: business metrics, operations metrics, and process metrics. Let's take a closer look at each of them. Business metrics are typically used to measure the financial aspects of an organization or quantify high-level aspects of the operations. Some of the metrics used at the business level include return on equity, earnings per share, growth to expenses ratio, and return on investment. These metrics are usually reported in financial reports or operational status reports. Operation metrics measure the aspects of the operational activities within an organization, and the aim is to improve and guide the management of these operations. These metrics give a high-level overview of how operations are running, for example, the percentage of returned products. And process metrics give detailed information about the frontline production processes. They're typically used to monitor production and the machinery. All processes within an organization are linked to some form of a system. For example, the output of one process might be the input to another process. And because of this relationship, the metrics are also linked. All processes have inputs and outputs of different types, and these inputs and outputs are in the form of variables. Process inputs are normally the physical materials and labor that are needed to complete a process. They might include controlled and uncontrolled variables and internal variables. These types of inputs are categorized as key process input variables. Key process output variables are those important outputs of a process, and these can vary at the different levels of an organization. Key process output variables at the strategic level typically include profits, customer satisfaction, and quality, while at the operational level, key process output variables could be the number of defects in a product. Different types of metrics are linked to different types of goals within an organization. Corporate level goals are the strategic aims of an organization. Business metrics are also referred to as strategic metrics, and these are commonly linked to corporate goals. For example, we could have a goal to increase overall revenue for the company by 20%. Appropriate metrics to measure this could be profit, revenue, or return on investment. Department-level goals could include things like increasing the sales department revenue by 15% to meet market expansion goals. This type of goal is quantified by operations-level metrics such as percentage of sales growth per year. Tactical-level goals aim at the functional level of production. For example, the goal could be to reduce the cycle time for making a key helicopter component from 3 months to 15 days. This type of goal is quantified through process-level metrics such as cycle time. Now let's take a look at an example. Consider a large aircraft engine manufacturer, which has specific metrics that are linked to different levels of goals. A strategic goal of the company is to achieve a 99% customer satisfaction rating in all of its production lines. The metric associated with this is the number of customers that have purchased more than one product from the organization. The business or department goal is to reduce the defect to 5.5 sigma. This metric is used to measure the number of defects per million opportunities. And then the process or tactical level goal of the company is to have 75% of the managers and supervisors complete Six Sigma Green Belt training. The metric associated with this is then the number of these employees that have been sent for training. Metrics are a critical aspect of Six Sigma. So what exactly makes for a good metric? A good metric has several attributes. First, it measures performance over time. A metric must indicate any emerging trends and isolated measurements at static points, and a process just can't do this. A metric needs to give direct, clear, and unambiguous information about the process that you're trying to quantify. This enables managers to see the process at a glance or in the larger context of emerging trends within the process. It also needs to be linked directly to an organizational performance goal. The main function of a metric is to give an indication of whether a goal is being achieved or if it's not being achieved. It also needs to be practical. This means that the employees that are most familiar with the process for which that metric is being developed are involved in developing the metric. And finally, the metric needs to be easy to collect and use. When designing a measurement system of a given metric, there are several considerations to take into account. First, there's typically many metrics that are used to evaluate large projects. Each one, though, should have a different person overseeing its collection and use. If one person is responsible for too many metrics, they can become confused, and that extra work associated with collecting metrics may also mean that the quality of the data being collected is sacrificed. The metrics also need to operate over time so that they can indicate trends. Because of this, metrics need to be selected so that the past history of the processes is considered, as well as the present operating conditions and the potential future direction of the process. In designing the system of metrics, the managers and analysts also need to consider that processes are not static. They will change and evolve over time. Therefore, the metrics also need to be flexible enough to change and adapt as the processes change. Metrics also need to address all of the relevant performance goals that are linked to that specific process or project. Several metrics working together give a much better picture of how well goals are being met, rather than numerous unrelated metrics. And finally, the perspectives of all stakeholders involved in the process need to be considered when choosing the metrics for the measurement system. What may be important for one type of stakeholder may be uninformative to another, and therefore different levels of metrics should be incorporated into the system. The Balanced Scorecard is a management system that helps to align the metrics of an organization to their strategy and goals. The Balanced Scorecard was developed in the 1990s by Dr. Robert Kaplan, a professor at the Harvard Business School, and Dr. David Norton, president of the Palladium Group. In terms of Six Sigma, the Balanced Scorecard helps to link the Six Sigma goals to the organizational vision. The Balanced Scorecard is a way to view an organization from different perspectives. Then managers can develop or select metrics that adequately evaluate the organization from these different business perspectives. There are 4 different perspectives that a Balanced Scorecard addresses. The first is the financial performance, and this is a traditional way of viewing an organization in terms of profit and financial status. The typical metrics associated with this perspective are net income, return on investment, market share, and cash flow. The next perspective is customer. It's important to view the organization with a customer in mind because this gives a different perspective when choosing metrics. Managers need to understand who the customers are and what their needs are in order to meet customer-oriented goals. The metrics typically associated with this perspective are customer retention, customer satisfaction, number of complaint logs, and customer loyalty. The third perspective is the internal business process. Viewing a company in terms of its internal business process is important in establishing how well those processes are running. Metrics from this perspective include project management, throughput, and Six Sigma. The final perspective is learning and growth, and it's important to view an organization from the perspective of learning and growth because many knowledge workers have a goal of continuous learning. Metrics that are typically associated with this perspective are staff morale, training levels, amount spent on training, and the extent of knowledge sharing. Now let's take a look at an example of how the Balanced Scorecard is used with a Six Sigma project. The Chief Operations Officer of a company that manufactures aluminum cans is using a Balanced Scorecard approach to link the goals and the metrics on the latest project in the beverage department. The first area on the scorecard that she considered was the financial performance area. The goals of the new beverage project were already established, and the financial goal was to provide the cheapest product to the market and undercut the competition by at least 5%. Thinking about the metrics from this perspective, she chose cost per unit as the metric. The next perspective that she looked at was the customer perspective. The customer in this case was a large beverage manufacturer, and customer satisfaction was a primary consideration here. The COO therefore chose to measure this using a survey completed after the project was delivered. Then, when the COO considered that the new beverage project from the internal process viewpoint, she decided that Sigma levels of the production process needed to be considered to ensure proper quality levels. This metric addressed the goal of achieving Six Sigma in internal production processes, and it also linked to the goal of satisfying customers, which is an associated metric. The final perspective that the COO approached for the new beverage project was a learning and growth view. To measure training effectiveness, she chose the metric of the number of people trained in Six Sigma methods. This metric gives an indication of how capable the organization is to handle the new project and to achieve the process goal of Six Sigma. Lean is a continuous improvement initiative that aims at streamlining processes and reducing wastes. Lean has its origins in the Japanese manufacturing industries in the 1950s as a waste reduction and improvement methodology. However, as it turns out, these methods and principles of lean thinking have spread to logistics, and from there on to military and construction industries. Lean methodologies and principles have since been applied successfully across many other industries, including service and transactional industries including healthcare, insurance, financial services and banking, call centers, government, retail and transportation, among many others. Lean is a methodology that incorporates a powerful set of tools and techniques designed to maximize customer value, while reducing waste along the entire value stream. It also focuses on improving overall efficiency, quality, and customer satisfaction. Due to its ability to improve customer satisfaction and deliver bottom-line financial gains to an organization, Lean is a preferred strategic choice for many business organizations. An organization moves from identifying waste to eliminating waste through 4 stages of the Lean methodology: identification of the opportunity, design of the solution, implementation of the solution, and continuous improvement. Let's examine each of these stages in more detail. During the first stage, several important events occur to prepare employees to identify improvement opportunities. This includes training, understanding values defined by the customer's needs and expectations, and then identifying the opportunities that exist within the current processes. Once the opportunity is identified, then stage 2 is where a solution is designed. For example, the process and flow that produce each finished product or service are identified. Then, non-value added activities are pinpointed, exampled, and slated for elimination if possible. In the third stage, solution implementation, the teams decide which improvements to address first. Many of the project teams begin with focusing on the low-hanging fruit. These are improvements that involve the employees directly without management involvement and can typically be made quickly and cheaply. And these are also processes that have highly visible waste. It's important as a team to really identify those opportunities that exist and prioritize which improvements to address first. The last stage of the Lean methodology strategy is to attain perfection through continuous improvement. Employees who have been trained to think about their work as processes and have been empowered to success and enact improvements should take ownership of their processes. Then the team members should continue to troubleshoot to find new ways to eliminate waste and monitor the processes to ensure that the improvements are sustained. At the same time, the team should identify new ideas for waste elimination and act upon these. The Lean tools fit nicely into the Six Sigma DMAIC methodology. In terms of general Lean concepts, there are tools such as theory of constraints, value chain flow, and perfection that are used throughout the Six Sigma DMAIC methodology for deployment within an organization. In the improved stage of the Six Sigma DMAIC methodology, tools that focus on waste elimination, reduction, and prevention, and efficiency improvement are the focus. These include tools such as MUDA, or the 7 wastes, value stream mapping, pull systems, Kanban, 5S, standard work, and Poka-yoke. In the control phase of the Six Sigma DMAIC methodology, the Lean tools that focus on process control, such as total productive maintenance and visual factory or visual control, are used to control the improved process. While Lean and Six Sigma are both methodologies that focus on continuous improvement, there are several key differences between the two methodologies. First, each methodology has a different focus. Six Sigma focuses on reducing variation, while Lean focuses on removing or reducing waste within the process. These methodologies are also slightly different. Six Sigma follows the 5-phase methodology of define, measure, analyze, improve, and control, or the DMAIC methodology, while Lean follows 4 steps to identify the problem, design a solution, implement a solution, and then a focus on continuous improvement. The tools used in Lean and Six Sigma methodologies overlap significantly, although each toolbox has some methods and tools that the other does not use. For example, Lean relies on pull scheduling, setup reduction, and the 7 wastes. Six Sigma uses advanced statistical tools such as design of experiments and hypothesis testing. Six Sigma comes equipped with a large toolkit of prescribed tools and methods to use in each stage of the DMAIC methodology. Increasingly, though, Lean and Six Sigma are being combined as an integrated methodology, and tools that were formerly specific to Lean are now being used within Six Sigma with great success. The primary effects are also slightly different. Six Sigma focuses on eliminating defects through variation reduction and improving customer satisfaction. Process variation is understood and brought under control by applying the DMAIC methodology and sophisticated statistical tools. Lean focuses on increasing the velocity of processes by eliminating barriers and waste, speeding up the production processes, eliminating non-value-added activities, and reducing inventory. Finally, the key concepts and underlying assumptions are slightly different. With Six Sigma, the assumption is that as you reduce variation, you're also reducing defects. And this is done through data and analysis support improvement. With Lean, the assumption is that as you remove waste, you're improving your business continuously, and small improvements are preferred. Despite these differences, Lean and Six Sigma are very similar and complementary. First, both methodologies were inspired by the Plan, Do, Check, Act cycle. During the first step, Plan, when a problem is identified, the cause is determined. Then a plan is made for solving the problem. This is done with the participation of employees and management. In the next step, the Do step, the improvement plan is communicated to all employees, who take responsibility for achieving the desired results. If the workers face any difficulties, or if the plan is not working properly, those differences will be identified in the check phase of the cycle. Finally, in the act phase, when the necessary results are achieved, they are documented and the standards are set in order to prevent the problem from reoccurring. The plan is iterative, so if the results are not achieved, the plan is repeated until they are. There are other similarities between Lean and Six Sigma. Both use systemic problem-solving tools. In addition, both depend on project teams and specialists for implementing and supporting the process improvement efforts. It's important to note that, typically, Six Sigma relies on this more heavily than Lean does. Both Lean and Six Sigma also require employee participation, and this often results in widespread behavioral and systemic changes, as well as a happier and more engaged workforce. And finally, both Lean and Six Sigma deliver significant bottom-line results. Lean is a continuous improvement initiative that streamlines and improves processes by reducing waste and cycle time. Though Lean and Six Sigma are initiated as two different strategies and two different environments with different tools and methodologies, they are increasingly being seen as complementary processes. In keeping with this perspective, the combined methodologies are commonly referred to as Lean Six Sigma. Six Sigma helps organizations reduce defects and improve quality. Lean thinking helps reduce waste and improve process flow and speed. Due to the complementary nature of Lean and Six Sigma, many organizations are choosing to incorporate the Lean approach into their overall Six Sigma strategy. As more and more organizations adopt the combined methodologies known as Lean Six Sigma, a body of knowledge is building about how to best use the combined strengths to execute organizational strategies and gain and keep competitive advantage. Wasted time and effort translate into lost business opportunities and revenue. The Six Sigma methodology and the Lean initiative allow improvements to be made across an entire organization to address these problems. This results in errors being reduced, quality is improved, and businesses perform faster. The benefits brought by implementing Six Sigma are typically larger and have more of an impact than most other business improvement strategies. Let's take a look at the combined Lean Six Sigma methodology. The combination involves using Lean methodologies to identify and remove non-value-adding activities and processes and then applying Six Sigma methodologies to identify and eliminate process variation. This fusion of Lean and Six Sigma is necessary because Lean alone cannot bring processes under statistical control. And Six Sigma alone cannot dramatically improve process speed or reduce waste in the processes. By integrating Lean and Six Sigma tools and processes, we're able to create a powerful combination to improve quality, efficiency, and speed in every aspect of a business. Continuous improvement practitioners often debate about how to define the relationship between Lean and Six Sigma. Lean focuses on increasing the velocity of processes by eliminating barriers and wastes. This speeds up production processes by eliminating those non-value-added activities and reduces inventory. Six Sigma focuses on eliminating defects by reducing process variation, which results in improved customer satisfaction. The process variation is understood and brought under control by applying the DMAIC methodology. It's important to understand which tools you will use, Lean or Six Sigma. And there are questions you can ask around certain criteria that will help you choose whether Lean or Six Sigma tools will work better for your situation. The first is around the time frame and financial commitment. Lean is appropriate when you need a quick and relatively inexpensive strategy for reducing time. However, if it's feasible and worthwhile to apply rigorous statistical tools to uncover root causes of a problem, then Six Sigma might be more appropriate. Lean tools generally provide fast results, while Six Sigma tools require a longer time frame. The second criterion is around the nature of the problem. Here we're trying to ask, what is the primary problem that we need to address? Is it waste or speed? Or is it defects and variation in processes? Lean tools help reduce waste and increase speed, while Six Sigma tools generally address defects and variation in processes. The next criterion is around the capacity for change. We're trying to ask, how quickly can your organization change in response to a new improvement methodology? Lean tools can be implemented while people are still getting used to a new way of thinking. However, Six Sigma tools usually require a longer time frame. The next criterion is around the pervasiveness of the problem. If it's isolated and relatively simple to fix, Lean tools might be more appropriate. However, if it permeates the entire process, then Six Sigma might be the right approach. Lean tools are useful for addressing low-hanging fruit, problems that are relatively simple to fix, while Six Sigma tools and techniques are used for addressing more pervasive problems. Now, let's examine how the Lean tools line up with the 5 stages of the DMAIC methodology. In the define phase, the project team is concerned with defining the problem, the project goals, and customer deliverables. A required deliverable in the define phase is the process map. In a Lean Six Sigma methodology, the process map is replaced by the value stream map, also referred to as VSM. A current state value stream map can be used in the define phase, and a future state value stream map can be used in the improve phase. During the measure phase, lead time measures the time between the initiation of a process and the completion of a process. Takt time is the amount of time available to produce a unit of product as required by the customer. Any variation between these two times indicates a problem. In the analyze phase, the value stream map can also be used to look for process improvement opportunities. During the improve phase, the project team analyzes and determines the root causes of the defects. The 7 waste tool can be used by the team to quickly focus on reducing waste that's found to be a key issue. Value stream mapping is useful for identifying opportunities for efficiency. The 5S methodology can help improve a process and eliminate waste through organization, cleanliness, and workplace standardization. Kaizen is a method for continuously improving a process through incremental process improvement, rather than a leap caused by re-engineering or redesigning a process. Using the Kaizen philosophy helps to maintain those improvements. Just-in-time or Kanban tools are used for inventory reduction and control. Variation in the inventory processes is a common cause of problems, and this is where just-in-time or Kanban tools can be useful to a Six Sigma process improvement team. Finally, Poka-Yoke is an analytical approach that involves analyzing a process to uncover where human errors could occur, and then implementing procedures that prevent these errors from occurring. In the control phase, lean visual factory tools and total productive maintenance are useful tools for controlling future performance. Visual factory tools such as charts and schedule boards help maintain control over processes. Lean concepts and tools have been applied in the manufacturing and service sectors alike. In Lean's application in service industries, the key concepts of Lean are adopted when there is a flow of intangibles and services instead of materials and products. For example, Ford Motor Company, a global automotive manufacturer, eliminated waste in manufacturing, supply chain, and service processes by using Lean Six Sigma. Standard Life, a UK-based investment company, improved customer satisfaction by transforming service and transactional processes through the application of Lean concepts and tools. There are several benefits of applying Lean concepts and tools to an organization to increase safety, capacity, yield, performance quality, and the level of team integration. By improving work practices and ensuring high-quality products, you boost employee performance and customer satisfaction, and overall costs and inventory costs are lowered. All of this ultimately boosts profitability. Other benefits are that lead and cycle times are reduced, efficiency and quality are improved, communication between the organization and customers is improved, and the physical workspace and facility needs are reduced, and process flexibility is facilitated. There are 5 Lean laws that many companies have adopted to guide managers in their approach to the initiative. The law of the market means that the customer is the highest priority. Customers are your target market, and without them, you have no business. All aspects of the organization and its processes should be geared toward keeping the customer satisfied. The law of flexibility is that the velocity or speed of a process is proportional to the flexibility of that process. This means that the speed at which a process can run is directly related to how flexible and adaptable to change that process is. The law of focus is that 20% of activities cause 80% of the problems or delays in a process or operation. This is the Pareto principle in action. The law of velocity states that the velocity of any process is inversely proportional to the amount of work in progress. This is a very useful indicator of lead time, because the more work in progress you have, the slower the process and the longer the lead time. The law of complexity states that complexity adds more non-value and cost than either poor quality or slow process speed. This essentially means that complex products create more waste and less value than poor quality products or a slow process speed. Therefore, keeping the product or service as simple as possible is vital to achieving Lean. The concepts underlying the Lean way of thinking can also be thought of as the steps in the application of the Lean philosophy. Each one builds on the last. In order to successfully apply Lean in any organization, management needs to adopt the 4 key concepts of Lean, which include value, value stream, pull, and perfection. The first concept is value. Value is ultimately defined by the customer. It's a measure of how well a product or service meets the customer's needs. An important part of the Lean approach is to shift to focusing on the customers and their requirements, rather than on the internal processes. The first step that management must take to apply Lean in an organization is to identify what creates value, based on what the customer determines is value in the processes or products that you offer. A key aspect of this is good communication, which facilitates the transfer of information between the customer and the organization. Communication between the customers and the organization should be ongoing to ensure that any change in value is noted as soon as possible. Also, changes in processes and products can be made to meet those changing needs of the customer, which will allow the organization to stay ahead of the competition. The second key concept underlying the Lean philosophy is the value stream. The value stream represents all the activities and processes that are involved in producing a final product. This includes the value-added and non-value-adding activities. The value streams can be traced for each product or service offered by an organization. The value streams involve the suppliers, the organization, and the eventual customers or consumers. It's important to note that not all steps or activities add value. These are called waste steps. Eliminating these waste steps from the process in the organization is a fundamental goal of Lean. Identifying the value stream allows managers to recognize where process improvements should be made, and where the value stream can be optimized by removing those waste steps. This may mean restructuring a process so that it flows more smoothly. The third key Lean concept is pull. Applying Lean in an organization means shifting to a system where customers pull products through the value stream. This means that the organization makes what the customers actually request as they ask for it, rather than producing a set amount of goods based on sales forecasts and market predictions. That's referred to as pushing products to the value stream. For example, rather than producing 500 computer motherboards based on sales forecasts, a large computer parts manufacturer changed to a pull system, where they only manufactured motherboards as customers ordered computers. This means that the motherboards are manufactured, immediately placed in computers, and shipped to customers. Essentially, every motherboard that is manufactured has already been sold to a waiting customer. The fourth key concept of Lean is perfection. Organizations should aim for constant improvement in processes and products. This means reviewing processes and customer needs to strive for the ideal product or service as required by the customer. Once products with a value are being pulled through the value stream, the processes involved are reviewed and optimized in each ongoing cycle of improvement. To reach your destination, you need a map. A 5-step process can help you implement Lean and begin reaping its benefits. First, you identify value and map the value stream. You can create flow, establish pull, and finally seek perfection. The final step then leads back to the first step, creating a cycle. The first step in the Lean process involves finding out what your customers actually want and how much it's worth to them. The second step, mapping the value stream, involves outlining all of the processes, tasks, and information needed to develop a product and service, and deliver it to your customers. The third step, creating flow, requires you to remove interruptions, bottlenecks, and periods of inactivity from the value stream. The fourth step, establishing pull, involves creating a system in which customer demand drives production. The last step, seeking perfection, is a continuous process of finding ways to improve on the first 4 steps. First, you should define value for each product or service your organization offers. This gives direction to the entire organization's work processes, determining what, how, and whether it should provide specific goods and services. In Lean thinking, the customer defines value. The customer could be a person, team, or a company that's using your product or services. The value that a customer assigns to a product depends on factors such as the product's quality, capabilities, and price, and how well it meets the customer's expectations. Customers of a casual clothing retailer, for instance, may place a high premium on variety, style, and affordability, while customers of a more upmarket retailer may assign greater value to quality and personal service. In addition, customers of a healthcare provider are likely to value rapid service, accuracy, professional expertise, empathetic treatment, and a tranquil environment. Once you've identified value, you map your organization's value stream, including all of the steps that are used to bring a product or service from conception to delivery to the customer. The goal in doing this is to help you identify and eliminate the waste in your process. Waste are any steps that don't produce value or that create obstacles in the process flow. So how do you map a value stream? First, you walk backward through the entire production process and then draw the current and future state maps. Finally, you develop an action plan for moving from the current state to the future state. Once you've analyzed the value stream in your organization, the next step is to optimize the flow of value through the value stream. This involves removing all of the obstacles, bottlenecks, or wastes. 3 strategies for creating flow are organizing people, ensuring quality at the source, and ensuring that equipment is reliable and well maintained. Establishing pull is about supplying products at the same rate at which customer demands or consumes them. The customer should pull the production rather than pushing products out to the customer based on forecasts. Products or services are then created only when there is a customer demand for them. Similarly, goods and information are supplied or moved only when they're required. The concept of pull builds on the basis of good flow in the value stream, and it improves it further by reducing inventory and the time it takes to produce a product, which is known as the cycle time. The aim is to communicate real-time requirements to trigger production at each step. This synchronizes the production so that products are made only as needed. To move your organization from a push to a pull system, you level out production and then use Kanban to signal replenishment and adjust the supply and delivery logistics. The final step in the lean process is to continuously seek perfection. This is done by identifying and incrementally modifying practices that can be improved. A useful tool in implementing continuous improvement is the Plan, Do, Check, Act cycle, or PDCA cycle for short. In this topic, we're going to spend some time exploring some of the lean tools commonly used in Six Sigma initiatives. These include the 5S methodology, Just-in-Time, Kanban, Poka-yoke, Kaizen, and Kaizen Blitz. So, to begin with, the 5S methodology aims for the continuous improvement of the general work environment. This includes both mental and physical work. It was developed in Japan, and each S stands for a different Japanese term. Translated from the original Japanese word seri, the sort aspect of the methodology involves separating the needed from unneeded items, eliminating the unnecessary ones, and clearing out the clutter. Translated from the original Japanese word of sitan, the straighten aspect of the methodology involves arranging and organizing the necessary items remaining after the sort stage and setting everything in order. A commonly used phrase for this is a place for everything and everything in its place. Translated from the original word seiso, the shine aspect of the methodology involves cleaning the work area, removing trash, and defining the standards of cleanliness to adhere to. It also includes repairing any broken machinery. Translated from the original Japanese word seketsu, the standardized aspect of the methodology involves maintaining the clean work environment by setting a regular cleaning and maintenance schedule. This is a step where the previous 3 S's are standardized. Finally, translated from the original Japanese word shisuke, the sustain aspect of the methodology involves maintaining the 5S approach to work, ensuring that the method develops deep roots within the organization and establishes 5S as a normal way of doing things. The key benefits to applying the 5S approach are improved work efficiency, reduced waste, and increased speed. An additional benefit is that employees are empowered to take control of their work environment, which leads to improved employee morale. In addition, workplace safety often improves as well, because the work area is cleaner and tidier, and the chance for accidents is reduced. A cleaner work area also means that fewer mistakes are made, which results in improved quality as a final output has fewer defects. In a JIT environment, materials arrive at the exact time and place they are used with no waiting or storage needed. Therefore, on-hand inventory is reduced, if not eliminated, as materials enter the next phase of production immediately. In non-manufacturing situations, work flows more smoothly between departments, and there's no waiting around for vital information. JIT reduces waste by allowing a process to produce items as they are needed, rather than storing large stocks of material and finished goods. JIT also helps save in terms of inventory holding and handling costs. A just-in-time environment must be tightly controlled, regulated, and coordinated to be successful. Some of the common characteristics of a JIT environment are that demand triggers production, which assists in the lean concept of pull. Workers are skilled in several areas so that they can help with different process aspects as needed. Lead time for production or completion of work is reduced. Potential suppliers are carefully screened to ensure that they are reliable. And finally, related process elements or departments are in close physical proximity to one another to improve communication. Kanban is a Japanese term that means signal in English. It is an inventory control system that indicates whether material or stock is needed by a process and tells an upstream supplier to send material downstream. Upstream suppliers do not necessarily need to be external, but may be internal coworkers or a preceding station in an assembly line. The Kanban system was originally implemented as a manual system using visual cues, such as cards attached to storage bins. A more modern system uses electronic notices that are passed between departments until the supplier is notified of the need. The Kanban system is a pull system, meaning it pulls materials and stocks into the process rather than waiting for a scheduled time when materials and stocks are pushed forward into the process. In a Kanban environment, manufacturing only begins when there is a signal to manufacture. This is in contrast to a push manufacturing environment where production is ongoing. The Kanban system has numerous advantages and disadvantages. The advantages of the pull-type Kanban system are that it avoids overproduction by regulating the amount of materials available. It also improves the overall quality and inventory control, and it also reduces setup and manufacturing time. The disadvantages of the Kanban system are that no inventory buffer exists to carry production over in the event of non-delivery, and there are potential bottlenecks. The system can fail if organizations become reliant on the supplier's ability to deliver on time, and if there's no provision for unforeseen events. Poka-yoke, or mistake proofing, is another lean tool. Mistake proofing is an analytic approach that involves examining a process to uncover where human errors could occur. Potential errors are traced back to their source, and their potential is reduced by using a Poka-yoke device. Poka-yoke devices prevent inadvertent mistakes that result in defects. These devices are usually very simple and inexpensive. For example, the connector of a computer keyboard is a specific shape to prevent it from being incorrectly connected, thus avoiding potential damage to the computer. Kaizen is a Japanese word that has come to mean continual process improvement. It is an important lean tool and involves constantly improving a process through incremental steps, rather than through a leap caused by re-engineering or redesigning a process. Process improvement can take up to 6 months to bring about the changes to a process. But change can be forced to happen quickly with a Kaizen Blitz. A Kaizen Blitz is also typically called a Kaizen event, and it's an intense process that usually lasts about a week. During a Kaizen Blitz, a multidisciplinary team spends time learning lean techniques, focusing in on a process, deciding potential improvements, and then implementing these improvements to improve the process. The toolkits for Lean and Six Sigma originated on the shop floor to improve manufacturing processes. Eventually, however, people involved with marketing, sales, and finance started using some of the tools and techniques, and found that the tools were just as effective in improving service processes as they were with manufacturing processes. As more and more service organizations started reaping the benefits and sharing their success stories, the methodologies gained more popularity in a variety of service organizations. Today, almost an equal number of service organizations, including hospitals, hotels, banks, software, and IT companies, along with many others, are using Lean Six Sigma to improve their organizations and build for future growth. Services have 4 unique characteristics that make them different from manufacturing processes. A service is often an action or an event. It's not something that can be held in one's hands. For example, a doctor gives a physical examination, or an insurance agent discusses a claim over the phone. Services can't be produced and stored for future use. The actions of a desk clerk when you check in at a hotel are a service. The outputs of services can't be stored and must be consumed on the spot. The outputs of a service are variable. For example, a concierge at a hotel provides many different services, and each service is initiated by a customer request. Each request can be different and can result in many different outputs. Because services are perishable, the output of a service is consumed at the same time or shortly after it's produced. For example, in a call center, the service is a solution to a problem. The solution is created and delivered to the customer at the same time. When a service organization decides to improve its processes by adopting Lean Six Sigma, one of the key activities is to define what quality means for services. The key elements of delivering customer value in a service organization are excellence in each and every aspect of service quality. Applying Lean Six Sigma in a service organization means identifying those costs and procedures that contribute to improving customer satisfaction. Generally, there are three things that make up quality as a customer perceives it. First, the organization must define what its product is in terms of the value that is delivered to the customer. This is the service product, which is equivalent to the product created by a manufacturing operation. For example, in a healthcare service, the service product includes diagnosis and treatment. In transportation, the service product is a trip to the destination, plus the porters, flight attendants, baggage handlers, and beverages. The elements that comprise a service product must be carefully defined. A 4-star restaurant and a fast food diner both provide a dining experience. However, the factors that comprise their service products are very different. In addition to defining a service product, the organization must define how that product will be delivered to the customer. This is a service delivery process. Similar to manufacturing, a service process generally contains a number of steps. For example, the service product of an insurance company is an insurance policy. The service delivery process includes all of the steps required to deliver the policy to the customer. These steps include making sales calls, signing the contract, entering the contract into an IT system, printing the policy, and mailing the contract to the customer. The third aspect that a service organization must define is the nature of the customer-provider interaction. Consider what happens when you go to your local supermarket. The checkout clerk greets you, scans your items, processes your coupons, makes change, and sometimes bags the items. The same kind of interaction happens in every retail establishment. In contrast to manufacturing, all service organizations have a direct interaction with their customer. The customer-provider interaction has an enormous impact on how your customers feel about your organization. Let's explore an example of Lean Six Sigma in the service industry by using the example of an online mail ordering system. The accounting department and external customers of an online mail order company are complaining about the organization's invoicing system. It takes much longer than it should to complete and submit an invoice. Also, the customers find the invoices confusing and often have to call the accounting department for clarification. A preliminary investigation indicates that in addition to other problematic issues, there is no standard operating procedure for filling out the invoice. Management decides to take immediate action. The cost of poor quality, or COPQ, is used to justify the product financially. It is estimated that it costs the company $400,000 per year, plus the lost customer goodwill. A goal was established to reduce the invoice processing time by 50%. Management decides to use Six Sigma for its structured DMAIC problem-solving methodology and a rigorous toolkit and statistics in order to control the improvements. Management also decides to pull in lean tools and techniques as needed within the DMAIC structure. During the define phase, the project team identifies the parameters of the problem and determines how to conduct the project. The team uses the project charter first. The project goal, scope, budget, personnel, resources, and the problem to be resolved are documented in the project charter. A SIPOC diagram is drawn to learn all of the relevant elements of the project, including the suppliers, inputs, processes, outputs, and customers. The team members interview employees and external customers to learn what level of service they expect from the help desk. In addition to phone interviews, the team members also send out surveys. During the measure phase, the team collects data about cycle time and help desk processes. The cycle time is found to be 167 minutes, with a standard deviation of 81 minutes. The team also creates a detailed process map. The inputs and outputs of each step are identified, and the team determines whether steps are controllable or not. Steps that are controllable can be improved. Next, during the analyze phase, the team analyzes each step of the process map. The team also brainstorms intensively and creates the cause and effect diagram to identify all of the potential causes of long invoice processing times. The team concludes that the root causes of longer than acceptable processing times are the lack of a documented operating procedure and lack of expertise among the technical help desk personnel. The team adopts a multi-pronged approach during the improve phase. The team recommends to the organization that they develop a standard operating procedure to help deliver the services quickly and efficiently. They also recommend establishing a requirement that anyone wanting to work on the help desk must have a minimum of 2 years of technical experience. And the final recommendation is to monitor the help desk semi-annually to ensure that employees are staying current with the changes in technology. During the control phase, the last phase of the Six Sigma project, the team creates a checklist for internal management to use. The team also creates a control chart to monitor service processing time over the long term. So what was the result? The Lean Six Sigma project that ran slightly over 4 months helped reduce the processing time from 167 minutes to 80 minutes. This also resulted in a total cost savings of $300,000. While the Lean Six Sigma project ran slightly over 4 months, it was able to reduce the invoice processing time by 50%. The team used the Six Sigma DMAIC methodology in addition to SIPOT process maps, statistical tools, and control charts. This also resulted in a cost savings of $300,000. Since all manufacturing organizations share a purpose, making good quality products as efficiently as possible for customers, they all have a number of processes in common that can benefit from Lean Six Sigma improvement. For example, improvement in quality assurance processes reduces the number of product defects, customer complaints and claims, and also the amount of rework and scrap. Operations can be improved to reduce lead times, late orders, average cycle time per order, instances of emergency maintenance, and scrap and rework. Purchasing processes can be improved to reduce the cost per invoice and purchasing errors, and to consolidate the number of suppliers. Also, distribution processes can be improved to consolidate the number of shipments, reduce freight charges, reduce the level of returned products, and eliminate late deliveries. Let's examine how a large playground equipment manufacturer used Lean Six Sigma tools to resolve problems and meet organizational objectives and improvement goals. Intent on maintaining its competitive advantage and increasing profitability by at least 3%, the company launched the Lean Initiative. Management was intent on reducing lead time, improving efficiency, and eliminating scrap and rework. An outside consulting group was hired to provide training in lean thinking and techniques. The initiative began by targeting low-hanging fruit first. This started the ball rolling and got everyone on board with the practice of continuous improvement. Eventually, several lean tools and techniques were used, including value stream mapping, Kaizen Blitz, and the Plan, Do, Check, Act cycle. After 2 years, the company cut lead time by 60%, improved productivity by 22%, and decreased scrap from 0.8% to 0.6%. The company also achieved a just-in-time approach to inventory management and effected a culture change throughout the organization. The employees became highly motivated by continuous improvement, and they expressed pride in their work and their company. However, clearing out the low-hanging fruit revealed a deeper, more persistent problem. Pinholes were discovered in the PVC coating on the pipes used to make the playground equipment. The pinholes created a large amount of scrap and generated returns from unhappy customers who received the defective equipment. To resolve the problem, management turned to Six Sigma tools and techniques. A cross-functional team was formed, and the team spent time on the shop floor observing the process and talking to the various employees. They took measurements on temperatures, PVC thickness, and tolerances in order to perform a rigorous analysis required by Six Sigma. Detailed process mapping enabled the team to isolate the root cause of the problem to the welding process. The brazers were given no specifications on how to create their welds. They were expected to use their own judgment to achieve a good flame on their torches. Lack of a standard operating procedure permitted variation to enter these processes. To rectify the problem, a standard operating procedure was immediately created to instruct the brazers on how to achieve the right flame. This reduced variation and also vastly reduced the instance of pinholes in the PVC. During the analysis, the team identified another source of variation in the priming process. Operators were expected to remember which racks of pipes had been sent to the priming baths, but sometimes they forgot. The team solved this problem easily with a Poka-Yoke. An indicator light was installed on each rack to show which racks had been primed and which still needed to be primed. As a result, there was less variation in the process. Scrap was reduced to 0.02%, and returns were reduced by 30%. The theory of constraints, or TOC, was developed by Dr. Goldratt, a leading business consultant and thinker. The main concept behind the theory is that all systems have at least one element that's limiting them. This restrictive element is termed as a constraint, and it prevents the system from producing infinite output. It also stops the system from being any better than it currently is. Constraints to the elements dictate the level of performance in a system or organization. This also implies that the constraints are the leverage points for the system. The theory of constraints helps identify constraints and can be used in the define phase of a Six Sigma project. Once those constraints are identified, it can help appropriately handle improvements in the system during the improve stage. Some important questions to consider are how to leverage your constraints, how to optimize and work around these, and how to rethink them, pacing other operations to level out the constraints. For example, you reduce work in process, reduce inventory, reduce overproduction, smooth out production, or invest in those constraints. Dr. Goldratt's theory of constraints had several underlying principles. First, Dr. Goldratt compares systems to chains. A chain has a weakest link that prevents it from being better or stronger than it currently is. A system also has a weakest link or a limiting factor called the constraint. There can be only one weakest link or constraint limiting at a time. The remaining links or system elements are called non-constraints. The theory of constraints focuses on improving systems by fixing that weakest link, the system constraint in a chain. This is a slightly different approach than Lean, which focuses on eliminating waste. Removing constraints may remove waste from processes, thereby addressing Lean principles. To understand where changes should or could be made, a manager needs to understand the entire system, its goals, and all of the processes that are involved in it. As soon as the weakest link is strengthened, it's no longer the weakest link. The next weakest link becomes the constraining factor in the system, so the process starts again. Like a chain, a system is a set of processes and sub-processes in an interdependent relationship. The strength and performance of the system will depend upon the strength and performance of the constraining process. Therefore, it's vital to identify and fix the constraint if you want to strengthen the system. Strengthening the weakest link in a system brings about improvement and may eliminate process waste. However, strengthening any link other than the weakest link brings about no benefit to the system. Finally, systems work according to the Pareto principle, which states that 80% of problems are due to 20% of the causes. This means that 80% of the undesirable effects in a system are due to 20% of the potential causes. There are three types of internal constraints. The first are machines and equipment. These are physical in nature, and constraints can arise from the way they are used. Physical system constraints are easier to identify, and they usually have some visible element. The second type are people, and this involves any lack of ability or knowledge, because it can become a constraint. And the final type are policies and procedures, or rules. These constraints are non-physical in nature and more difficult to recognize. They could be written or unwritten, but they are often entrenched in an organization. They have been accepted as fact. Identifying and remediating constraining policies results in a larger degree of system improvement when addressed. For example, a factory is capable of producing 500 units in a day. However, the factory running this manufacturing process only has capacity to ship 400 units each day. Additional stock must be stored, but this will cause enormous shipping backlog, resulting in a warehouse full of stock that the organization is incapable of handling. so the process only produces 400 units per day, the amount that could be adequately handled and shipped. This limits the system and prevents it from reaching its potential of producing 500 units per day. There are 5 steps within the theory of constraints. The first step is to identify the constraint. Step 2 is to determine how to exploit or leverage the system's constraints. Then in step 3, you subordinate everything else to the above decision. In step 4, you elevate the system's constraints. And finally, at step 5, if a constraint has been broken in any previous steps, you go back to step 1. This forms an iterative circle. There are 3 critical interdependent operating measures for the performance of any system, business, or organization. They include throughput, inventory, and operating expenses. Throughput is the rate at which an organization or system generates output, such as money through sales. It can be thought of as money coming into the system. Throughput is not directly equal to sales revenue because payment costs for the vendors involved must be subtracted from the actual credit an organization receives from revenue. Throughput can be calculated as selling price minus the cost of production. Inventory includes all assets, materials, semi-finished and finished products, and parts that are locked within the system waiting to be processed for customers. In other words, this is money the organization or system has invested in things that it intends to sell. Inventory includes raw materials, work in progress, and finished goods. Operating expenses are the money that the organization or system spends, turning inventory into throughput. This is a measure of how much money is actually leaving the system rather than being reinvested in it. Operating expenses include the cost of consumable supplies, labor, and depreciation. The throughput, inventory, and operating expense measures help Six Sigma professionals define systems and get a handle on how they will respond to potential changes, such as those that are aimed to strengthen the system constraints. These measurements are the main source of feedback for Six Sigma professionals when deciding which changes should be made. In terms of these 3 measurements, there are only 3 changes that can be made to the system: increase throughput, reduce inventory, or reduce operating expenses. Reducing inventory and operating expenses is limited by the fact they are both vital to the continued functioning of the system. Beyond a certain point, a further reduction becomes counterproductive and begins to affect the system negatively. Technically, throughput could be increased indefinitely. Realistically, though, this is not true, as organizations don't have unlimited funds to support this activity, and there must be a market for the increased amount of goods that are produced. Considering these aspects, it's more likely that any action taken to improve the system will focus on increasing throughput, rather than decreasing inventory or operating expenses, because it's much easier to increase throughput. So, the basic model for system improvement focuses on increasing throughput, with decreasing inventory and operating expenses as a secondary aim. However, the optimal solution often incorporates elements of both of these solutions. The location of a constraint within a system is known as a bottleneck. In a bottleneck, the demand for service exceeds the capacity to serve. This means the throughput of the system is dependent on the throughput of the bottleneck. There are several techniques that can be used to alleviate bottlenecks. The first is leaning. Leaning is an umbrella term for a wide variety of tools in the lean methodology. An example of using leaning to alleviate a bottleneck would be to implement a Kanban pull. Standardizing a process means documenting work and doing it the same way every time. Standard work alleviates bottlenecks by saving time and preventing mistakes from being repeated. Mistake proofing, or poka-yoke, alleviates bottlenecks by preventing errors. For example, a factory machine might be designed to input material only one way so that it can't jam the machine. Flexible resourcing involves the provision of skilled people in the right place at the right time for the required duration. This prevents bottlenecks by providing human resources with options for completing work in a process. For example, work could be assigned to full-time employees, but contractors would handle overflow on an as-needed basis. Finally, job leveling is an analysis of each person's role in the process to determine where the improvement could be made. This prevents bottlenecks by making sure physical and human resources are evenly matched for maximum efficiency and effectiveness. An example of job leveling might be job sharing between 2 people with different skills. There are several additional measures that are used to define process results and system output in high-level terms that are meaningful in the context of the entire organization. The first is net profit. Net profit is the actual money that an organization makes by producing and selling a specific product. It's calculated by subtracting the operating expenses from the throughput. Return on investment is a measure of how much money is being made for each dollar invested in the process. Return on investment is calculated as the throughput minus the operating expenses divided by the inventory. Productivity is a measure of how much is being produced by the system in terms of saleable items. Productivity is calculated as the throughput divided by the operating expenses. And then finally, turnover is a measure of the rate that a system turns a work in progress into saleable items and eventually profit. Turnover is calculated by dividing throughput by inventory. Each person in an organization values different things, so it can be difficult to figure out what's wasteful and what's useful for the organization. Lean provides clear guidelines on this. It makes it simple to define what's valuable for a business and what constitutes a waste. According to Lean, value is a rating of how well a product or service meets the customer's requirements. If it's something a customer is willing to pay for, it has value. The different activities performed during a process either add value to the end product or they don't. So activities can either be value-added or non-value-added. Value-added activities are the actions and tasks that make a product more complete. These activities make a product or service more valuable from the customer's point of view. For example, connecting components, polishing a completed product, and delivering the product to a customer are value-added activities. Non-value-added activities are the actions that add no value to the end product or service from the customer's perspective. These activities include any non-essential actions that the customer isn't willing to pay for. For example, transporting components and conducting inspections are non-value-added activities. So let's explore an example. By slicing bread before offering for sale, an enterprising baker adds a step that makes his bread more convenient for customers. Customers become more willing to pay a little extra for pre-sliced bread. Any procedure a customer is willing to pay for adds value. It's likely that every procedure a company implements seems valuable to someone. For example, managers may value long, thorough hiring interviews. The interviews may have value for people inside the company and may also be necessary for hiring the right people for the company. However, customers may not be willing to pay for these procedures. According to a Lean perspective, hiring interviews don't add value. To determine if a procedure or activity adds value, there are 3 questions that you need to be able to answer yes to. The first question is, does it fulfill a customer's need or preference? When workers install bolts or attach a handle to a product, they are fulfilling a customer's need for a handle on the product. Customers expect to pay the cost of assembling the product and want handles, so this procedure adds value. The second question is, does it change the product or service in some way? Installing a spark plug in an automobile engine or cooking a hamburger makes a physical change in the item that helps it become a finished product. These activities are performed to add value. Similarly, a programmer who writes computer instructions or a banker who negotiates the interest on a loan are acting in a way that makes a change in a service, even if the change can't be seen. In an office setting, making and storing extra copies of documents doesn't change the service provided, so this activity doesn't add value. The third question is it done right the first time in the process? In Lean, activities are focused on getting things right the first time. For example, using a Poka-Yoke, which is a mechanism that automatically prevents or corrects errors as they occur, can add value by improving the quality of a product for customers. Activities that involve finding or correcting mistakes only after they've been made aren't value-adding. For example, a customer who buys a television won't find the product more valuable because the company that built it needed more than one try to get the wiring right. However, not all activities that fail to meet the value-adding criteria should be eliminated. Some non-value-added activities are necessary even if they don't change a product or service or meet customers' preferences. Other non-value-added activities may be necessary to operate the business. They may be needed to meet regulatory or accreditation standards that apply to your organization. These types of activities are known as required non-value-added activities. For example, writing a production report, paying wages, or even implementing a lean initiative are necessary for the efficient running of a business, even though they add no direct value for the customer. Typically, quality inspections are required non-value-added activities. At least one quality inspection is typically performed before a product is delivered to the customer as a risk management strategy. However, redundant or excessive quality checks don't add value and aren't required. Business support departments such as HR, IT, finance, and legal departments typically provide required non-value-added services. An organization's goal should be to minimize the effort needed by these services. For example, the payroll service ensures that employees receive the correct salaries on the correct dates. This service is necessary for maintaining their workforce. So, although the service doesn't specifically add value, it can't be eliminated. An organization can, however, reduce the cost, time, and effort associated with providing the payroll service. By identifying value from the perspective of the customer, you can gain a fresh view of what it is that your organization actually does. You can then focus on the value-added activities and minimize or remove the non-value-added activities, as well as modify or reduce the time associated with the required non-value-added activities so that they use less resources. So let's consider an example. An insurance company wants to eliminate waste and add value to its processes and procedures. For the company, an example of a value-added activity is creating modular packages to fit the different needs of its customers. Making hard copy backups of contracts and other documents and having employees walk into the file rooms to retrieve these documents is non-value adding. However, maintaining the document copies is regarded as a necessary precaution for the business. To minimize the effort expended on backing up data, the company automates the process by copying electronic versions of the files. The file backups are then instantly sent to an internet-based storage hold, and employees can access the data copies from their computers. A common goal of Six Sigma professionals working on improvement projects is to recognize value-added activities from required non-value-added or non-value-added activities. Non-value-added activities or processes are considered waste. Waste is also known by the Japanese term muda, which is defined as any activity that doesn't add value to a process or product, but it still adds cost. Basically, waste is anything that is not essential to the manufacture of a product or delivery of a service. Taiichi Ohno, the founder of the Toyota production system, identified 7 forms of waste that may be presented as overproduction, extra processing, motion, waiting, transportation, inventory, and defects. In Lean Six Sigma projects, identifying and removing waste can be a very useful tool at the improve stage in the DMAIC cycle. Overproduction is the creation of more products, services, or components than either the operator, the next stage in the production process, or the external customer needs. If too many items are produced by one step in a process, they will be left in storage until the next step in the process is ready to handle them. This goes against the lean principle of creating a just-in-time environment, where items arrive just as they are needed for the next step in the process. Stored work in process costs the company money, yet it doesn't benefit it in any way until the items are completed, and the customer pays for them. When the number of completed items exceeds the number required by the customer, they must be stored in such time as another order is placed, creating a demand. This could be any time, and items sitting in storage in this manner don't make money for an organization. They do tie up funds and halt cash flow, because the raw materials that were used for this production have already been paid for. This is a cash outlay, yet no cash has been received in return for the completed project. To avoid overproduction, managers need good metrics to evaluate the consumer market and process capability so that they can match production to demand. Extra processing is applying more processes than needed to create a product, service, or component. Typically, this includes using overly large or complex equipment or reworking in a process. This includes any additional steps in the manufacturing process. Process waste can also include all of the overly complex designs that add too much value to a product that customers aren't willing to pay for. Examples of process waste include extra setup procedures for machinery, inspection steps, handling during packaging or delivery, and documentation. Motion wastes involve people, information, or equipment that make unnecessary motion due to workspace layout, ergonomic issues, or searching for misplaced items. For example, let's consider the workspace, where workers must walk 50 feet to a central raw material storage area to get screws before they can begin manufacturing the sunglasses that the factory produces. This adds additional time to the process, which costs money. If the screws were within the arm's reach of the worker's workbench, each pair of sunglasses would be completed faster, and waste would be eliminated. Unnecessary motion also includes excessive bending, stretching, and reaching for tools or materials. It's an indication of a poorly designed workspace, which could be redesigned, eliminating the unnecessary motion waste. Equipment or employees may waste time waiting for another process to be completed before performing a task. Waiting is usually caused by unrealistic or badly planned scheduling and process delays. Delays include holdups due to delivery problems and downtime. Delays can also include process and design changes. Employees may have to wait for raw materials to be delivered before work could be started, and inspection to be carried out before working can continue, information to be relayed or reports to be compiled, or machines to complete a production cycle. Transportation is a movement of a product or its components. All transportation other than delivery of a product to the customer is considered waste. For example, consider a factory where items are manufactured in one area. Then they are moved with a conveyor belt to an inspection area, and then moved again using a forklift to a storage area, where they're left until they're ready for shipping. Moving the items to a different area for inspection is unnecessary, because inspection could be performed as items are coming off the production line. Moving completed goods to a storage area before packing and shipping is also unnecessary. The product could simply be moved directly from inspection at the production line to the packaging area. The additional movement adds cost to the products and increases production time, but it adds no value. Inventory is material that is not yet needed and must be stored. Unnecessary inventory means any items that must be stored, including raw materials, work in progress, and finished goods. Inventory may originate from suppliers, or it could be the result of overproduction. Inventory requires having unused space and storage that's currently not required. The cost of storage and handling associated with unnecessary inventory adds to the manufacturing cost of the end product, but adds no additional value to the product. Stored inventory may end up costing an organization even more if it becomes damaged while in storage. In such an event, the entire manufacturing cost of the damaged items is lost. The last type of waste is defects. Defects are flaws in a product or service. A defect causes the product, or a part of it, either to be scrapped, discarded, or reworked, and this represents waste. When an item is defective or rejected, the entire item may have to be scrapped, or the defective part may have to be sent for repair. If the item is scrapped, all of the resources invested in that item are wasted, with no gain to be had. The cost of the raw materials, labor, and transportation involved must be carried by the organization, with no way to recover them from customers. If the item is repaired, the cost of a new part, as well as the costs involved in a rework, are added to the cost of the completed items. Customers don't pay for these costs. They only pay for the value of the item as if it was produced correctly the first time. Neither of these actions, scrapping or rework, adds value to the end product, but they both add cost. An eighth waste has been added to represent the non-utilized or underutilized skills and talents of employees. With the addition of this eighth waste, there's an easy acronym or mnemonic to remember, which stands for downtime. Downtime represents defects, overproduction, waiting, non-utilized talent, transportation, inventory, motion, and extra processing. A value stream defines the flow of materials, service, and information that brings a product or service to customers from start to finish. This includes suppliers, production operations, the final customer, and all of the activities in between. In other words, it's the way the value is delivered from the source or starting point through to delivery to the customer. Any obstacles or waste, such as wasted time, unnecessary motion, or excess inventory, will disrupt the flow of value in a value stream. You need a clear picture of a full value stream before you can determine where waste is occurring, or before you can plan how the flow of value to the customer can be made more efficient. A useful tool for attaining this picture is a value stream map. Rather than focusing on an individual process, the value stream maps show the entire value stream of activities that go into producing value for the customer. Although it was originally used in manufacturing situations, value stream mapping is equally useful in service situations for identifying waste. Services have the same sort of value stream that provide a finished product to a customer. The value stream map provides the flow of information and the flow of the products on one sheet of paper. It starts with the focus of the customer and then works backward through the production processes and then to the suppliers. It also includes the information flow that's captured from the central planning system to the customers, as well as the suppliers and each individual step within the process. Value stream mapping and analysis involves the creation of two maps. The first map reflects the current state of the system, and the second map reflects the future state. Each value stream map is a graphic chart of the processes and activities that produce the product as it goes through its entire creation. Both maps illustrate the production flow and the information flow. The current state value stream map is a visual representation of the process as it currently is. This map provides a starting point or a baseline for identifying wastes and its causes. The future state map represents the targeted state of the processes, or the state once improvements have been implemented. The future state map also highlights areas in the process where important initiatives are required and what flows should be altered to create a leaner production and information flow. There are 4 steps in conducting a value stream analysis. The first is to define the product family. The second step is to create a current state map. Then a future state map is created. The fourth step is to plan implementation. To be meaningful, a value stream map should be created for a single related group of products. So in step 1, the product family is defined. Product families can be identified by the similar processing steps and equipment that the products pass through as they move downstream in the manufacturing or service system. It's important to clearly define and document all of the details of the product family in step 1. This includes what the related products are, the demand for the products, and the rate of sales. A convenient tool for determining which products are related is the product and equipment matrix. This type of matrix plots each product against the processes and equipment that pass through, so you can determine which products go through similar processes in your system. For the sample manufacturing process, the first and the fifth items receive very similar treatment in the production processes. They both go through clean, polish, press, and trim, so they probably belong in the same product family. A Pareto chart can also be used to choose the product family. Products with the highest production volume could be chosen for the value stream map. Process operators and line managers are the ideal people to help define the product family. Also, a cross-functional team can provide valuable insight into the product family selection. Value stream mapping involves 4 steps: defining the product family, creating a current state map, creating a future state map, and planning implementation. In this topic, we're going to focus on what's involved in creating a current state map. After deciding on the product family to map in step 1 of the process, the second step is to draw a current state map. Ideally, this begins with a walkthrough of the process by the improvement team to collect current state information. This means physically tracing the path of both the material flow and the information flow of the entire value stream. This can provide an important sense of its sequence and flow. The team should work backward through the value stream because this keeps the emphasis on what the customers value. Beginning at the final link to the customer and backtracking through the system allows the team to consider how each process step adds value or creates customer value. It can be very useful to have every team member draw an additional map of the current state, using the standard icons to convey key information. Afterward, you can integrate each of these maps into a single current state map. There are different kinds of data that can be collected for a value stream map. These typically include cycle time, net operating time, and work in process. Several others may also be collected, including lead time, which is the total amount of time it takes for one unit to complete the process, including value-added time and non-value-added time. Throughput time is the time it takes for a unit to be completed by the operation from start to finish. Changeover time is the time it takes to switch production from one type of product to another. Uptime is the actual machine time available to run, divided by the time scheduled to run. Work time is the available working time per period, minus any breaks for cleanup. For example, if a worker that has an 8-hour shift also has 1 hour for lunch and 2 15-minute breaks, the work time for the shift is 6.5 hours. Finally, queue time is the time that work has to wait before being acted upon. Although value stream mapping icons are not standardized, there are some accepted ways to portray the common elements and activities in a process. The first is inventory. It's represented with a triangular icon with the letter I in the center. When mapping the current state, the level of inventory can be approximated with a quick count, and that number can be placed beneath the symbol. Electronic flow is represented by the jagged arrow icon. This symbolizes the electronic flow or exchange of information across such platforms as the Internet, intranets, local area networks, and wide area networks. You could also include the frequency of exchange, type of media used, and the type of data shared. The manual information flow is represented by a straight arrow. This can include memos, schedules, conversations, reports, and also the frequency of the exchange. A process is represented by a rectangle with a horizontal line near the top. A process could be an operation, machine, or department through which the material flows. A source is represented by a rectangle icon with a jagged top. This symbolizes the usual starting and ending points of the material flow. The supplier is the usual starting point for the process flow, and the customer is the usual endpoint. Buffer stock is represented by a stack of 3 vertical boxes. This icon represents a safety net of stock, which is sometimes referred to as a supermarket. It's used to protect against such things as fluctuations and customer orders or system failures. The push arrow icon is a striped, straight, horizontal arrow. It represents the pushing of material from one process to the next, and means that something is being produced regardless of the immediate needs of the downstream process. Let's explore an example. The Six Sigma team at an auto parts manufacturer is conducting a value stream analysis of its front and rear bumper manufacturing process. After defining the product family at step 1, the team members are in the process of creating a current state map. They start with the source symbols. The supplier is placed on the left, which is the usual starting point for material flow. The customer is placed on the right, the usual endpoint for material flow. There are 5 main processes: fabrication, molding, machining, painting, and inspection, all represented by rectangular process boxes. These boxes contain details about the cycle time, changeover time, and uptime. For example, the fabrication process has a cycle time of 5 minutes, a changeover time of 45 minutes, and an uptime of 90%. The team then adds icons for inventory locations next to each process box. Small boxes are also used to add details about the inventory type and the quantity that are found at each inventory location. For example, the inventory icons on each side of the fabrication process tell you that the inventory delivery takes place between the supplier and the fabrication process. They also indicate that 4,400 items of inventory are passed from the fabrication process to the molding process. Additional icons representing movement of raw materials to the manufacturer and finished goods to the customer are added in the form of trucks. The information flow beginning at the production planning and control area, running down through the process, and through the production manager is represented by the manual information arrows between icons. The jagged arrows between processes, supplier sources, and customer sources indicate that the information flow between these entities is electronic. Putting the lead time ladder along the bottom of the map is a final step. To get the total production lead time, the team takes the inventory number and divides it by the daily customer requirements. In the ladder, the peaks represent the lead time between each process. In this case, 1 week, 4 weeks, 5 weeks, 2 weeks, 1 week, and 2 weeks. The troughs represent the value added time associated with each process: 5 minutes, 8 minutes, 12 minutes, 14 minutes, and 6 minutes. The team then adds the values for both of these, reaching a total lead time of 15 weeks and a value added time of 45 minutes. And there is the current value stream map. Value stream mapping involves 4 steps: defining the product family, creating a current state map, creating a future state map, and planning implementation. In this topic, we're going to focus on the last 2 steps: creating a future state map and planning implementation. The information used to create the current state map is combined with any insight gained from the physical evaluation of all activities. Along with the knowledge about lean improvement methodologies, these form the basis for imagining and designing an improved future state map for the system. To create a future state map, team members use various lean improvement tools such as pull, tack time, Kanban, setup reduction, and total productive maintenance. The future state map is where the team identifies creative solutions for all of the identified issues. The future state map shows specific changes that are required to the current state to achieve the envisioned future state of the value stream. The areas where Kaizen events would improve the process are noted, and potential areas for improvement are circled on the map. There are a few additional icons that are more commonly used in the future state map. The pull arrows are a major change from the current state map, where the flow is indicated by material flow arrows and push arrows. Kaizen bursts are represented by gold bursts. The signal Kanban is typically used to represent the withdrawal from a supermarket. The Kanban post is a location where the Kanban cards are kept, and the production Kanban is a signal to produce more. Let's say a Six Sigma team is mapping the future state of the value stream for an automobile manufacturing process. The results of the analysis of the value stream map showed several opportunities for improvement, such as combining processes to create a better flow and eliminating batching of inventory between processes. So let's examine some of the elements of the future state map and what they mean in relation to this example. 2 Kaizen bursts were targeted: a designed Kanban and a designed work cell Kanban. The work cell was created for the fabrication, molding, and machining operations. 2 bottleneck processes were also identified: machining and painting. A cycle time related to these processes is 8 weeks, and a goal is set to reduce this cycle time. In the future state map, the flow of products between suppliers, the manufacturing process, and the customers will be based on the pull of customer demand. An inventory supermarket was used at the material receiving, starting, and ending points to reduce the total inventory and limit overproduction. In addition, a pull method was used between the sub-processes for this purpose. A Kanban post, represented by the goalpost symbol, was identified between the painting and inspection sub-processes for the pickup of the in-process materials. Finally, signal Kanbans, represented by the inverted triangles, were used next to the inventory supermarkets to signal a trigger or a minimum point whenever the inventory levels in the supermarket between the 2 processes drop. The cycle time was estimated to reduce by 33%, and the lead time was estimated to reduce by 31%. The future state map is also expected to reduce the inventory substantially. More sophisticated forecasting, faster reporting, improved communication, and reduced inventory and monthly blanket orders cut the lead time and cycle time even further. The requirement for visual inspection was eliminated by using automated inspection, and the symbol was removed from the future state map. The fourth and final step in the value stream mapping process is the plan implementation. This includes developing a step-by-step plan. When developing the plan, you use the value stream map to highlight the goals and objectives for the team. The team should include those working with the relevant processes to ensure buy-in. The plan also highlights the types of interventions needed. For example, these might be just do-it fixes that could be implemented in a day, Kaizen blitzes that take 2 to 5 days, or even longer-term projects. You then present the plan to management, secure the necessary resources, and finally execute the improvement plan to reach the future state. Six Sigma and Design for Six Sigma, or DFSS, are both very powerful tools, but each has a slightly different focus. Six Sigma uses the Define, Measure, Analyze, Improve, and Control, or DMAIC methodology. It's typically used when you already have a process in place, but you're having issues with variation or defects, and you're trying to improve that process. Design for Six Sigma, however, is used more for the upfront planning. It's used before you have a process in place, and when you're trying to make improvements prior to starting the production process. Six Sigma only gets you so much in terms of improvement with existing processes. Therefore, you're only going to reap just so much in terms of process improvements. Studies have shown that using Six Sigma principles, you can typically get about a 4.5 Sigma process. After that point, you hit a brick wall. That's where you have to go back and redesign your product or your processes. This is where Design for Six Sigma comes into play. Design for Six Sigma is an approach that's used to design or redesign a product or service. Design for Six Sigma uses many of the principles of Six Sigma as well as a similar philosophy. But now we are using it to do all of the upfront design work when we're developing these products, processes, or services. By using Design for Six Sigma for the upfront work, we're being proactive, choosing to achieve a Six Sigma level from the very beginning. Another key aspect of Design for Six Sigma is that as we're designing these new processes, products, or services, or redesigning them, we're taking into account and ensuring we meet our customers' requirements and expectations. Studies have shown that approximately 2/3 of a product's costs come from the design of the product or service. If we go through and understand really what the customer wants, and we design it right the first time, using tools such as Design for Six Sigma, we can improve the benefits to our customers. The first benefit of Design for Six Sigma is that it helps to greatly reduce errors or defects, because we're planning the process with a Six Sigma philosophy in mind. Design for Six Sigma also helps to reduce production costs and increase customer satisfaction, because we're making sure we're meeting our customers' needs, and because we're taking those needs into account every step of the way while redesigning our product, processes, or services. Because of this, Design for Six Sigma helps us to generate the same types of benefits as the Six Sigma DMAIC methodology. Design for Six Sigma also helps support larger Six Sigma goals, because we're going to use Design for Six Sigma before we even start producing or designing our product. That's going to help us reach our long-term goals for Six Sigma. Design for Six Sigma also helps us to build to the Six Sigma quality levels. Again, because we're taking that mindset into account and designing our new products or services based on customers' expectations, we're able to reduce the variation. Traditionally, companies spend around 5% of their costs on design and 70% on production. However, by rolling out DFSS, companies can reduce the total production costs of the products or services they create. By beginning the process in a way that severely limits the potential for errors and defects, companies can save costs in the long term and increase their standing and reputation with customers. General Electric, or GE, a forerunner in successful Six Sigma deployment, began implementing a DFSS strategy for product and service development. This approach structured the company's design process, providing more predictable and low-defect results. As a result of implementing DFSS, GE increased its earnings by 19%, and its revenues for the same year grew by 16%. New products designed using DFSS generated 50% of the company's revenue. This approach helped GE increase sales and provided a range of long-term benefits to the company, ensuring higher quality innovations at lower costs. Design for Six Sigma is very useful in new product and service development because we're using it to redesign or develop a whole new product or service. There are two types of applications for Design for Six Sigma. The first is with the product or service. This is when your organization is developing a new type of product or service that you've never offered before. Typically, when you're doing this, you're building upon existing knowledge to build a product or service that you previously offered. A second type of Design for Six Sigma application is a process DFSS. This is where you're developing a new process, so you're not currently manufacturing or producing that product. This means it's a brand new process. You will design the process to account for variability and focus on reducing that variability. Design for Six Sigma and new product development are very closely related. However, Design for Six Sigma is not meant to replace new product development. It's really meant to enhance the new product development process. DFSS is very closely related to the new product development or NPD process. It helps in drastically improving the design product in terms of its customer value, quality, repeatability, and cost. Milton D. Rosenau, Jr. outlined 5 steps in the NPD process. The first step is a concept study. Before you proceed any further with a new product idea, you need to make sure that you determine if there are any unknowns about the market, technologies, and processes associated with your idea. The next step is the feasibility investigation. This is where you determine if the issues that you found in the concept study are resolvable, and what limitations might exist. The third step focuses on the development. This is where you establish the specifications and the needs of the customer. You determine your target markets, and use a cross-functional team to set up tollgate stages. The maintenance phase includes all of the post-delivery tasks that are associated with product delivery. The fifth and final stage is continuous learning. In this stage, project reports and evaluations are used to ensure that teams learn from both their successes and failures. Design for Six Sigma incorporates several additional tools. The first is the Failure Modes and Effects Analysis, or FMEA. An FMEA is a structured method for analyzing potential failures and their effects, and how these might influence design parameters. Quality Function Deployment, or QFD, helps provide an organization with a clear understanding of what the customer's needs actually are. It helps to translate the voice of the customer into the technical requirements, to generate the best possible products, services, and processes. Design of Experiments, or DOE, is a structured methodology that enables teams to design experiments and analyze the results of these experiments. The focus of Design of Experiments is to understand and control variation of the key process inputs, and to use that information to improve the results of the project outputs. Design for Six Sigma uses these experiments to validate and discover the relationships between the inputs and the outputs of a process. And Robust Design Optimization, also known as RDO, is a tool that helps to integrate experiments early in the development process. This really helps the team discover the optimal solutions to meet customer needs. These solutions are typically strong and very adaptable, so that the team can accommodate changing focuses and enduring problems. Before an organization decides to roll out Design for Six Sigma, there are 4 key considerations that really need to be addressed. The first one is that you need to understand your organization's current Sigma level, the trends within your organization, and your business environment. If your Sigma level is rising fairly steadily, then it might be unlikely that you really need to focus on new designs. However, if the rise in your Sigma levels is starting to slow significantly, you might have reached your capacity with your existing processes. Studies have shown that when you reach a level of about 4.5 Sigma, you've probably reached a point where you need to go back and start redesigning products and services and going after harder process improvements. It's also important to understand the level of change in the market demand, your customer requirements, and the technology within your organization. You need to be able to manage your organization's business environment. If you do have changes in market demand, customer requirements, or technologies, these might render your products or services obsolete in the near future. So if you have situations like this that are hindering your business's growth, Design for Six Sigma could help your organization adapt to these changes. You also need to look at your organization's prioritized project schedule. When you're going through process improvement projects, you need to plan accordingly and prioritize the list based on each project's complexity. Typically, it's easier to go after those simple projects, the low-hanging fruit projects, first. You can then prepare your organization so that they're ready to roll out Design for Six Sigma for the more complex projects. Finally, it's important to understand your organization's capacity to roll out Design for Six Sigma. For this, you need to consider how the organization is currently handling improvement projects. You need to understand the resources that you have available, and whether the teams and management can become more involved in the design. So now, let's examine some of the situations that are best suited for Design for Six Sigma. We start by having an issue that we want to address. With this, we can first determine if the product or service currently exists. If it doesn't currently exist, then we will want to go through and use Design for Six Sigma to design and develop that new product or service. However, if the product or service does currently exist, we will want to go through and use tools such as the DMAIC methodology from Six Sigma, Kaizen, or other improvement tools to improve the project initially and go after some of the low-hanging fruit. At that point, we would want to go through and determine if the improvements is sufficient enough to yield the desired quality or Sigma level. If the answer is no, that's when we need to consider using Design for Six Sigma. That will allow us to reach the next level of improvement gain. If we have reached the desired level of quality improvement, we can continue just using DMAIC and other improvement tools to further enhance the project. So let's examine a couple of examples to understand when to use Design for Six Sigma and when to use DMAIC. The first example is an automobile manufacturer that has seen defect rates from their drive shafts steadily dropping over the last 15 months, since they started implementing the DMAIC methodology. In this case, it makes more sense to continue moving forward with the DMAIC methodology, because they're heading in the right direction. DMAIC is working well for the organization, so there's really little reason to consider redesigning the product. The second example is a mobile phone manufacturer that's decided to launch video phones as a new line of products. Unfortunately, the company has been losing market share, and their defect rates are not dropping. In addition, their Sigma levels are not increasing. They've exhausted all of their possible efforts, including several DMAIC projects, trying to meet customer specifications, but their customer satisfaction is still very low. This situation calls for Design for Six Sigma, because it's a new process and all of their possible efforts previously have not helped enough. Let's consider two more examples. The first is a new soft drink company that's entering the market. The company wants to develop a tastier and more consistent cola than what's currently on the market. In this case, Design for Six Sigma is the most appropriate choice because the product and the business do not yet exist. Any additional cost and problems associated with redesigning, retooling, and reallocating resources are not limiting factors at this point because it's a new company. The second example is a bulletproof surveillance camera. The company started using the Six Sigma methodology 3 years ago and yielded great returns from these projects. The projects resulted in a quieter and more smoothly rotating device. They also increased pixel quality and created a more resilient armor coating to protect the devices. Recently, however, the projects have been yielding smaller and smaller gains, and the rate of improvement has started flattening out. In this case, Design for Six Sigma is also more appropriate, because the rate of improvement has slowed and almost come to a stop. Design for Six Sigma is useful when you or your company feel that the process and its outputs are still not at the desired level of quality, so you may need to go back and redesign the process or product from the ground up. Six Sigma and Design for Six Sigma have several key similarities. First, they're both quality improvement strategies, focused on achieving a performance standard of 3.4 defects per million opportunities. Because of this, both strategies really have a focus on quality and customer requirements. Design for Six Sigma and Six Sigma also both require the use of statistical and quality tools. They're very systemic processes that focus on the use of data, and they're both very data-intensive and systematic processes that seek to improve the highest quality levels at the lowest cost to the company. Both Design for Six Sigma and Six Sigma are implemented by teams, and the teams typically have different belt levels, including green belts, black belts, master black belts, and champions. The use of teams helps ensure that the approach is integrated quickly into the culture of the organization. Last but not least, Design for Six Sigma and Six Sigma both result in lower costs. These costs come from reducing cycle times, inspection requirements, and waste and rework. Now that we've talked about some of the key similarities between Design for Six Sigma and Six Sigma, let's go over some of the differences. Six Sigma focuses on improving existing products and services. It does this by looking for the root causes of the errors or defects to reduce the process variation in the current products or processes. Design for Six Sigma, however, starts at the design stage by trying to achieve an error-free product or service before you've even rolled out and started to deliver that product or service. Let's now examine the attributes of Six Sigma and Design for Six Sigma and how those relate to the goals, defects, and processes for each of these methodologies. With Six Sigma, the primary goal is to improve current processes. However, for Design for Six Sigma, we're trying to optimize new designs that don't currently exist. With Six Sigma, we're trying to remove defects. And with Design for Six Sigma, we're really trying to prevent those defects before they even occur. With Six Sigma, the processes are predefined. But with Design for Six Sigma, the processes are defined by the organization. Six Sigma also solves very specific existing problems using an exact methodology known as Define, Measure, Analyze, Improve, and Control, or DMAIC methodology. On the other hand, Design for Six Sigma identifies problem areas and design workarounds, and uses two different methodologies, IDOV and DMADV. IDOV stands for Identify, Design, Optimize, and Verify, while DMAVD stands for Define, Measure, Analyze, Design, and Verify. The focus of Six Sigma is on improvement projects, while the focus of Design for Six Sigma is on new process or product development. Six Sigma typically provides quicker returns because it's making improvements to an existing process. However, with Design for Six Sigma, the terms might be a little more long-term because we have to design the new product and go through the entire product development cycle. The nature of Six Sigma is very reactive, as you're improving upon current existing problems and approaches. Design for Six Sigma is very proactive in nature, as you're trying to fix problems and prevent them from happening before they even occur. So now let's examine a hospital scenario to further illustrate these key differences. Let's say we have a team in a hospital that's decided to initiate a Six Sigma project to help improve its current drug ordering process. The current process has frequent shortages and sometimes excessive inventory. Using the DMAIC methodology, the team has worked through the process to find flaws and correct them wherever possible. The Six Sigma project took 4 months, and the team expects an annual savings of $120,000 per year by removing the flaws and wastes within the process. So this is an example that shows that the goal of Six Sigma is to improve a current process in reaction to a perceived or real problem. Now, let's suppose the hospital wants to initiate a new surgical procedure for patients who suffer from head trauma. In this case, the hospital uses Design for Six Sigma and the IDOV methodology to create a new process and service. The deadline for the design of the new service is 8 months, and once the procedure is approved, the hospital would be one of only a few in the country to provide this service. So it's really a long-term realization of benefits. In this case, the process is more on ensuring that the surgical procedure is error-free, so it's very proactive as an approach. because the hospital is not responding to errors in the existing procedure. The hospital can't afford to make mistakes when people's lives are at risk. Design for Six Sigma is a more flexible approach in the Six Sigma methodology. Within Design for Six Sigma, there are three different methodologies. The first is IDOV, which stands for Identify, Design, Optimize, and Verify. The second is DMADV, which stands for Define, Measure, Analyze, Design, and Verify. And then finally there's DMADOV, which stands for Define, Measure, Analyze, Design, Optimize, and Verify. All of these methods have their foundations in new product development and encompass the same overall processes to identify, design, and verify, but they have slightly different processes, and these slight differences provide for flexibility in these methodologies. Let's examine the IDOV methodology. In the Identify phase, the customer requirements are incorporated into the formal product design. This is accomplished by setting up a cross-functional team, assigning responsibilities to the appropriate people, gathering of the voice of the customer, and then defining what the customer requirements are. Once you've identified these requirements, you should conduct a competitive analysis and determine the critical to quality attributes. Some of the tools typically associated with the Identify phase are the team charter, quality function deployment, failure modes and effects analysis, and benchmarking. The design stage of the IDOV process is where the concept and designs are developed. Once various designs are developed, their alternatives are evaluated so that you can select the fit concept that best meets the customer's requirements. Then, based on the concept design, the raw materials, process, or service scope is started, after which the team can start to develop the procurement and development plans. The two main tools associated with this phase are design of experiments and then various statistical tools. The focus of the Optimize phase is to establish the product specifications, service parameters, and process settings. In this step, the process capability information is also calculated so that the team can project performance of the current systems and then optimize the designs as much as possible. Using this data, the team can also start to incorporate error proofing into the manufacturing or service processes to reduce variation in costs. In this phase, statistical tools and capability analysis are commonly used. Finally, in the Verify phase, the team starts to focus on conducting tests and validating the design and quality control systems. It's important here to verify and validate that you're ready to move into full production. In this phase, product designs are typically developed to help validate the systems. So now, let's examine how the IDOV methodology actually works. In this example, a radio equipment company is developing a new MP3 player using Design for Six Sigma. In the Identify phase, the company organizes a cross-functional team and assigns design responsibilities to the appropriate team members. These responsibilities include market research and researching the technical implications of the customer requirements. The team uses this information in the design phase, along with customer requirements and technical considerations, to develop a set of product design drawings. The design alternatives are then evaluated and compared against each other on the basis of cost, efficiency, schedules, milestones, and available resources. Using that information, the team selects the best product design drawing that meets the customer's requirements. In the Optimize phase, the team takes that chosen product design drawing and finalizes product specifications. The specifications and product design drawings are given to manufacturing, who are responsible for machinery and equipment setup and calibration, as well as implementing any error proofing that's necessary into the production system. Once the production system is set up by manufacturing, the team conducts a series of tests, using prototypes as part of the Verify phase. If there are any defects occurring in the manufacturing processes, they're identified and corrected. It's important at this stage to fix any errors and validate the processes to ensure all of the corrections have been fully implemented. The Design for Six Sigma methodology of DMADV is also known as Define, Measure, Analyze, Design, and Verify. This methodology is very similar to the IDOV methodology, except that the DMA-DV process is divided into 5 steps. The first 3 steps of DMAVD, define, measure, and analyze, are roughly equivalent to the identify phase in the IDOV methodology. Let's consider each of the steps of the DMADV methodology in a little more detail. The define phase is very similar to the identify phase of IDOV. The process here is to establish a team and determine what customer requirements are and what internal metrics should be gathered to make sure that we're meeting those customer requirements. This is where the project charter is created and the goals are set. In the measure phase, the team assesses the current customer needs based on the information gathered in the previous stage. They then set the specifications for the product, service, or process, start to formulate multiple design concepts, and address the customer quality needs and any other production needs. In the analyze phase, the activities are analyzed in terms of how they add value. We want to make sure that the parameters and scope of the design are reviewed again, back to the customer requirements that were identified, to make sure that we're meeting the needs of the customer. In addition, this is a good place to perform benchmarking analysis and look for those potential best practices. In the design phase, the team starts to develop a design and make sure they're balancing quality, cost, and time. And then each design is tested against the required credible quality measures to make sure they meet customer requirements. If they don't, they're refined as necessary. And in the 5th and final phase, verify, the team start to test the prototypes against the customer requirements. Again, we want to make sure the product, service, or process that's being designed meets those identified customer requirements. Also in this stage, the team ensures the controls are in place for each of the processes involved. The IDOV and DMADV methodologies have several similarities. The first is that both methodologies involve cross-functional teams in the concurrent design and development of new products and services. Within these teams, you're involving manufacturing, quality, design, sales, and marketing to make sure you're getting a good understanding of what the customer really wants. The second key similarity is that both the IDOV and DMADV methodologies put a key focus on truly understanding the customer's needs and specifications prior to even starting the project. The initial steps in both methodologies are to gather the voice of the customer and really define what those customers' expectations are. Next, both methodologies rely on early detection and correction of errors. Both methodologies have a goal of reaching Six Sigma, so they both focus on designing the products and services right the first time in order to reduce variation and waste within the processes. And finally, both methodologies focus on closing the loop of improving the end product, service, or process during the design phase. Again, the key idea is to reduce the waste and variation within the process, to make sure everything addresses the customer requirements by closing the loop at each step of the process and taking into account what the customer requirements are in each step. In this topic, we're going to explore the differences between the DMAIC, IDOV, and DMADV methodologies. DMADV is a traditional Design for Six Sigma methodology, where IDOV is a modified methodology that was developed by General Electric. The IDOV methodology involves identify, design, optimize, and verify, where DMADV is define, measure, analyze, design, and verify. It's important to note that IDOV has optimization as one of the major steps that could really be beneficial for certain business processes. With that in mind, IDOV is typically more suitable for designing a completely new product, service, or process. DMADV is often applied to redesigning an existing product or process to make sure it meets the level of Six Sigma. DMADV and IDOV also differ in their implementation and with respect to systems engineering. IDOV is a more sophisticated method, so it's usually used for testing and validation for business process designs. The two methodologies also differ in their measure of success. IDOV considers cost efficiency evaluation as well as some other measures, not just the quality, but also from a financial perspective. The goal of IDOV is to produce the highest quality product while still meeting the financial goals of the organization. So let's compare the DMAIC methodology versus IDOV and DMADV. When we talk about Six Sigma, the focus is on improving current products or processes. However, with IDOV and DMADV, we're trying to redesign a current process or product or create new products or processes. In terms of process capability with Six Sigma, the current processes are viewed as capable of satisfying the customer's needs. Therefore, what we're trying to do is improve the current process using statistical tools. However, IDOV or DMADV will be applied where the current process is not capable of meeting quality needs and customer requirements. So we need to redesign the current processes or products to make sure they're capable of meeting customer requirements. Within the design stage of Six Sigma, we're assuming the current design is satisfactory and capable of meeting the customer's needs. So we actually don't have to go back and change the design itself. However, with IDOV and DMADV, we need to redesign the product or process based on various drivers, such as cost, producibility, or quality. In terms of flexibility, the Six Sigma methodology assumes that the current processes are flexible enough to meet customer requirements. So we just need some improvements within our current process. However, with IDOV or DMADV, we're considering a major change to our current process. And with that, we're going to take into account changes in potential customer demands and new needs. Finally, Six Sigma and the IDOV and DMADV methodologies require verification. However, with the Six Sigma methodology, you're verifying that the process changes are sustained and that they meet customer requirements. With the IDOV and DMADV methodologies, you're doing more of an advanced verification because you need to make sure your processes are designed to meet customer expectations. Failure Modes and Effects Analysis, or FMEA, is a very systemic and proactive approach to identifying and reducing risk within your products and processes. It's used both in Six Sigma and designed for Six Sigma to identify and really understand the potential problems or failure modes that could occur in your processes, products, or services. It also helps you understand what could go wrong in your process and identify the causes and their effects on your organization and, most importantly, on your customers. Once you've identified the causes and effects as a team, you can evaluate the risks that are associated with those failure modes and their causes and effects, and then prioritize them based on their overall impact. Another key aspect of FMEA is that it helps you identify the appropriate corrective action so that you can address the most serious problems in terms of their impact on your customer or organization and prevent them from happening again, using tools such as Poka-Yoke or mistake proofing. FMEA is a very useful tool during the beginning of a project because it helps you understand the scope and feasibility of that opportunity within your product or processes and the types of failures that could go wrong. This helps your team narrow the focus down to that specific type of problem that you're trying to improve. Failure Modes and Effects Analysis is used in both Design for Six Sigma and Six Sigma to identify potential risks and then take the necessary corrective action. FMEA, however, is used slightly differently in each methodology. Design for Six Sigma uses FMEA to evaluate new processes or products before you move forward with the product development process. It's used to understand why products or services might fail, so that you can understand the potential risk with a new product or process. This helps you understand the effects that the failures have on your customers, on your own organization, and to prioritize those to take corrective actions. FMEA is used in Six Sigma in the Analyze phase to help analyze potential defects, and in the Improve phase to fix issues before they occur in a process, product, or service. With Design for Six Sigma, the FMEA is more of a proactive approach. However, with Six Sigma, since the process already exists and we're trying to improve it, it's more of a reactive approach. FMEAs have numerous benefits. The first is that an FMEA can help your team rank the effects of failures by identifying what the most important failures are, and then the required actions for those failures to help improve the product and process. FMEAs can also help in identifying and ranking the customer's requirements that are introducing errors. These requirements can be analyzed for appropriate trade-offs to make sure that the improvements make sense while still meeting the customer requirements. An FMEA also documents the product and process knowledge that's gained through implementation. This documentation includes information such as the potential risk, which helps with future products and processes, and also with design and testing to make sure that the failures are eliminated or caught. Then there's a focus on prevention. Rather than being a reactive tool, FMEA is a very proactive tool when designing new products and processes. The goal is to make sure that the Six Sigma teams take action before errors happen. FMEAs also help to reduce development costs by identifying the potential failure modes early in the product development process. Those failure modes are what lead to extra costs from scrap, rework, late changes, and repairs. They also help improve the quality and reliability of the product or process by removing or reducing the effects caused by these potential failure modes from the process of the product. It also helps to ensure customer safety by preventing safety defects and failures. And finally, FMEAs are developed by a cross-functional team, which really helps to facilitate teamwork and communication between different departments and levels within the organization. There are 4 types of failure modes and effects analysis, or FMEA: design, process, system, and service. The 2 most commonly used FMEAs are design and process. The design FMEA is used when designing or redesigning a new product, while the process FMEA is developed for the manufacture or delivery of a product or service. A design FMEA is a very proactive approach to identifying potential design weaknesses prior to launching a new product. Design FMEAs are used to analyze component design because they take a systems approach to looking at the integration of all of the components and assemblies and how they fit into the entire design of the product or service. With that, design FMEAs focus on identifying potential component failures, which can have a significant impact on the entire system and potentially lead to system failure. It's important to apply design FMEAs once you've identified the potential design and before you release any design drawings. Process FMEAs are used to identify weaknesses or potential errors and risks within your production processes. They're usually conducted during the production process. Cross-functional teams walk through each step of the production process to understand what happens if something goes wrong in each step, and what that impact is on the next step of the process, which would be one customer, and also the final customer who's actually using your product. It's very useful in manufacturing, for example, because you can see what the impact is. System FMEAs are useful in analyzing system functionality in the early stages of design. You want to incorporate systems FMEAs before a specific hardware is determined. They help identify potential failure modes that are associated with the functionality of the system and may be caused by the system design. System FMEAs are particularly critical to use when you have very complex systems because they take into account the components and your subsystems and subassemblies. How a change in one subassembly may impact the entire system and functionality. Service FMEAs are used to analyze services and to identify potential failure modes that are caused by the system or process problems. They should be performed before the first service reaches the customer, so that you can identify any potential errors that might have a negative impact on your relationship with your customer. Service FMEAs are typically conducted on non-manufacturing aspects of the business, areas such as financial or legal services, education, healthcare, or hospitality. Developing an FMEA involves 10 steps. Let's start by talking about the first 3 steps. The first step of the FMEA is to review the process and design of the service that you're trying to improve. and identify all of the potential failure modes. This is typically done by walking through a process or identifying each design aspect. For example, if we consider a fire extinguisher, it could have problems with locking pins, discharge hoses, or pressure gauges. These are all potential failure modes that could impact the success or failure of the process. If we think about a service aspect, this could be data entry or incorrect coding that could lead to errors. The second step of the process is to identify the potential effect each failure mode could have on the customer. This is the information that's going to be used later in the process to assign ratings. If we think back to the fire extinguisher, a failure with a pressure gauge could cause an explosion when the customer uses the extinguisher, or a discharge hose failure could cause the extinguisher to spray erratically. If we think about the service side, using the incorrect coding example, this might make this software susceptible to bugs. This leads us to the third step of the process, which is to assign a severity rating to each effect. The severity rating is based on the relative scale that starts from 1 to 10, and it's assigned based on the knowledge and expertise of the team members. The highest rating, 10, means that the failure has a dangerously high severity in terms of the impact on the customer, where a rating of 1 means the severity is extremely low, and the customer may not even notice the impact. If we think back to the pressure gauge failure, the team could assign a severity rating of 10, because it could lead to serious injury or death. On the service side, if we go back to the coding error, this could lead to a software bug, which could be a 9 on a severity scale because of the impact on the customer. Now let's examine the next 4 steps in the FMEA process. The fourth step is to identify potential causes for each of the failure modes that you previously listed. For example, if we go back to the locking pin in the fire extinguisher, a failure could result from a malfunctioning of machinery. On the service side, the coding error could creep in due to a limitation of the software, or the inbuilt debugger. The next step in the process is to score the cause probability by assigning each failure mode an occurrence rating. This is where the team estimates how likely or how frequently failures could occur in the product or process. The ratings are again based on a 10-point scale. The best way to determine scores is based on actual failure data from past products if you have it, or if you don't have that information, using previous experience from a similar product. If we think again about the pressure gauge issue on the fire extinguisher, the team could determine the occurrence rating as a 4. The next step in the process is to determine the existing process controls for each of the failure modes that were identified. The controls, tests, and procedures should be identified to understand whether or not they've reduced the likelihood of a defective product reaching the customer. For example, if we go back to the fire extinguisher, the pressure gauge is checked by a quality assurance team before the product is shipped to wholesalers. And if we return to the coding error, both the inbuilt debugger and a separate debugging in the test process offer controls to the system. The seventh step is to determine the probability that each control will be able to detect and prevent the failure mode or its cause. Again, here we use a 10-point rating scale to assign a detection rating, where 10 means it's extremely unlikely that we're going to be able to detect the potential failure mode, and a 1 means we're very likely to detect it. The team determines that the detection rating for the pressure gauge is a 3, which means that the problem is quite likely to be detected. As for the coding error, the team assigns a rating of 4. The eighth step in developing a failure modes and effects analysis is to calculate the risk priority number, or RPN, which is done by multiplying the severity rating by the occurrence rating and by the detection rating. This is calculated for each item. Since each of these 3 items is rated on a scale from 1 to 10, the lowest possible RPN is a value of 1, and the highest RPN value is 1000. If we go back to the pressure gauge example, the team calculates the RPN value as 120, because they multiplied the severity rating of 10 by the detection rating of 3 and the occurrence rating of 4. Once all the RPN values are calculated, the team can prioritize them to identify what recommended actions should be taken. This helps to eliminate or reduce any high-risk failure modes in order to reduce the risk to your customers in your own organization. Once the recommended actions have been implemented, the final step is to calculate the new RPN values. So, once changes are made to the process or product, you need to go back and update the severity, occurrence, or detection ratings as appropriate, and then recalculate the new RPN value. The team can continue to monitor and maintain the results and use the FMEA as a continuous improvement tool based on the highest RPN numbers. The Failure Modes and Effects Analysis worksheet captures all of the potential risk and failures. The header of the FMEA captures information about the product and process under consideration. This is helpful with document control, as it provides information on when the FMEA was prepared, who prepared it, and when revisions occurred. The main part of the FMEA form captures all of the information about each step and features of the process, as well as the potential failure modes. In this case, the step is the receiver, and the failure mode is a dropped signal. The effect of a dropped signal could be a loss of service. This helps the team provide a very systematic approach to identifying failure modes and their causes, and understanding how the process is being controlled, and what the potential risks are. It helps the team identify and prioritize those risks so that you can take the appropriate action. The Risk Priority Number, or RPN, is a very useful aspect of FMEA because it helps your process improvement teams prioritize potential effects and focus on the improvement efforts. There are three main components to the Risk Priority Number: severity, occurrence, and detection. Severity ranks the seriousness of the effect of a potential failure. Occurrence ranks the probability that a particular failure will actually happen, while detection ranks the likelihood that a failure will be detected before it reaches the customer. Each of these is typically on a scale of 1 to 10, although some companies have modified these to put them on a scale of 1 to 5. A lower number in each of these categories means a lower risk. The higher the value, the higher the risk, or higher the chance. In order to calculate your risk priority number for each failure mode, you need to be able to rate the components that go into the RPN. Each of these components uses the rating scale to help prioritize the failure modes. The rating scale should be focused on three things: a range of ratings, again, typically from 1 to 10, a description of what each of those ratings means, and the criteria for each rating. There are some generally accepted scales. However, most organizations use their past experience and judgment to develop their own rating scales for their products and services. The key here is to make sure that the ratings are clearly defined and understood to allow for an objective prioritization. The severity in an FMEA is an indicator of the seriousness of the problem. Let's discuss the generic severity rating scale. If we use a rating scale of 1 to 10, a rating of 1 to 2 would have very low or little effect on the actual customer. When we talk about the criteria or definition, the failure would probably not be noticeable to the customer and would not significantly impact the product or the process. When we look at the mid-range in the rating system at a 5 or 6, this has a moderate or significant impact on the customer. The failure would result in the partial malfunction of the product, so the customer would not get all of the intended value from the product. When we reach a scale of 9 or 10, this risk has a very high or catastrophic impact on the customer. This could be a potential safety issue or result in an injury or death. So let's consider the example of a greenbelt that's working in an assembly department of a toy manufacturer. The assignment is to improve the painting process. The severity of the failure could have a slight effect on performance. If the customer is rather discerning, the non-vital faults could actually be noticeable. This would result in the customer being slightly annoyed, so the team might give this a severity ranking of 6. Occurrence ratings are an indicator of the frequency of potential failures. So let's examine a generic occurrence rating scale. And again, let's consider a scale from 1 to 10. If we have lower ratings, such as a 3 or 4, that means that the chance of occurrence is low or relatively few failures would occur. If we consider our potential failure rate, that means that we would have one occurrence every 1 to 3 years. However, if we have a higher rating, such as a 7 or an 8, this means that the chance of failures is high, and there are repeated failures. This could mean that we would have one occurrence per week. If we look back at our toy painting example, the probability of occurrence is fairly low. They have occasional failures, so about 1 every 3 years. Therefore, the occurrence rating would be a 3. The final component of the risk priority number is a detection rating. It is an indicator of how likely you are to detect an error before it reaches the customer. Now, it's important to understand when determining the detection rating that our customer might be the next step in the process, or the final customer that's actually using the product. Let's use a generic scale, again using ratings from 1 to 10. If we have a low rating of 1 or 2, that means it's almost certain that we're going to catch the defect before it reaches the customer. In other words, it means that the defect is completely obvious, and it will get caught. However, if we look at a rating of 7 or 8, that means our chances for detecting the defect before it reaches the customer are pretty low. For example, the product could be manually inspected during a process. Now, if we go back to our example of the toy manufacturer, the failure mode of the scratches and the paint had a very effective process control in place. Therefore, the probability of detection or prevention was pretty good, and the team determined the detection rating should be set at 4. In this topic, we're going to explore how to calculate and use RPN. Once you've determined your ratings for severity, occurrence, and detection, you could then calculate the risk priority number. This is calculated by multiplying the severity by the occurrence and then the detection. Let's take a look at an example. If we have a severity of 7 and an occurrence of 3 and a detection of 9, our RPN would be 7 times 3 times 9, and therefore our RPN is 189. So what does this tell us about our process? What does the value of 189 mean? Well, at this point, really nothing, because we have to know enough about the other steps within our process to see what the other RPN values are. The RPN ratings are relative to each other, and they're really only meaningful once you compare them against other RPN values in your failure modes and effects analysis. The RPN really provides its value by helping the team prioritize where they need to take corrective actions. Once you've performed those corrective actions, you need to go back and recalculate your risk priority number. So let's examine an airline baggage handling process where the team has identified 2 specific problems. The team is not sure which problem they should address first. In the first problem, the automated system that codes the baggage with its destination doesn't always record the proper codes. With the second problem, the tags attached to the baggage and used for identifying the destination aren't always secured, and they get lost. When we consider the first problem, we start by calculating the risk priority number using a scale of 1 to 10. The team determines that the coding problem has a severity of 10 because it's imperative that the luggage arrive at the proper destination for the customer. The team finds that 2 out of every 100 pieces of luggage are coded incorrectly. Therefore, they assign an occurrence rating of 3, because it's not very likely to occur, and in almost every case, the problem is detected before the customer's luggage is actually lost. Therefore, the team assigns the coding problem a detection of 3. Then we move on to the second problem, with the baggage tags being lost. The team assigns the severity rating of 10, because without the tags, the baggage handlers have no way of knowing where the luggage is going. The team decides that the occurrence rating should be a value of 6 because the baggage tags fall off and are lost fairly frequently. The team then determines that the detection rating should be a value of 3 because most of the time, the baggage handlers realize that the piece of luggage is missing its tag, and it's tagged before it's actually loaded. Then we calculate the risk priority number for problem 1. We multiply 10 times 3 times 3, and we get an RPN value of 90. For the second problem, we multiply 10 times 6 times 3, for an RPN value of 180. When the team determines priority, they decide to focus on problem 2, because the RPN is much higher. Generally speaking, the higher the RPN number, the higher the risk. But there are a few caveats when we talk about RPN values. First, you should only compare the ratings from the same analysis to make sure you're really getting a comparative analysis. Second, if you have 2 or more problems that have the same or similar RPN values, you should prioritize and focus on the one with the highest severity number. This problem has the biggest potential impact on your customer, and it also becomes the highest risk in terms of what could go wrong and what your customer sees. Third, you need to take into account organizational priorities. This will help you to determine your risk priorities. For example, if your organization is very risk-adverse, you might have a general rule that any RPN over a certain value must have a corrective action, actively being worked on to reduce that RPN value. Once you've completed your corrective action, you can use the original and revised RPN values to calculate the percentage reduction. This will help your team evaluate the effectiveness of the corrective action. The percentage reduction is determined by subtracting the revised RPN, which is noted as RPN sub-R, from the initial RPN value, which is noted as RPN sub-I, and dividing the result by the initial RPN value. If we return to our baggage handling example, let's assume that our suggested actions resulted in a revised RPN value of 60 as opposed to the initial value of 180. When we calculate our percentage reduction, we start by subtracting 60 from the 180, and then dividing that by 180. This results in a reduction of 67%. This means that the airline was able to reduce the risk associated with the tagging process by 67%. By implementing the recommended corrective actions. Failure modes and effects analysis are used to identify risk within your products and processes, and then prioritize those potential risks to make sure that you are meeting your customers' needs. There are several similarities and differences when we talk about a design FMEA and a process FMEA. Design FMEAs are useful in uncovering problems with a product or a service design. This is typically done before production begins, so you're being proactive by identifying and reducing risk before you move from design to production. Process FMEAs are useful in finding problems in currently operating products and operational processes. Process FMEAs are typically done before production starts, when you're setting up a production process. In addition, they're done during normal operations of your process as a continuous improvement effort. Both process and design FMEAs use severity, occurrence, and detection ratings and explore why a product might fail, or might not meet the customer's requirements or expectations. Both of these are an effort to continuously improve the products and services for your customers. Both design FMEAs and process FMEAs are methods to identify problems, good results, safety hazards, product malfunctions, or shortened product lives. So let's examine some examples of design FMEAs and process FMEAs to highlight some of the differences and the focuses of each. Design FMEAs could be used on things such as an airbag in a car that might not be working properly, or a flawed temperature control mechanism. Process FMEAs could be used in a chemical manufacturing process, or to investigate potential causes of an inadequate mixing time. There are a few other differences between design FMEAs and process FMEAs. First, with the design FMEA, you assume that the process is going to operate as intended, meaning the focus is on the product design itself. Alternatively, the process FMEA assumes that the product design meets the intent, so the focus is on the process and doesn't take the design aspects into account. Finally, while the design FMEA considers the technical and physical limits of the production process, it doesn't use the process characteristics to overcome the design weakness. The focus is really on improving the design itself. While the focus of the design FMEA is on the design, and the focus of the process FMEA is on the process, it's important to understand that when you perform either type of FMEA, you may want to include some overlapping elements. For example, if your team is performing a design FMEA, it doesn't need to include process-related failure modes causes if your effect is covered by the process FMEA. As a team, you need to decide what's appropriate. You might decide to consider some of the process elements in the design FMEA. Likewise, when a team starts working on a process FMEA, they don't necessarily need to include failure modes and causes and mechanisms from the design. However, the team might choose to include some of the design FMEA elements. One of the reasons for this is that when you start creating your process FMEA, It typically originates from your process flowchart. And because of this, it might include some potential effects from the design FMEA when it's appropriate. Whether you're conducting a design FMEA or a process FMEA, your team should use a worksheet to capture this information. In this topic, we're going to explore the elements or components that make up an FMEA worksheet and how you compile each section for both DFMEA and PFMEA worksheets. When you start conducting a design FMEA, the first column includes the features or functions of the product or service. When you're conducting a process FMEA, each of the process steps are listed in the first column. The failure mode identifies how the product might fail under specified operating conditions. Then the effect is what your customer experiences, is based on the failure mode. The next column is a cause, the potential cause of the failure, which is what the eventual improvement solution should focus on. It's important to note here that you need to make sure that you don't confuse failure modes with causes. There are separate columns that are used to record these. A failure mode is any way in which the design or process may fail to meet its intended function or requirements. The final columns of the FMEA worksheet include the controls, ratings, RPN, and response columns. The control column is where we identify existing measures that are in place to detect our failure modes. When we are performing a design FMEA, these are the design activities and tests that are used to prevent or detect failure modes. Within the process FMEA, these are tools such as statistical process control and other methods to prevent or detect failure modes. In the ratings column, you record the team's assessment of the severity, occurrence, and detection of each failure mode. The RPN value represents the product of the severity, occurrence, and detection rating for each failure mode. Finally, in the responses column, you record the action that you will take, or have taken, to improve the design or the process. In a design FMEA, these are the actions that are taken to improve the design, which may include actions to detect, reduce, or lower the severity of a failure mode. In a process FMEA, these are the actions that focus on preventing the failure mode from occurring. However, when we talk about reducing the severity of our process failure mode, that might require design improvements, or process revisions, or both. Now let's examine an example of a design FMEA that was performed for a satellite receiver. Before starting a design FMEA, it's important to understand what the customer's requirements are and what the engineer's design intent was. This helps to outline what is and isn't expected from the design itself. When we review the top portion of the worksheet, it gives us information on the item itself. Who is responsible? Who prepared the FMEA? Who is involved in the team? And the revision date. For the design FMEA, we want to understand and analyze how the receiver functions, so that we can identify any design weaknesses that could be improved. Next, we move on to the failure mode. The failure mode helps to identify what could go wrong. The first potential failure mode that was identified by the team is a drop signal. The second failure mode is weak signal reception. We next move on to the effect. The effect of a drop signal is a loss of service, and the effect of a weak signal is diminished quality of service. Continuing on with the design FMEA, we can now add causes, controls, and ratings to the FMEA worksheet. When we consider the failure mode of drop signal, transmitter failure is determined to be one of the potential causes. Atmospheric interference is determined to be one of the causes for the weak signal reception. Since atmospheric interference can't be controlled, none is entered as a control. When the team looks at transmitter failure, they determine that a random inspection is being performed. Using this information, the team can next determine the severity, occurrence, and detection ratings for each of these failure modes. So now, let's calculate the risk priority numbers and the responses. The RPN value for the drop signal is calculated by multiplying 8 times 3 times 5, which gives us a value of 120. For a weak signal reception, the team multiply 8 times 7 times 10 and gets a value of 560. Based on these RPN values, the team determines that they should take action on both. The highest priority should be the weak signal reception, because the risk priority number is significantly higher than the RPN value for the drop signal. The team determines that they should improve resistance for the weak signal reception to help improve the risk priority number. They also decide they should increase inspection for the drop signal. Now let's examine an example of a process FMEA. There's another team that's working on improving their travel booking services. The team decides to use a process FMEA to understand how to better improve their service. They've started with analyzing step 3 of the booking process, which involves making a reservation. They start by identifying 2 potential failure modes. These include the reservation not being recorded and the reservation being made for the wrong room type. As they go through this, the effects are that the customer has no room and that the customer does not have the right room. They also have identified the potential causes as a lost network connection and a poor selection interface. Now with the process controls in place, they perform a random quality assurance check. In the case of the wrong type of reservation that's made, there's no control in place. The team goes through and determines the appropriate ratings for the severity, occurrence, and detection for each of these failure modes. The team calculates the risk priority number to be 168 for the reservation not being recorded and 192 for the reservation being made for the wrong room type. Since there's no significant difference between these 2 RPN values, the team looks at the ratings and determines that they should prioritize and focus on their reservation not being recorded because the severity is higher, and this issue has a bigger impact on the customer. Now that the team has determined their priority for improving the reservation process, they start developing corrective actions. In terms of their reservation not being recorded, one of the issues was just using a random quality assurance check. In order to improve the process, the team decided to change the process to include a verification activity. This will help with detection and further reduce the RPN value. Then, in terms of making a reservation for the wrong room type, the cause was determined to be a poor selection interface. Therefore, the team decided that they should change the selection button to a radio button to prevent this from happening. This would help reduce the RPN value for this failure mode as well. In this topic, we're going to explore some of the common approaches that organizations use to solve problems that relate to quality, cost, and customer dissatisfaction caused by issues within an organization, such as poor processes, products, and services. The Plan, Do, Check, Act cycle is an iterative process that is the underlying basis for most continuous improvement methodologies. It starts with the plan phase, in which the team starts to understand the objectives of the process and the customer's expectations or targets. In the Do phase, the team starts to execute the process and collect data, which helps lead to some of the analysis. The Check phase is where you study the actual results and then compare these results against those expected targets. And in the Act phase, your focus is on implementing corrective actions. The goal is to make sure you're closing the gap between what's expected and what you're actually achieving. You can use the PDCA cycle for any of your Six Sigma processes to understand how you're meeting the goals and objectives of your Six Sigma projects. Quality circles were developed in the 1960s in Japan. They're defined as a volunteer group of employees or workers. Quality circles are teams of typically 6 to 8 people that meet regularly to focus on identifying problems, gathering and analyzing data, and then generating solutions. It's a way for a team of people to work together to improve quality. This leads into continuous quality improvement, an approach to quality management that builds upon the traditional quality improvement methodologies. It emphasizes the need to structure quality improvement as a systems approach, and focuses more on the process itself, bringing in Deming's philosophy that there are no bad people, it's just bad processes. If you want to improve processes, you need to improve the systems within your organization. Additional problem-solving methodologies include ISO 9000, TQM, and business process reengineering. ISO 9000 was developed by the International Organization for Standardization, or ISO. It's a quality management system that helps an organization define, establish, and maintain quality assurance within a manufacturing or service industry. Total Quality Management, or TQM, is a system that was developed in the late 1980s and early 1990s to establish organization-wide continuous improvement efforts focused on delivering high-quality products and services. TQM helps to change the culture of the organization to make it a permanent change. Business process reengineering is a business management strategy. It was started in the early 1990s and focuses on analyzing the design of workflows and business processes within your organization, thus helping you rethink how the work is done so you can meet your customers' needs. Lean is a methodology that's derived from the Toyota Production System. It focuses on reducing the waste within your system. What you're trying to do with Lean is reduce the overall lead time within your process and eliminate activities that are non-value adding. This helps you to deliver only what your customer deems as value, which in turn helps you reduce the costs associated with delivering that product or service. Some of the common Lean tools used are value stream mapping, 5S, standard work, and visual management. And finally, Six Sigma was developed in the mid-1980s at Motorola. It focuses on identifying root causes and reducing variation within your processes. By reducing variation, you're able to provide a more consistent product or service to your customer. Six Sigma is based on the Define, Measure, Analyze, Improve, and Control, or DMAIC methodology. Once your organization decides that you're going to use Lean Six Sigma as your problem-solving approach, you need to perform a comprehensive assessment, including a readiness assessment to understand if your organization is really ready to implement Lean Six Sigma. The readiness assessment includes 3 main steps. The first step involves assessing your organization's outlook and future path. This is where you need to understand your current critical business processes, and if you need changes to help improve those critical business processes. To do that, you should look at your bottom line and your cultural and competitive needs. You need to understand how well you're meeting your customers' expectations compared to your competitor. Is the culture of your organization ready? And financially, do you really need to make the change at this point in time and put the time and investment necessary into it? You also need to understand if your organization has a clear strategic course. When you start down the Lean Six Sigma path, you need to make sure that you select projects based on where you need to go as an organization. Understanding what that direction is, and then how likely you are to meet your financial and growth goals, is critical. You also need to understand how your organization responds to changing circumstances. Are you able to respond efficiently and effectively? This will help you understand if your organization is ready to implement Lean Six Sigma. The second step in the readiness assessment is to evaluate your current performance. This is where you want to understand and get a baseline of where your organization currently stands. Some of the key questions you ask during this step of the readiness assessment provide you with information on the current results for your output, your defects, your yield, and your variation. Once you have this information, you can address a second question, which is how well are you currently meeting customer requirements? What is the gap between your customers' expectations and your current baseline performance? Then you need to look at your production processes to determine how efficient they are in terms of rework, waste, and cost per unit. The final step of the readiness assessment is to look at your systems and determine what type of capacity for change or improvement you have within your organization. At this point, you need to understand your organization's outlook and its future path. And then you need to have an understanding of what your current baseline performance is. Using that information, you can then understand how well your system is going to handle the change and how effective your current improvement approaches are to helping you reach the change needed within your organization. You also need to look at the change management structures within your organization. A few questions you may ask are, how well does your organization manage cross-functional processes? Is there a lot of interaction between divisions? Are you operating more as a silo-type organization? Also, if you implement Lean Six Sigma, how is it going to impact your other initiatives or activities within the organization? Are they going to work together and support each other? Or are you going to have a conflict between implementing Lean Six Sigma and your current systems? Once you've completed your readiness assessment, you need to go back and interpret the results. In the first step, you're trying to understand if Lean Six Sigma is critical to your business needs, your bottom line, and your cultural and competitive needs. A key aspect of this is having a clear strategic course for your organization. If this is not in place, it's going to be very difficult for your organization to buy into a Lean Six Sigma approach, because there's no burning platform or need right now that's clearly linked to your strategic organizational goals. Therefore, it's going to be very difficult to get momentum behind implementing an initiative such as Lean Six Sigma. In the second assessment, you're evaluating the current performance of your organization. You're also trying to understand your customers' requirements. If you already have strong processes in place that are helping to meet your current performance, and you don't have a big gap to fill between your current performance and your customers' expectations, it's going to be difficult to implement Lean Six Sigma. It might actually be detrimental to some of the current systems that you have in place. So you may be better off staying on course with your current initiatives. In the third step of the assessment, you want to look at your capacity for change. It's important here to see if your potential gains are really going to justify an investment as big as Lean Six Sigma. If you already have systems in place that are reaching your current needs, and if you don't have the right resources and culture in place, it might be very difficult. It also might be very overwhelming to employees and resources to implement an additional process improvement methodology, particularly if you're already meeting your customers' goals. The first step in any Six Sigma initiative is to select a project. It's an important aspect of deploying Lean Six Sigma because it helps dictate how well the Six Sigma methodology will be used. If you're introducing Lean Six Sigma within your organization, it's important to select the most appropriate projects. Training projects are the initial projects that people implement during their Lean Six Sigma training. So if you want to make sure that the projects are aggressive enough, but also realistic so that people are successful, you want to ensure that the participants get the benefit of understanding Lean Six Sigma, and then their momentum will spread the power and the benefit of Lean Six Sigma throughout your organization. There are 4 key steps in selecting projects for your Lean Six Sigma initiatives. The first starts with shortlisting your project or opportunities. This is where you really need to understand your current business performance and how that relates to what your customers' expectations are. You can then develop the improvement opportunities based on your current performance and how you're meeting those customers' expectations. The next step is to determine the selection criteria. While there are general guidelines, you might want to modify them slightly for your organization. It's important to select a criteria that specifically relates to your organization and what you're going to get out of these projects to help your organization with its Lean Six Sigma projects. Once you determine the selection criteria, you prioritize your product opportunities, and then select the best or most appropriate project opportunities for your organization, where it is you want to spend time, money, and effort on implementing Lean Six Sigma initiatives. One way to prioritize your Lean Six Sigma projects is to use a priority matrix. To use a priority matrix, the first task would be to have criteria developed based on your organization's needs. Example criteria for selecting your projects could include your sponsorship and level of support from management, their projected benefits, resources required, the scope of the project, the clarity of the deliverables, time to complete, team membership requirements, and the value of the application. Once you have the criteria developed, you weigh the importance for each criterion. It's important to note that the weight should add up to a value of 1, because each weight value is essentially a percentage given to the importance of each of the criteria. Then management will look at each of the criteria and score each project opportunity based on those criteria. A scale of 0 to 10 is typically used to rate each project opportunity. Their weighted score is then calculated for each project opportunity by taking the score for each of those categories, multiplying it times the weight, and then calculating the total weighted score. The value for the total weighted score will then be compared for each project opportunity. The highest total weighted score would then become the top priority for the first project that you would target for implementation. Let's look at an example of how an organization used a priority matrix to prioritize 3 different project opportunities. The organization developed criteria to measure their projects. Next, they developed the associated weight for each criterion. Then the team scored each project against the criteria using a scale of 0 to 10. The weight of each score was calculated by multiplying the weight of each criterion by the score for each criterion. For example, with Project 1 and the Criterion 1, the weight is 0.16 and the score is 6. Therefore, the team took 0.16 times 6, which calculates to a weighted score of 0.96. Once all of the weighted scores are calculated, the team determined the total weighted scores by adding up all of the weighted scores for each specific project opportunity. For Project 1, the total weighted score was 6.64. For Project 2, it was 6.81. And for Project 3, it was 7.01. Since Project 3 had the highest weighted score, this is the project that was prioritized as the highest. Once you prioritize your Six Sigma projects, it's important to then decide which Lean Six Sigma methodology you should use. There are 3 different types of Six Sigma projects. There is the Six Sigma Define, Measure, Analyze, Improve, and Control, or DMAIC methodology. There's also the Design for Six Sigma methodology. And finally, there's a methodology that incorporates Six Sigma and Lean into a Lean Six Sigma methodology. Let's explore each one. The Six Sigma methodology should be used when you're improving an existing process, product, or service. It includes 5 phases known as Define, Measure, Analyze, Improve, and Control, or DMAIC. These 5 phases take you through defining what your problem statement is, measuring your current baseline to understand how well your current process operates, analyzing the relationships between the inputs and the outputs of your process to determine the key variables, improving those key variables, and then controlling your processes by monitoring it to ensure that you sustain the gains that you've achieved. The Design for Six Sigma methodology is used when you're developing a completely new product, or when you've used Six Sigma to improve your processes to a point, but you can't reach any further improvement. This typically happens when your processes get to about 4.5 Sigma. This is where you need to go back and redesign your products to get those further gains and continue to meet or exceed your customers' expectations. Design for Six Sigma projects can take the form of IDOV or DMADV projects. IDOV stands for Identify, Design, Optimize, and Verify, and is typically a little more sophisticated in terms of the testing and validation, because it uses a systems engineering approach to design for Six Sigma projects. DMADV stands for Define, Measure, Analyze, Design, and Verify, and it's typically used more for new designs. The Lean methodology uses the framework of Kaizen. Kaizen translates from the Japanese as small incremental improvements. There are 4 different types of Kaizen applications: Project Kaizen, Process Kaizen, Kaizen Blitz, and Gemba Kaizen. For Project Kaizen, you use Lean methodologies within your projects to drive out the waste as you make improvements or design improvements for your project. For Process Kaizen, you specifically apply Lean tools to a process to improve it. Kaizen Blitz is performed as a 3 to 5 day event where a team of typically 6 to 8 people work on implementing Lean within a specific area. Gemba Kaizen is another application you can use. Gemba means go to the place. So you perform a Kaizen event in a specific location or a specific place where the process improvement needs to occur. Kaizen is best used when there is going to be a high impact on efficiency. It's also good to use Kaizen events when there's going to be a low effort required to complete the project. You want to use your Kaizen events to go after the low-hanging fruit. This also ties into using Kaizen events when you have a high probability of success, and you're doing it in an area where there is not a politically charged project. Since Kaizen is a Lean tool that focuses on reducing waste within your process, it's also good to use Kaizen in processes where you need to reduce the inventory, or the work in process, also known as WIP. The Kaizen process involves 4 key steps. The first step is to conduct a strategic business analysis to understand where you currently are as a business. This involves understanding how you're currently meeting your customer expectations and what type of competition you have. The second step is to conduct a value stream analysis. It's important to map the current state of your process to understand how it currently operates. and whether there are any potential wastes that could be removed. The third step is to look at your current state and use that information to identify Kaizen event opportunities where there are potential wastes within your process that should be removed to better meet your customers' expectations. The final step in the Kaizen process is to plan a pilot Kaizen event based on those Kaizen opportunities. Benchmarking is an important tool within Six Sigma because it helps you to identify who or what company is the best-in-class industry standard. It allows you to compare the performance of your company to that best-in-class and determine the gap between where you are and where they are. Once you've identified your process performance against the benchmark, you can establish improvement targets so that your company can become closer to that industry standard, or even better, beat the industry standard to become best in class. Benchmarking also helps in discovering methods that can help you enhance your value to your customer. It's important to understand that when you're benchmarking, you should focus on the process itself, regardless of what industry you're in, and look for what truly is best in class or the standard across all industries. There are some common categories you should consider as you start looking for organizations to benchmark. You should first try to determine who is the industry standard, and if there's a standard set that's recognized by industry leaders. You should also consider benchmarks based on regulatory requirements to determine what organizations are meeting those regulatory requirements the best. As you think about common benchmarks, consider that these organizations don't have to necessarily be within your industry. For example, if you're a small manufacturing company and you're having trouble with your invoicing and billing, rather than looking at another manufacturing company, you could look at an industry that does this function day in and day out. For example, credit card companies. The main function within their organization is to send out bills or invoices and receive payments. Therefore, you might want to look at using that type of industry as a benchmark within your own manufacturing company. In addition, if you're trying to improve customer service in a healthcare setting, you might want to look outside of the healthcare industry and find examples in the hospitality industry, where business is dependent on their customer service. There are quite a few benefits of benchmarking. First, benchmarking helps stimulate creative thinking by looking at who is best in class and determining how you will fill the gap between your business operations and becoming best in class. It also accelerates the improvement process because it gives you a target, so you can start working toward being best in class. Benchmarking also helps you set SMART performance goals. SMART is an acronym that stands for specific, measurable, assignable, realistic, and time-related. Benchmarking also leads to cost savings, because you're focusing on the process improvement that's necessary to meet or exceed customer expectations. It also helps to build confidence in the team, because you can learn where you are within your current processes and how you're better than the competition in certain areas, but also where you need to focus. So it helps to build confidence in determining where you need to move forward to as a team. Benchmarking allows you to accurately evaluate your internal operations by comparing them to other organizations. It also helps to eliminate repeating those past mistakes by focusing on how you can further improve your own operations compared to your competitors. And finally, benchmarking helps to improve communication and networking by allowing participants to work as a team to understand how to better improve your own processes. Let's examine an example of benchmarking. A large university instituted a benchmarking project to help improve how they provided educational services. The goal of the benchmarking was to improve educational accountability and academic achievement. The Six Sigma team began with internal benchmarking to understand current operations. The Six Sigma team members compiled evaluations of the internal operations for each faculty team. The results of the evaluation found a number of past mistakes and successes that were used to improve operations for each department. The next benchmarking initiative involved external benchmarking. This is where the team compared the university's improved services with 5 other world-class educational institutions by assessing academic achievement. The benchmarking results allowed the team to translate the academic quality into standards and indicators that were used to establish a quality assurance framework for how they provided superior academic services. By eliminating the repetition of past mistakes and demanding an accurate evaluation of internal operations, as well as improving communications and networking, the benchmarking team was able to gather data that allowed the university to establish performance indicators for students. This also enabled the team to set a curriculum that fulfills the customer's needs and provided a way to save money by eliminating redundant or irrelevant educational programs. There are several desired outcomes when you're performing benchmarking on a Six Sigma project. The first is to understand what is achievable by figuring out who is best in class and in what area. This also enables the Six Sigma team to determine how they should focus their improvement by seeing what is best in class. Benchmarking also helps to develop realistic targets and determine ways you should go about achieving these targets. Finally, benchmarking helps your Six Sigma team determine how to adopt the best practices. Again, by understanding who is best in class and what characteristics they are currently achieving that your organization isn't, and then performing a gap analysis, you can determine how to achieve each of those benchmarking outcomes. Six Sigma benchmarking involves 3 key layers. The first layer is measuring current performance. This is where, as an organization and as a Six Sigma team, you need to understand your current baseline performance. This will help you see whether you need to make improvements based on who is considered best in class. The second layer is to determine the cause of performance. This means understanding why your current baseline performance is where it is, and why it's set at a higher level. The third level is to emulate the work practices of whoever is best in class in that area to help improve your current performance and elevate the current performer closer to best in class. There are also some common benchmarking misconceptions, so it's important to understand what benchmarking is and what it isn't. Benchmarking is a tool for understanding who is best in class. This information is used as a method to perform a gap analysis, to understand where your business is falling short. It's also a learning process to understand how to improve your process. Benchmarking is a partnership because typically you're working to improve your process by using another organization or another department within your own organization to benchmark. By developing a partnership with that other department or organization, you can both learn from each other. Benchmarking also can be used as a warning system because it helps to identify where you're falling short based on your competition. You can use this information as a learning experience to better understand how your organization operates and where its strengths and weaknesses are. Let's now consider what benchmarking is not. Benchmarking is not easy. It's difficult to understand where those gaps are and how to better improve your own organization. Benchmarking also is not a foolproof method because there are constant changes within the business environment, and therefore making changes may not necessarily always take you where you need to go. Benchmarking is also not spying or stealing. It should be a partnership effort to understand how you can better improve your process. In addition, you should not be subjective. You should be using facts and data to better understand how to improve your own processes compared to your competition. Benchmarking is also not a remedy for all of your problems. It's a useful method to understand how you measure up to and what is best in class. Finally, benchmarking is not a strictly competitive analysis tool. You could benchmark against organizations that are not your competition, but that conduct a same or similar process. You should focus on the process itself and that function of that process, and how to make it better within your organization. Using the information you gather, you need to try and determine other opportunities for process improvement. There are 2 types of benchmarking: internal benchmarking and external benchmarking, and both differ slightly in terms of sources, benefits, and costs. Internal benchmarking involves comparing groups within your own organization, and this could be from one department to the next department. However, With external benchmarking, you're comparing peers and competitors within the marketplace. Internal benchmarking helps organizations gain self-knowledge because of how they're benchmarking their processes against each other. In external benchmarking, you also reveal the competitive environment, which further spurs innovation by looking at what your competition does. This also helps with value creation and detecting trends within your industry. Internal benchmarking can be very easy to implement because it doesn't take much in terms of extra resources or effort to compare your own processes. There is also a low risk of failure because you're not depending on external resources to gain new ideas. However, with external benchmarking, since you're trying to benchmark your organization against another organization, it can require a heavy investment of time and resources. Internal benchmarking is beneficial for several reasons. First, essentially it holds a mirror up to the organization so that you can examine and understand how your own organization is operating. By doing this, you can identify those in-house practices that are considered best practices and use them to measure and benchmark your own processes. Internal benchmarking also helps to measure the value of a unit. As a benchmark, you're looking at differences between projects, personnel, and departments to understand where those best practices are. Then you can compare your own processes to other units within your organization. External benchmarking can help you gather knowledge from leading-edge competitors to understand what they're doing differently. You can then take that information internally to help improve your own processes. External benchmarking also helps to identify demographic trends and political product niches. This helps to give you a competitive advantage by understanding what the current industry trends are. External benchmarking also helps to reveal an organization's competitive strengths and weaknesses by seeing how you compare to external competition. Based on all of the information you gather, you can prioritize your strategic initiatives to help make sure that you're moving in the right direction. Competitive benchmarking involves studying who the leading competitor is and understanding why they're the leader in that area. There are 3 different types of external benchmarking: competitive, best practices, and collaborative. Competitive benchmarking is looking at your competitors. You're looking to see who's best based on the type of process to gather the best practices. Best practices benchmarking involves looking at the process or function you're trying to achieve and looking across different industries, not just within your own industry, to determine who is best in class and who has those best practices. Finally, collaborative benchmarking implies working with other organizations and benchmarking against each other. A process occurs when you take inputs and transform them in such a way that you deliver outputs to meet your customers' expectations. The process itself involves the resources. These resources are the people, materials, energy, equipment, and environment necessary to transform those inputs into the necessary outputs. Examples of business processes include such things as manufacturing steering knuckles for trucks, the accounts payable process, or the process of hiring new employees. Each of these has specific inputs to the process as well as very specific outputs. A process has several characteristics. It has the inputs that make up what's coming in to develop the product or service. The process itself is how that product or service is assembled or changed in a way that it provides value in terms of what the customer is expecting. The outputs are what's actually being delivered to the customer, whether it's a service, a product, or a test that's being accomplished. The overall process is a series of events that produces outputs defined through several steps. Another characteristic of a process is that it has boundaries. Boundaries are the beginning and endpoints of your process. If you think about a manufacturing operation for your organization, your process boundaries may start when a casting is received within your facility. Then the process stops when that casting is machined and assembled into a final product. For example, this could be gear housing for an axle component. If you think about a service environment, this could be an oil change company, where the service begins when a customer comes in to have the oil changed in their vehicle. The process is not complete until the customer receives the car, ready to leave the facility. When you look at your processes, you need to understand that between the boundaries, you will typically have the transfer of information, or the transfer of processes between different people, departments, divisions, or processes. There are cross-functional processes. Between each step of these processes, there are transition points. This is when we're transitioning or transferring information or parts between these different departments or people. You need to pay careful attention to those transition points, because this is where mistakes commonly happen. This is where information could be misunderstood or not properly transferred. When that happens, you have the potential for defects or errors. So it's important to understand where each of these transition points are and make sure that you have robust processes in place so that the information or material transfers appropriately to the next step of the process. A process swim lane chart is a special form of a process flow diagram. It adds in swim lanes to indicate where there is a transition point between people, departments, divisions, or processes. It can be used to better understand the cross-sectional business processes, because it breaks down the process itself into who is involved in the process, whether it's different departments or individuals, and the actions that are necessary. It also takes the process into account over time, because the process moves from left to right. Anytime the process moves past one of the swim lanes, this is a transition point. You need to be careful and manage the documentation and the process to ensure that no information is lost as a product or process transfers from one department to the next. Let's look at an example. The process swim lane diagram starts with the creation of a new supplier form. The documentation is uploaded and it's submitted for approval by the originator. Then the process transfers down to SharePoint, where the General Counsel is notified. Then it moves to General Counsel, and that process may go back to the originator or stay with the General Counsel until it reaches the next step of approving a new supplier and updating the supplier library. At this point, you go back to SharePoint or go to the supplier, and then to Accounts Payable. Each step of the process that crosses a swim lane is a potential area for defects or misinformation. There are three key sources of challenges that can arise when you're trying to carry out a process improvement effort and the process crosses various functional areas within the organization. These three sources of challenges stem from stakeholders, communication problems, and cross-functional teams. The first challenge for process improvement can be the stakeholders. When you have various functional areas working together, they may not understand each other's stakeholders. It's important that these functional areas start to work together, that they have an initial discussion about who the true stakeholders from this combined effort are. Stakeholders exist in each functional area within the organization. There are three main difficulties when it comes to stakeholders. The first is getting buy-in from a variety of stakeholders across various departments and processes. The second challenge comes from managing multiple process owners and leaders. The third challenge comes from prioritizing the processes between the different departments. The second challenge is with communications. When you bring different functional areas together, for example, manufacturing, design, and aftermarket, these three separate functional areas are all within a manufacturing organization. But there still might be slight differences in the terminology used, and this could lead to communication problems. For example, if you consider three departments within a manufacturing organization, finance, product creation, and sales. When they're trying to work together to develop a new product that comes from the product design group, the sales department needs to make sure that there is a significant market to justify the new product, and they'll need to start drumming up new business for it. In addition, finance is concerned about making sure the design is cost-effective and that there will be sufficient revenue from that new product. As the three different groups communicate, probably using slightly different terminology, and focusing on different areas, it might be very difficult to manage the communication and make sure that everybody's working toward the same goal. The final challenge is having cross-functional teams. You may have individuals that are used to working together within their own functional areas. Now, when you bring these individuals into cross-functional teams across different functional areas, they have to learn to work together and function as a new cross-functional team. This can create more difficult challenges. If you consider individuals from different departments, for example, finance, product creation, or sales, they're used to working within their own teams, and they've developed working relationships with the rest of their team members. Grouping individuals with different experiences and different backgrounds in their functional areas, where they're used to a different communication style and different technical terminology, makes it a bit more difficult to bring all those individuals together to truly function as a cross-functional team that's working towards achieving a common goal. Within process improvement, the objective of a Six Sigma project is to reduce variation within processes and to provide a more consistent product or service to your customers. With Six Sigma projects, it's critical to have a thorough understanding of the process. It's also important to understand and identify all of the inputs to the process, because this is typically where the variation comes into the process. You need to understand your processes when working within a Six Sigma project. There are different resources that can add increased variability into the process and ultimately affect the output. Inputs include the material, people, energy, equipment, information, and any other resources that are input into your process. For example, if you look at a manufacturing process, these could be the castings that are coming in to be manufactured. There is variability in the castings. Then you also have the people that are working on the process, and the equipment to produce the parts. These are the inputs as well as information that's received on how to produce this product. They are all sources of potential variation. Process outputs are the result of a process. The output should be what your customer has been asking for. This should be what they see as value in the product or service, because that's what they've ordered or requested from you. The output should also be something that's measurable. It's key that when you're looking at delivering the right product or service to your customer, you can measure that output to ensure that it's meeting your customer's requirements. For example, outputs could be the service that you receive from a call center or at your doctor's office. It could be the medical diagnosis that you get. These are typically final outputs. You also need to understand that an output from one process could be an input to a subsequent process. For example, if you think about a manufacturing process, there's a foundry that makes the casting. The casting is the input to the next step, which could be the manufacturing organization, the machines, the casting. As you look at your Six Sigma projects, you need to understand your processes, how there are internal and external customers, and how the outputs from your processes could potentially be inputs to other processes. Another key aspect within Six Sigma is the relationship between the process variables. The inputs and the outputs of your process are interrelated. What happens between the inputs and the outputs is typically the key focus of the Six Sigma projects. The process converts the inputs into the outputs, so that they are what the customer is expecting. This is where you need to make sure that you're meeting the customer's expectations. Within Six Sigma, the key focus is understanding this relationship so that you can know how changing the inputs, which could be one of the major sources of variation, in a more controlled method that can help you achieve the desired outputs for the customer. When you truly understand all of the different inputs into your system, the variation that comes from those inputs, and the relationship between the inputs and the outputs, then you will be able to manage that variation and reduce its impact within your processes, on your outputs, and better meet your customers' expectations. The SIPOC diagram is an extension of the process flow diagram. It represents the suppliers, inputs, processes, outputs, and customers, and aids in process improvement by giving a detailed picture of all the relevant elements that are involved in the process improvement project. The SIPOC process starts by the team collecting a complete list of suppliers. This helps the team to identify the start of the processes, and by knowing all of the suppliers that are involved in developing the final product. Once the list of suppliers is developed, the team creates a comprehensive list of all of the inputs into the process. Once the inputs are identified, the steps within the process that convert these inputs into the outputs is detailed step by step. Next, the team develops a comprehensive list of the outputs. These could be products, services, or tasks that are accomplished based on how the inputs are transformed by the process. The final step is to determine all of the customers that receive the outputs from this process. Once the team develops a comprehensive list of the suppliers, inputs, steps of the process, outputs, and customers, this detailed information is used to build the SIPOC diagram and is added to a table to document the information. Now, let's examine a SIPOC diagram using a service example of a loan process. When you look at the suppliers, one of them will be the customers, because they're helping to supply information into the loan application process. There also would be a loan agent that's handling the loan, and a financial services or loan provider that would be involved. Inputs into the processes would include information about the applicant, the actual loan application, and then any other documentation that's necessary for that loan application. The process would involve the request for the loan and all of the steps necessary to make that request. This would include information processing on the loan, requests for any documentation needed for the loan, a loan application document that's being prepared, and then the loan application would be approved or denied once it's reviewed. Outputs to the loan process would be whether or not the loan moves forward, based on if it's approved or denied, as well as the loan policy and agreement, any commission or revenue from that loan. Then the customer of the process would be the customer that requested the loan. Now let's examine a manufacturing example of a SIPOC diagram. The suppliers would include any external resources or any internal resources when you're receiving supplies for your process. This could be the companies where you get casting or components or the tooling for your process. The inputs to the process would be the casting, the components, the tooling, the equipment, and the information. The process itself could consist of several manufacturing pieces of equipment. Perhaps there's 5 different manufacturing steps that are followed by 3 assembly steps, when you're actually transforming that casting into a product, and then assembling it to produce the final product. The output would be the product. The customers could be the next step in the process, which may be another assembly process that uses this assembly in a larger assembly. You've probably heard that stakeholders are the necessary ingredient for any project success. So who exactly are your stakeholders? And why are they so important to your project? In a general sense, a stakeholder is anyone that has a stake in the project. When examined more specifically, a primary stakeholder is anyone who directly benefits or is affected by a certain business activity. This could be a product or a change to a service agreement. Primary stakeholders include employees, investors, company owners, creditors, and suppliers, among many others. Secondary stakeholders are individuals that have a more secondary stake in what's happening in the project. These could be members of the public or families. For example, for an organization that makes lighting systems for residential customers, the primary stakeholders would be the customers that actually receive the product, the lighting systems. But you'd also have employees that help to make the product. You'd have vendors that buy the product and sell the products to the customers. You'd also have the stockholders for the company. In order to improve your processes and products with Six Sigma, you need to identify your stakeholders. This can be done using brainstorming sessions, for example, with your project sponsor or your team. When you brainstorm with your team, there are several key questions that you should ask and consider together. These questions include who would be impacted, who would provide the inputs, who would use the inputs, who might hamper the progress, and who uses the process. These questions will help you identify who should be included in the list of stakeholders for your project. Stakeholder management is critical to the success of a project. If stakeholders are not supportive or they are against the project, their impact can be extremely detrimental to the success of the project. There are times when a stakeholder may even want to impede the progress of a project, potentially because there's a competing interest and a lack of time to focus on the specific project. There are 2 factors to consider about every stakeholder. The first is their level of interest in the project and its outcome. The second is the potential impact or power they can have over the outcomes. You need to understand the goal of stakeholder management. It's to get reluctant or potentially hostile stakeholders on the side of the project to the point where they're positive about the project. You also want to get uninterested stakeholders enthused and actively supporting the project. There are a couple of tools you can use to help manage stakeholders. The first tool is the Stakeholder Register, which is used to identify and manage stakeholders. The table that's used for Stakeholder Register shows the overall attitude of the key stakeholders and their impact on the project. It can also include some other useful information on the stakeholders. In addition to their name, it also typically includes their role, their attitude toward process improvement, and their potential impact. Other information that can be included is their contact information, any communications requirements that might help change their attitude toward the projects, and the expectations that they would have on these projects as well. Another useful tool you can use to manage and identify stakeholders is a stakeholder matrix. Stakeholders are added to a 2x2 grid according to how they fit into certain characteristics. For example, stakeholders could be high power or high interest. Other possible characteristics that are commonly used are their power versus interest, power versus influence, and impact versus influence. The stakeholders that land in the high quadrant are the ones that require the most attention. When starting a Lean Six Sigma project, you need to start identifying the key players who enable success of the project. One of the key players is a process owner. The process owner is the person who's managing or overseeing the process that's going to be worked on for the process improvement. Therefore, it's important that the process owner thoroughly understands the process that's the subject of the Six Sigma project. Process owners are the people that are responsible for the overall success or failure of the process improvement effort. Process owners need to be involved because as the Six Sigma team comes in to make the changes to the process, if you don't have buy-in from the process owner, it's going to be very difficult to make the changes necessary for the process improvement. Even if you make those changes to the process, once the project is done, it would be very difficult to have sustained success if you don't have that buy-in from the process owner. Another key player in the Six Sigma initiative is the project champion. The project champion is typically a high-level individual that sits at the management or executive level. This person is one that helps to provide resources and support in terms of the Six Sigma initiative. Project champions help select the projects because they know how the long-term vision of the organization is supported. Project champions typically have fairly limited experience with Six Sigma. However, they act as a liaison between the long-term strategic goals of the organization and the Master Black Belt. They help to make sure that the right Six Sigma projects are being selected to help move the organization in the right direction. Now, they wouldn't necessarily have all of the statistical and process improvement knowledge to train or mentor any of the black belts or green belts or yellow belts. But these would be the individuals that would help provide the resources to make sure the projects are getting done and are successful. Six Sigma leadership starts at the high-level executive team or top-level management, and this makes up the enterprise leadership team. This is a part of the organization that helps to provide the strategic vision and to make sure that Six Sigma is being implemented throughout the entire organization. They help to provide the resources and support for the training. Below the enterprise leadership team is the business unit leadership team. This is where the projects start getting selected within each business unit to make sure that the overall success of the organization can be achieved through process improvement projects. The next level is comprised of the improvement project team. These are the teams that are directly working with the Lean Six Sigma projects. They're making sure the projects are getting done, and they're actively involved in the process improvement activities. Then below this level are the team supporters or the employees. These are the people that might be called in on an ad hoc basis to make sure the improvement project team can meet the requirements and deadlines. The black belts and the green belts are part of these team supporters and employees. They help pull in the right employees to get their projects done. Then, the team leader and the coaches typically sit at the level just below or around the business unit leadership team. There are two groups of leadership when we talk about a Lean Six Sigma initiative. These are the enterprise leadership and the Six Sigma team leadership. The enterprise leadership group establishes a vision. They have a strategic view of the organization, which they can use to help allocate the appropriate resources to make sure that the Lean Six Sigma projects are actively being worked on. Because of the strategic view, the enterprise leadership team also has an enterprise focus. The other aspect of the enterprise leadership team is that they can help remove roadblocks and help facilitate change because of their role within the management structure. The Six Sigma leadership is a group that implements the vision. They have more of an operational orientation toward process improvement. They manage the resources that are provided by the enterprise leadership team to make sure that they can get the projects done in an adequate time frame. This team also has a project goal focus because of their role within Six Sigma process improvement, and they're able to manage the roadblocks and change necessary to make sure that they can reach their goals toward their project improvement initiatives. Another key role in the Six Sigma initiative is the Six Sigma Green Belt. The Six Sigma Green Belt is an individual in the organization that's using Lean Six Sigma tools directly as they relate to their own function within the organization. They're mentored by the Black Belts and typically receive their training from them. Their projects focus mainly on their own functional areas rather than Black Belts, who could be distributed throughout the organization for the process improvement efforts. The Green Belts focus on the process improvements that make their job easier, which roll up into improving the overall effectiveness of the entire organization. In this topic, we'll explore the concepts of the voice of the business and voice of the customer, and we'll compare and contrast the perspectives of each. When thinking about Six Sigma projects, your goal is to meet or exceed your customers' expectations and requirements. So when you talk about your requirements, you need to look at them from two different perspectives. The first is the voice of the business, which is essentially your business requirements. The second perspective is the voice of the customer. These are your customers' requirements and expectations. The voice of the business, or VOB, is the process of capturing the business requirements. These requirements are the needs or constraints of the internal customers. They include requirements that relate to the process, cost, safety, and delivery. Typically, the voice of the business focuses on internal efficiency and productivity. It's directly influenced by the necessity of solving operational problems and improvement issues. These business requirements are essential drivers of the organization, typically derived from the mandates, goals, and objectives of the organization itself. They deal mainly with inputs. There are also constraints from budgets, governments, or regulatory bodies. These are typically related to resource limitations and may impose technical or budgetary constraints on a project. The voice of the customer, or VOC, is a process of capturing customer requirements. That is, the needs and desires of the organization's customers. The customer could be the purchaser or the end user of your output. The needs of the customer are typically expressed in terms of what's unclear and in need of more qualification. You might need to do some more digging to really understand what your customers need because of their wording or feedback. For example, sometimes these could be expressed as terms such as attractive, effective, profitable, or rapid. You might have to drill down to really understand those needs. These customer objectives are typically given in quantifiable terms that indicate what features a customer would like, typically in terms of quality, the purpose of the output, or the functionality the customer is looking for. It's important that you gather this information from the customer because, as an organization, it helps you determine which products or services you should offer and where you should focus your process and quality improvement efforts. The voice of the customer is provided in a couple of ways. It's a complete set of customer needs. It's expressed in the customer's own words, and it reflects how the customer sees, uses, and interacts with the organization's outputs. Using this information, you can prioritize the voice of the customer based on the importance to your customers. The voice of the business are the business requirements, including profitability and return on investment, cost, and productivity. The voice of the customer are stated customer requirements, including value, price, durability, and features. It's important as an organization to understand that you need to gather information on both the voice of the business and the voice of the customer to get those two different perspectives. Having that information helps an organization understand the overlap, and that overlap is what helps you provide quality customer support and deliver to meet or exceed the expectations of those customer requirements in order for the organization to be successful. The voice of the customer strategy includes 5 key tasks. It starts with defining the goals of your voice of the customer process. The next step is to identify your customers, the customer types, and the segments in relation to your projects. Once you understand who your customers are, the next step is to plan and collect your data. Then you need to analyze the data you've collected. Finally, the 5th step is to determine the customer requirements, and then use them as action goals. Now, let's consider an example of a Six Sigma project at an online technology retailer to demonstrate how you could implement the voice of the customer strategy. Within this technology retailer, sales have been lagging, and some customers have indicated that they're not happy with the billing process. So let's examine the first 3 steps. The first step is to define the voice of the customer process goals. The Six Sigma team at the online retailer has concluded that the process goal of their voice of the customer exercise is to determine why their customers are unhappy with the current online billing process. The team writes a purpose statement of determining why customers are dissatisfied with the company's billing process. The team then moves on to identifying their customers. Since they're an online retailer, the customers they want to talk to are the online buyers using the company's website, within a specified demographic group and market segment. They want to make sure that they're capturing the voice of the customer from their key customers, who are between the ages of 18 and 30, based in North America. The third step is to plan and collect the voice of the customer data. Since the company collects customer information through online profiles, the team has information on which of the regular customers have had billing issues in the past month, and on which customers have filled out online complaints or called the help desk about their issues. The team can collect information from those complaints and from follow-up data from customers when they need to fill in the gaps. The last 2 steps for the online technology retailer are to analyze the data and then determine the customer requirements. While the team is analyzing all the data, they're able to determine that customers want immediate confirmation of their payment and an online receipt, which are very important to correcting the billing process. The team is able to do this by using Six Sigma tools such as the Kano model, quality function deployment, and critical to quality trees, which help to identify trends in the marketplace and determine ways to better meet customer expectations. That led to the 5th step of determining the customer requirements. The team is able to understand that their customers enjoy the store's low prices, but really want better service at the checkout and better information about their payment. Therefore, a key customer requirement is focused on improving the payment gateway and the checkout and billing processes. The team sets the goal of meeting this need as their top priority. They want to make sure the payment gateway is the key focus of their project, so it becomes the basis for their Six Sigma project. With process improvements, it's important to understand your customers. And typically, when you're talking about your customers, you're thinking of your external customers, the ones who are outside of your organization and are typically your final customers. They're the ones who pay for and consume your products and services. But it's also important to remember that you have internal customers within your own organization, your internal coworkers. They also play an important part in understanding the expectations of all of your customers. With Six Sigma, it's critical to identify all of your different customers and to know all of your expectations and priorities based on both internal and external customers. It's essential for process improvement. External customers are those people who are external to your organization. They're usually the final buyer of your products and services, but it could also be a channel purchaser. In other words, a distributor, retailer, reseller, or independent representative within the supply chain. These are all of your external customers because they're external to your organization and pay for your products and services. If you're thinking about a banking operation, then your external customers are external to the bank. These are the patrons who have bank accounts within your organization. If you're in healthcare, your external customers are your patients, the ones who are coming in to be treated for an ailment or for their annual checkup. Your internal customers are those customers who are internal to your organization. They get value from or are affected by downstream processes, and are the people who work to serve the external customers. Our internal customers are also people that work to make products and services available to external customers. Think about a receiver of the next operation. If it's an internal department, it should be thought of as an internal customer. For example, think back to the healthcare example. When a physician submits a request for a prescription in a hospital, the internal customer could be the pharmacy within the hospital. When you think about banking, when someone comes in to apply for a bank loan, they see a loan agent. However, the next step of the process, and whether or not the loan is approved, is typically handled by a loan manager or a department manager. They receive all the information, so they are a customer to that information within the process. A useful tool for understanding the customer value chain related to your internal and external customers is a SIPOC diagram: the suppliers, inputs, processes, outputs, and customers diagram. It documents the external and internal customers and the entire value chain, and helps to indicate and illustrate the internal and external customers within the process. If you think about a process, both the internal and external customers fit in your organization's value chain and can be depicted on the SIPOC diagram. The internal events or processes overlap with each other at the handoff points between the internal customers, producers, and suppliers. The points where the processes overlap form the links in the chain. Each link is an area where internal customer satisfaction can be tracked and improved. You can then observe the impact it has on your final external customer. When you start with Lean Six Sigma projects, it's important to understand the potential benefits they might have for internal customers. These benefits often translate to benefits for external customers as well. So you need to make sure that you're carefully listening to the needs of both your internal and external customers. For internal customers, such as suppliers, process owners, and employees that are linked to a particular process, product, or service being improved with Lean Six Sigma efforts, there are several potential benefits you might see. The first is a more streamlined and efficient process that's less complex. As well, you'll typically see some general reskilling, retraining, and retooling as part of the Six Sigma project. Within your process improvement efforts, these can also alter process inputs, output requirements, or tool requirements. This has an impact on the scope and schedule of work, which might also impact how you streamline procedures and methods within your process environment. Finally, internal customers typically see improved process outputs by making these changes through Lean Six Sigma efforts. These are what are often translated to external customers. There are also several benefits that Six Sigma projects can have on external customers. The first is looking back at internal customers. The benefits that internal customers realize are often translated to benefits for the external customers as well. In addition, external customers typically see improved quality, delivery, and service based on the continuous improvement efforts of the Six Sigma team. And since the Six Sigma team prioritizes projects, the projects that they're working on often address the most pressing customer needs and requirements. Also, as a team focuses on making improvements within their Six Sigma initiatives, they are continuously going back and talking to the customers, both internal and external, to make sure they understand the customer's requirements. This leads to better communication with the customer. Finally, since quality, delivery, and service are being improved, as in communication with customers, external customers also have an increased satisfaction with the company in its service and products that are being offered. Collecting customer data is essential with a Six Sigma improvement project. It helps the Six Sigma teams that are implementing the voice of the customer strategy to translate raw customer data into precise customer requirements during the define phase of the DMAIC project. These critical customer requirements need to be known and measured before you can move on to the next stages of a Six Sigma project. Typically, organizations like to collect customer data in terms of the number of defects or trends. Collecting this data allows teams to identify urgent problems that they're facing and determine how the organization can gain a competitive advantage. It also helps teams know their customers' preferences and needs. It helps define what products and services should be offered, and also the critical features and specifications for those products and services. It helps determine the customer's desired level of quality, and this helps the organization measure customer satisfaction to ensure that customer needs and expectations are being met or exceeded. Data sources can either be primary or secondary, depending on the type of information you want to collect. Primary data sources come from direct interactions with the customers, including observations, interviews, focus groups, or surveys. When you're using primary sources of data, you should go straight to your customer to collect your data. This is why these methods are called direct sources. Secondary data sources are also called indirect sources. These are the sources that already exist. This might be information that you've collected for another purpose, such as a different project that you're working on. Other sources of secondary data include industry experts, market watchers, other external resources, and other internal projects. Typically, with a Six Sigma project, you're going to use both sources of data collection. As you start collecting the data from the voice of the customer, you start understanding the customer's needs and the wants. It's important to use that information in a general input-process-output flow to understand how everything functions together. Start by collecting data on what customers actually want or need. Then this data is converted into useful information, such as identifying desired characteristics for all of the raw materials, quality levels, and process steps. This helps further define processes and reach the desired output. Collecting data from customers is not a one-time event. Customers' expectations and requirements change over time, so it's important to have an ongoing customer feedback loop within the process to ensure good organizational processes and responsiveness. You need to be able to respond quickly to these ever-changing customer demands. This enables you to meet all of your customers' expectations and requirements by continuously gathering that information. The continuous feedback loop must be established, and it's important to be responsive to the changes in customer preferences. In this topic, we're going to talk about data collection tools. There are 4 commonly used tools: observations, interviews, focus groups, and surveys. We'll get into each of these in more detail and when they should be used. The first data collection tool is observation. Observations are useful because they allow you to watch your customers as they're using your product or service in the environment where they'd actually be using it. So it gives you that real-life environment. Because you have no control over their actions, and it's typically how they would use your product or service, you're able to get a much more realistic, first-hand understanding of how they interact with your process, product, or service. It's also a good method to use if you want to observe your customers in their normal environment. For example, you could observe them using your product in a lab-type setting, where the work situation is set up, and the participants are interacting. You should use observations when you want to get insight into what it's really like to be one of your customers, or if you need to see how something is being used. Also, if your customers aren't aware that you're gathering data, you're more likely to get insights into how you should improve your products and services, because you can actually see them using your product. The next type of data collection tool is interviews. Interviews are conducted with customers, either face-to-face or over the telephone. They're typically done for 2 reasons. First is that interviews help you to gain a reasonable, unbiased view of your product or service from the customer's perspective. Second, interviews also help ensure that you're not overlooking issues that could negatively affect your value and your customer satisfaction. Interviews are a useful data collection tool when you need to get an individual's perspective rather than a group's. The fact that they can be conducted in person or over the phone adds to the advantage of getting insight from that specific customer. When you conduct your interviews face-to-face, you can also gather other information, such as facial expressions and body language from your customers. If you're conducting these interviews over the phone, you can gather information about the tone of voice. Interviews also allow you to gather a unique perspective because you're going to ask more open-ended questions, and they help enable you to pursue unexpected lines of information. You might ask a specific question, and then based on how the customer answers, go further down that path and look for clarification. This data collection method really helps you pursue that. In addition, because you ask those follow-up questions, interviews help to provide a more in-depth understanding of what you're trying to gather from your customer. Finally, these insights you're gathering from your customer may lead to further innovation in your products and services. Face-to-face interviews can be very helpful because they provide an opportunity to really create a rapport with the person that you're interviewing. This may not be as easy to do if you're trying to collect this information over the phone. Face-to-face interviews allow you to capture visual cues, such as body language or facial expressions. They also allow you to make eye contact, so you can pursue more complex questions and have a more in-depth conversation. Based on these qualities, face-to-face interviews can be a much more personal way of gathering data from your customer to understand their needs and expectations. Interviews over the phone also provide several benefits. They help you gather information from customers who are widely dispersed over a large geographic region. They're also good for collecting information about basic or simple issues, where you may not need to talk about more complex issues or ask follow-up questions. Phone interviews are useful because you can usually get them done in a fairly short time frame, providing a quick turnaround on the information. And they're a good way to get a lot of data at a fairly low cost. Another data collection tool is a focus group. Focus groups typically consist of a small group of current or potential customers involved in a more structured discussion. Using this method allows for more spontaneous information than interviews. You can use this discussion to explore participants' needs, options, and attitudes in more detail. A focus group helps you gather information from a small group of customers. Typically, you'd include 10 people or less. It helps you gain participants' feedback in one place at one time, and it's a good setting to help with brainstorming and really watching your customers bounce ideas off of each other. Focus groups can be very helpful when you're trying to gather information from customers who have similar product or service needs. You can conduct a focus group of people who are in a similar segment. For example, if you have purchasing managers from several companies who buy your product for their own manufacturing needs, you could gather them together to get their insight. Focus groups are typically more beneficial than other methods because they're not as restrictive as surveys. Also, you can ask more open-ended questions and meet with several participants at once, so it's not as time-consuming as doing individual interviews. Focus groups are also helpful because you introduce props. You can tie in your product's prototypes and marketing material, and then see how the customers interact with those props to gain further information. The fourth type of data collection is surveys. Surveys are useful because they're very versatile. You can conduct them in person, over the phone, or by email. They allow you to collect extensive information from a large group of customers, and the responses you gather from them are quantifiable, meaning you can have statistical output, where other methods provide more qualitative data. In addition, surveys can be used in conjunction with any of the other data collection methods. They're also a good way to gather quantifiable data in a very consistent way, since a survey is exactly the same every time. Because it's the same every time, a survey is most useful when you have a basic or simple issue that you're trying to solve. In addition, because surveys can be sent out broadly, and you don't have to set up interviews or focus groups, you can usually complete them in a very short time frame with a very quick turnaround. So you can get a lot of data for a very low cost. In order to have effective data collection, the data collected must be valid, reliable, and bias-free. This is what's going to make it useful and hold up to scrutiny when you do your data analysis. Within Six Sigma, there are three key terms that refer to accuracy in data collection. These are reliability, validity, and margin of error. Reliability is the consistency of the data collection method. The higher the sample size in relation to the population size, the more reliable the data. Validity refers to the accuracy of the data collection efforts. What we're looking for here is whether the chosen data collection method actually measures what it's supposed to measure. If it does, then it's considered valid. Margin of error ties into surveys because they are subject to some uncertainty about how well a sample represents a population, and the validity and reliability of the testing tool. It's important to make every effort to ensure your data is free of error, because this can impact both the reliability and the validity. In other words, the error shouldn't be so significant that it prevents you from reaching valid conclusions. There are two types of errors when you talk about sampling error: sampling error and non-sampling error. A sampling error is statistical in nature and is caused by human error. Sampling error from surveying is where a particular portion of the population is surveyed, versus getting a representative sample from the entire population. As a Six Sigma professional, it's important to understand how effective data collection ties into Six Sigma. Reliability and validity are the cornerstones of effective quality data collection and are necessary to guide your Six Sigma improvement efforts and minimize the margin of error. If your data is consistent, stable, and repeatable, then you know that you can rely on the results being accurate. You also need to know that the method you use to collect the data is actually measuring what it's supposed to measure. Otherwise, it's going to lead you to erroneous assumptions when you go to analyze the data. Vagueness and ambiguity are both causes of ineffective data collection. It could be further caused by poor instrument design, which leads to erroneous readings. It's important to avoid using subjective measures, because when you go back to truly understand what you've measured, there may not be a clear definition. Ineffective data collection can also be caused by asking non-specific questions, or asking the wrong questions. Another cause of ineffective data collection is bias. This is a common data collection error which is systemic in nature. Bias can lead to significant error and incorrect conclusions in your research and process improvement efforts. Bias typically occurs when data is influenced in some way, so it no longer represents the populations being sampled. Bias can also affect your research and process improvement efforts. For example, you may have a survey respondent that gives you responses that don't truly reflect his opinions, because he wants to appear in a certain way. Or you might have an interviewee who's uncomfortable with the interviewer, so she rushes through her answers because she wants to finish the interview. In this topic, we're going to discuss data bias and errors. More specifically, we're going to talk about common sources of bias and error in data collection. If you have too many questions, it could cause bias error in surveys and interviews. You want to make sure that surveys and interviews are fairly concise, and that you're focusing on the right questions. Otherwise, it may lead to some ambiguity in trying to understand the customer's true responses and what's important. In addition, if you have multiple questions in one, it can lead to errors in all four data collection methods: surveys, focus groups, interviews, and direct observations. Because you're not asking a specific and direct question, it's very difficult to capture and really get to the heart of what the respondent's true response was. Bias and error in data collection can also be caused by how you lead your phrasing. Surveys and interviews are developed to ask very specific questions, but if you're not careful in how you word these questions, you might be leading respondents in a certain direction. In addition, you can also lead by behavior. With surveys, focus groups, and interviews, you can phrase questions and ask them in a certain demeanor, which again leads the customers down a specific path. Bias and error in data collection can also be caused by the surroundings, particularly in interviews and direct observations. Because they're conducted in the location where the product or service is actually used, you need to be careful to make sure it's as realistic as possible. Otherwise, there might be some outside influences that can bias the results. With surveys, focus groups, interviews, and direct observations, there can also be bias and errors from sampling errors. There are two different types of errors here. The first is non-sampling error, which is statistical in nature and caused by human error. And then there's sampling error, which results from surveying only one portion of the population, rather than getting a representative sample of the entire population. Errors can also come into play in data collection efforts when there are poor results. When you're conducting surveys, focus groups, interviews, or direct observations, you need to make sure you have a sufficiently large sample size. If you don't have enough respondents, the results are going to be poor and not necessarily representative of your entire population. And finally, if information from surveys, focus groups, or interviews is received in such a way that it's difficult to interpret, that might lead to erroneous assumptions, or using tools incorrectly to analyze the data. In the end, you could come to incorrect conclusions about the data. It's important to review your data collection questions to help eliminate vagueness, ambiguity, and bias. There are 4 factors that contribute to the ambiguity and bias that lead to ineffective data collection. These are poor design, subjective measures, incorrect questions, and non-specific questions. Let's consider each of these in more detail. Poor design refers to a poor instrument design. This could be a poorly designed survey or poorly designed questions. With surveys, you want to make sure the flow is effective and that anybody taking the survey can easily understand what the questions are. With respect to poorly designed questions, you need to make sure that you don't have too many questions and that you're not fully covering all the possible ratings for each question. These can lead to errors in data collection, which makes the data collection effort ineffective. Subjective measures can also lead to ineffective data collection. When gathering the voice of the customer through surveys, focus groups, interviews, or other means, it's important to ask questions in such a way that you're not asking for subjective perceptions. You need to ask for objective measures. For example, rather than asking a customer how they feel about a certain situation, you could ask them how often a certain situation occurred over the last week, month, or year. This will provide a more objective measure and more quantifiable data. Non-specific questions can also lead to ineffective data collection. If you're asking non-specific questions, then you're probably going to get non-specific answers. For example, if you ask a customer about their overall experience during their last banking transaction, you're going to get a high-level view. But if you're trying to understand the friendliness of the tellers and how helpful they are, then you'd want to be very specific about the customer's experience with regard to those aspects. It's important to make sure you're asking specific questions around what you're trying to improve. And lastly, incorrect questions can also lead to vagueness, ambiguity, and bias, which further lead to ineffective data collection. It's important to make sure you're asking the right questions. One way to make sure you're avoiding asking incorrect questions is to go through and do a pilot study. This requires developing your data collection methodology, and then going through that methodology with several individuals initially to make sure you're getting the responses you expect, and asking questions such that the data you collect with this pilot study is answering the appropriate questions. As a Six Sigma team, it's critical to understand your actual customers' requirements. You must know these requirements before you can translate them into product features, performance measures, or opportunities for improvement with your Six Sigma projects. Customer requirements are based on 3 elements: expectations, needs, and priorities. Understanding customer requirements is critical for this. Customer requirements are a complex group of criteria that customers use to make their purchasing decisions. Therefore, you really have to listen to your customers to make sure you're gathering the right information. Your organization might offer what it thinks is the world's greatest product, but if the customer doesn't want it and isn't going to buy it, it has no value. It's your customers who determine the value of the product. and they convey their requirements by either buying the product or not buying the product. With this information, your customer requirements can be translated into project goals and objectives to help your organization become more successful. Customer expectations are those requirements or needs from your product or service that make it a value and worth buying. The customer expectations are typically classified in a hierarchy, where they can be basic, expected, desired, or unanticipated. Basic expectations are the absolute minimum qualities that must be present in order for your product to be acceptable. For example, if you're buying a new television, a basic expectation would be that your television comes with a remote control and it functions properly. Expected qualities are those that generally come with a normal product. For example, your television should include an instruction manual and a warranty that protects it from initial defects. Desired expectations are the next step. These are the things that your customer would specifically ask for. For example, they might want their television to be high definition. Unanticipated expectations are those things the customer isn't even aware of, so they wouldn't even know to ask for it. This could be a market differentiator. For example, your television might have an interactive display, which would be an unanticipated feature that would provide a competitive advantage and additional value. Customer needs are always changing and evolving. This can be very good for your business if you're able to provide products and services that meet these ever-changing needs. But it can also be very difficult to figure out what is it your customers actually require. Once your customers' basic needs are met, new needs are often created. There are 5 different types of customer needs. The first are stated needs. These are what the customers actually say they want, so you need to listen to and understand what your customer is specifically asking for. The real needs refer to what customers actually need. Perceived needs are what customers think they need. Cultural needs refer to the status that the customers think they will attain from buying a product or getting a service. An unintended need occurs when customers use the product in an unintended way. Customers have different needs depending on whether they are buying a product or getting a service. When talking about a product, there are 6 things that customers need. The first is convenience. Customers have very busy lives, and they want products that are going to help make those lives easier. For example, food items that are prepackaged and only require reheating to help save time. The next is safety. Safety is becoming an ever-increasing concern for customers, and it's also an aspect when you're creating new products. For example, an easy-to-use baby gate could meet the customer's safety needs. Customers are also looking for simplification features. They don't want to spend hours trying to figure out how to use a new product. Simplification features, such as a one-touch menu on a cell phone, make it easier for customers to use new products. Customers are also looking for communication. They need to feel informed, and they want access to information about the products they buy. An example would be a 24-hour hotline that provides information about the product and potential recalls. Customers also want service for their product. If they buy a defective product, they want to know that the company will refund their money or offer a replacement. Service could also mean warranties or exchange policies. And finally, customers want service. They want access to trained personnel that can help solve problems or handle complaints. For example, having a customer service employee that's authorized to offer solutions without having to speak to a supervisor. There are 7 specific customer service needs. The first is convenience. Busy customers want services that offer them convenience. For example, many companies are now providing personal shopping for customers who don't have time to run their own errands. Second is courteousness. Customers require courteousness when they want to buy a service. For example, when you go to a restaurant, you expect your server to be polite. If they aren't, you're probably going to leave a smaller tip. The third is competent and reliable staff. Customers expect to deal with competent and reliable staff members when they pay for services. For example, when a customer drops off their dry cleaning, they expect the staff member not to ruin their clothes. Customers also expect responsiveness. They want to know that when they have a problem with the service, the company will respond quickly. For example, when a hospital patient has a concern, they don't want to wait hours to get a response. Next is safety. Customers expect service providers to keep safety in mind. For example, if you have a customer that's taking a taxi, they want to know that the driver has a license and can get them to their destination safely. Then there is trust. Customers want to be able to trust the companies they buy their services from. They want to know their service providers are being honest and truthful in their intentions. For example, when you open your power bill, you should be able to trust the charges are correct. And finally, facilities. When customers visit a service provider's facility, they expect a certain level of cleanliness, and they also expect everything to function properly. For example, when you visit your bank's ATM, you expect that you're going to get the money that you requested. The final element of customer requirements is determining your customer's priorities. You need to understand which of your customer's expectations and needs are most important, because this helps you know what should be your company's first priority. You can use data collection tools such as surveys, interviews, or focus groups to pinpoint customer priorities. But it's important to keep in mind that this shouldn't be a one-time effort. A high priority today might be unimportant in a year. Customers' expectations and needs are ever-changing, and it's important to prioritize those needs and expectations in a way that your company can respond to quickly. This will help you, as an organization, continue to provide the products and services that your customers find valuable. The Kano analysis, or Kano diagram, is a method that's used to identify true customer requirements. The Kano model puts each product or service characteristic into one of 4 quadrants. It helps you graph where each aspect falls with respect to the performance of the product or service in relation to customer satisfaction. On the x-axis, it measures if the product or process is incomplete or performs poorly, all the way to performing well. In terms of the y-axis, it starts with low customer satisfaction and then moves up to high customer satisfaction. Kano analysis addresses 3 levels of customer needs: dissatisfiers, satisfiers, and delighters. Dissatisfiers are those basic level quality requirements that customers expect to have. For example, customers assume that a cashier will be able to give the correct change and that a mechanic will be able to fix a flat tire. Satisfiers are those little extras that keep customers happy. For example, satisfiers may include waiting for less time than expected at a bank's drive-up window, or getting a free oil change with automotive service at a dealership. Delighters are the unexpected and exciting attributes that give customers more than they expect. As a customer, you might be delighted when a bank teller greets you by name, or if an automotive service department at a dealership washes and vacuums your car. So let's examine an example related to home buyers. Dissatisfiers would be that I assumed it meets all federal, state, and local building codes. Satisfiers are the spoken needs. I've asked for a 3-car garage, 3 bedrooms, and 2 baths. And those unspoken things are, I know it when I see it. And a delighter could be something like a lifetime warranty on the roof. Quality Function Deployment, or QFD, is a tool that takes the voice of the customer, the VOC, and translates it into the process, product, or service designs. The goal of QFD is to translate those often subjective criteria into objective criteria, which can then be used to design and manufacture a product or service. The QFD methodology is divided into 4 key phases, each of which uses 1 or more matrices. It starts with product planning. That information is then translated down to the part deployment, which is then translated down to process planning, and then finally to process control. QFD enables the voice of the customer to be used throughout the high-level design to how you manage your processes and critical characteristics to ensure you continue to meet the voice of the customer requirements. Quality function deployment consists of 4 phases of interlocking matrices, which connect the voice of the customer that you're taking into this process into the design requirements and the product features. The first phase is the product planning. In the product planning phase, the customer requirements are converted into design or technical requirements. This information is then taken into the second phase, called the part deployment phase. The technical requirements become the input into the part development phase. This is where the technical requirements are converted into part requirements. Then you move into the process planning phase. This is where the part requirements are taken into the process planning phase to make sure that you have the appropriate process planning characteristics to fulfill the necessary part requirements that have been identified. In this phase, you also start to select your process. The outputs of the process planning phase are then used as inputs to phase 4, the process control phase. This is where you develop the process control, inspection, and test methods to make sure you're monitoring and controlling the process. With quality function deployment, by having all of these matrices interlocking, you can make sure that the voice of the customer is your key process input and is translated throughout each of these matrices to ensure you maintain and control voice of the customer requirements. This helps ensure that you meet or exceed your customer's expectations. The first phase in quality function deployment is the product planning phase. This phase provides an integrated set of tables. When completed, looks like the structure of a house. This is where it gets its name, the House of Quality, or HOQ. HOQ matrix allows you to identify customer requirements and determine their technical implications and the relationships between these different aspects. The House of Quality is an integrated set of tables that are created during a product planning phase in quality function deployment. The initial matrix, the House of Quality matrix, allows you to identify the customer requirements, or the VOC, to determine the technical implications and infer relationships between the different technical requirements. These integrated tables work together to take in the voice of the customer, those customer requirements, and translate them into technical requirements. The House of Quality matrix is divided into several rooms. There's the customer focus, and then the rest really helps focus on the technical aspect and the relationships between the customer and the technical issues. Now let's examine what a finished House of Quality could consist of. There's a considerable amount of information that's contained in just one matrix. The customer requirements are located in the House of Quality. Then you have design considerations, and you also have different design alternatives that are put into the grid. Then, weighted scores are assigned based on market research, so that you understand how you rank against your competitors. This greater matrix documents the design team's perspectives of the relationships that exist between these different items, so that these relationships can be interpreted in the downstream processes of QFD. It's important because the House of Quality documents how the product addresses and satisfies all of the customer's stated and unstated needs. In this topic, we'll be discussing the customer focus areas of the House of Quality matrix, or HOQ matrix, starting with the customer requirements. These requirements are contained in the first room. The customer requirements list the customer's needs and wants. This is the voice of the customer for a particular product or service. These requirements are derived from the customer statements gathered during the initial phase of quality function deployment. Oftentimes, these will be referred to as the whats of the House of Quality matrix, because this is what the customer requirements are. The second room in the House of Quality is customer importance. The customer importance component is where the customer's perceptions and priorities are listed for each of the customer requirements, or the voice of the customer. Now, the information used to prioritize this is typically gathered during the market survey. This is where the team would determine, based on the customer survey feedback, what the importance is for each customer requirement. Then this information is rated on a numerical scale, to provide that prioritization. In this topic, we'll be discussing the House of Quality, or HOQ, matrix rooms that have a technical focus. Let's start with the room in the House of Quality that contains the technical requirements. This is where the team lists the measurable product specifications that are defined by the organization. It's where you define how the customer requirements will be met. The technical requirements are often referred to as the hows in the House of Quality matrix, because this is how you're going to meet the customer requirements. The next room in the House of Quality is technical priorities. This is where the team would detail the priorities and the measures of technical performance that are going to be achieved by competitor products. It's also important in this section to show the degree of difficulty involved in developing each of the requirements assigned to the technical requirements. This is how the product will be evaluated with respect to those priorities throughout the entire design process. It's important to remember that these values are based only on estimates of the probability of achieving these target values at this point. Typically, the technical priorities are rated on a scale of 1 to 5. The next aspect of the House of Quality is the interrelationship section. The interrelationship matrix shows how the design team's perception of the relationship exists between the customer requirements and the technical requirements. These relationships between requirements are classified as weak, medium, or strong. The purpose of the interrelationship diagram is to ensure all customer requirements have been addressed by a technical requirement. Otherwise, you'd miss one of the important customer requirements. The last room in the House of Quality is the technical correlation matrix. This is where the team identifies technical requirements that either support or impede each other in the product design. In other words, it's important to understand the relationships between the technical or engineering characteristics so that designers can identify what trade-offs need to be made. The technical correlation matrix, commonly called the roof of the House of Quality, is where the team classifies these relationships either as positive or strong positive, if the technical requirements support or help each other, or as negative or strong negative, if the technical requirements impede or hinder each other. In this topic, we'll explore the steps for creating a House of Quality, or HOQ, matrix. There are 6 steps involved in creating a House of Quality. The first step is to collect the voice of the customer information. Next is to develop a list of technical requirements, after which the team measures the technical values of competitor products. Next, the team calculates the priority of each technical requirement. The 5th step is to populate the correlation matrix, and the final step is to analyze the matrix and develop technical targets. For the rest of the topic, we'll focus on the first 3 steps in more detail. The first step in developing the House of Quality is to collect the voice of the customer information. This information is first listed in the House of Quality. Then, based on feedback from the customer, the importance is ranked so that the voice of the customer can be prioritized. Then a competitive assessment is performed to determine how the customer perceives the competitors versus your product or service. Now let's examine how the first step in developing the House of Quality would be developed. For this example, consider a company that manufactures dental surgical supplies. Their customer research shows that their customers are looking for pliers that have several characteristics. These characteristics include that the teeth on the pliers must not strip, the handle must not break, the metal must not rust or tarnish, the metal must be shiny, and the handle must be insulated against electrical shock. So this information is placed in the matrix as the voice of the customer. The next step is to determine the customer importance. The customer research also implies the importance rating for each characteristic. Higher values indicate greater importance. In this example, the teeth of the pliers not stripping and the handle being insulated against electrical shock are the 2 most important characteristics for the customers. Therefore, they're both assigned a value of 4. In the next step of developing the House of Quality, we're still focusing on addressing the voice of the customer. But now you want to move to the right-hand side of the House of Quality, the Customer Competitive Perceptions Matrix. It is important that you understand and identify the customer perceptions of your competing products. If you consider the example of a manufacturer of dental surgical supplies, your customer ratings for the quality requirements are compared against two successful competitor products that were acquired. These were Product A and Product B. The ratings are given from 1 to 5, and they're entered into the matrix for the customer perceptions component. In the ratings, 1 is good and 5 is bad, so a lower number indicates better performance. This is important before you go through and start developing your technical requirements, because this is a good time to understand how the product you are developing is perceived based on your competitors. This is where you can learn where you need to improve your product or service to better meet market expectations. The next step in the process of developing your house of quality is to develop a list of technical requirements. At this point, you've gathered the voice of the customer. Now, the quality function deployment team needs to develop a list of technical design requirements that are needed to make sure you fulfill each customer need. It's important to know that there are two key parts to this step. The first is to identify the technical requirements, and the second is to examine the relationship between the technical requirements and the customer requirements in the interrelationship matrix. Now, if you go back to the example of the dental surgical supplier, the engineering members of the company's quality function deployment team have developed a list of technical requirements to ensure they fulfilled each customer requirement. These are entered on the vertical axis and include Rockwell hardness, chromium content, surface finish, rubber thickness, and carbon content, among other technical requirements. As you develop the technical requirements, you also need to set the direction of improvement. Once the list of technical requirements is entered into the house of quality, the team needs to go through and identify the direction of improvement. A direction can be an up arrow that indicates a higher value is better to satisfy the customer requirements. A down arrow can be used to indicate that a value should be as low as possible, or a 0 can be used to indicate that a specific target is required. The interrelationship matrix is where the team brainstorms the interrelationships between the customer requirements of the voice of the customer and the technical requirements. This is in the center of the house of quality. The interrelationship matrix is populated with symbols that indicate whether relationships are strong, medium, or weak. It helps to show the design team's perception of the relationships that exist between the customer requirements and the technical requirements. This is important because you want to make sure that each voice of the customer requirement is addressed by a technical requirement. Otherwise, you've missed the customer's expectations. You can use relationships to make sure there's a strong relationship between each customer requirement and at least one of the technical requirements exists. Now let's consider that manufacturer of dental surgical supplies to discuss how to complete the interrelationship matrix. You would start by determining what the relationships are in the interrelationship matrix, and then you would go back and consider your customer requirements. If you consider the customer requirement of not strip, the customer requirement is that the pliers do not strip. It's strongly related to Rockwell hardness, vanadium content, and carbon content. The chromium content has a medium relationship with the customer requirement for stripping. If you consider the customer requirement of not break, carbon content and Rockwell hardness both have a strong relationship to the requirement that the pliers do not break. And the molybdenum content shows a medium relationship. Sulfur content reduces toughness, so it has a negative relationship. If you move to the next customer requirement, not rust, this is a customer requirement that the pliers resist rust. It's strongly supported by the molybdenum, chromium, and nickel content. The surface finish and sulfur content have a medium effect on corrosion, while carbon content has a negative effect on corrosion protection. The next requirement is be shiny. When you consider this one, shine is strongly related to the surface finish, with a medium relationship to the vanadium content and a weak relationship to the chromium content. And the final requirement is that it is shockproof. The plier's electroconductivity is strongly related to the rubber thickness of the handles, and it has a negative relationship to the nickel content. The next step in the interrelationship matrix is to replace the symbols that we've used for the relationships with the actual numbers that represent their relative relationship strength. It's important here that the team decides on the weighting system that they're going to use. In this example, we're using 0 for negative, 3 for weak, 5 for medium, and 9 for strong. Other commonly used weighting systems are 1 for weak, 3 for medium, and 9 for strong. It's important for the team to determine what weighting method they're going to use because this can amplify the importance and urgency based on the different types of weighting systems. So now the team changes the relationships from the symbols to the actual numbers. Note that, while you still have several blank spaces, those blank spaces mean there's no relationship between the customer requirement and a technical requirement. Once a team completes the interrelationships, then they need to go back and interpret those relationships to recognize certain patterns. For example, a blank column indicates you might have an unnecessary technical requirement. If a column is blank, the technical requirement is not addressing any of the customer requirements, which means it might be unnecessary. Blank or weak rows are an indicator that a customer requirement has not been addressed by a technical requirement. In addition, if you have a row with a weak relationship to the technical requirements, that might mean you have not adequately addressed that customer requirement. If you have identically weighted rows, that means you can have two customer requirements that have been addressed the same way. You should consider either combining the two requirements or going back and making sure you truly understand what those customer requirements are, because they're related to the same technical requirements. You might have these two slightly confused, or those customer requirements are not clear enough. A strong diagonal pattern is created in response to the customer requirements, but it's not something you would expect. The technical requirements are brainstormed ideas, and a strong diagonal pattern indicates that each customer requirement was directly related to one technical requirement. If you have a complete row, it's another indicator that the customer requirement has a strong relationship to the technical requirements. This could be a sign that the customer requirement is costly, because it's linked to so many of the technical requirements, and therefore it needs to be tightly controlled. If the customer requirement does not meet the technical specifications, this might also lead to a safety issue. In addition, if you have a complete column or a nearly complete column, this is an indicator that the technical requirements has a strong relationship to all or most of the customer requirements. This technical requirement is important then because it's linked to so many of the customer requirements. That means it needs to be tightly controlled, because if that aspect of the system, the product, or the process you're designing fails, then it's going to greatly impact most of your customer requirements. In this topic, we're going to focus on the third and fourth steps of developing the House of Quality, determining the technical values of your competitor products, and calculating the priority of each technical requirement. When you talk about the competitive values of your competitor products and previous products, you're going to use them as a benchmark for comparing the value of technical requirements. For each technical requirement that was identified, the team sets quantifiable measurements for their competitors and any previous product versions. These measurements help to highlight areas in the product or service being developed to ensure the right improvement is targeted. It also highlights areas of the design that are already considered best in class. Now let's return to the manufacturer of dental surgical supplies to review how technical values of competitor products are developed. For this manufacturer, the team runs reverse engineering tests on the competitor products against technical requirements that were developed by the QFD team. Now, normally, the customer perception part and the competitor's analysis would come from sales and marketing feedback and competitive intelligence activities. But sometimes it's important to have a deeper, more technical engineering analysis of competitor products and services. This is performed by technical experts, engineers, and research and development teams within the company, in conjunction with the activities of sales and marketing and company management. And it helps the team develop quantifiable metrics and estimates. The information is then entered into the competitive benchmarks component of the House of Quality for each of the technical requirements, based on each of the competitor products. So how is priority for each technical requirement calculated? The QFD first calculates the absolute technical priority of each technical requirement. If you consider the first technical requirement of Rockwell hardness, you begin by multiplying the prioritized requirement by the value of the interrelationship matrix. So for Rockwell hardness, you begin by multiplying 4 times 9, which equals 36. You then multiply 3 by 9, which gives us 27. The next three requirements, not rust, be shiny, and be shockproof, do not have a relationship, so those values are multiplied by 0. Then you would add up each of these values to calculate your absolute technical priority. 36 plus 27 plus 0 plus 0 plus 0 equals 63. Then, based on the highest number, you're able to prioritize your requirements. The next step in reviewing technical requirements and prioritizing them is to convert the absolute technical requirements into relative rankings. This is based on each value and how each of the different technical requirements rank relative to each other. The next step is to determine the technical difficulty. This is where the engineers involved in developing the product allocate a rank of technical difficulty based on how difficult it will be to implement each of the technical requirements. In this topic, we're going to focus on the 5th and 6th steps of creating a house of quality matrix, populating the technical correlation matrix, and analyzing the matrix to develop technical targets. The 5th step is to populate the technical correlation matrix. This is also known as the roof of the house of quality, and it's where the quality function deployment team works with engineers to populate the technical correlation matrix with positive or negative symbols, which represent the relationship between the technical requirements. It helps to have this information because you might have to make trade-offs between different technical requirements based on how they relate to each other. Let's go back to that manufacturer of dental surgical supplies and consider how they populate the technical correlation matrix. If you go to the roof of the house of quality, the chromium content has a positive relationship with the surface finish and nickel content. It also has a negative relationship with carbon content. Meanwhile, the Rockwell hardness has a negative relationship with the sulfur content and a positive relationship with the carbon content. And finally, the carbon and nickel content have a negative relationship with each other. All of these relationships are indicated by the pluses or minuses in the roof of the house of quality. The 6th step in developing the house of quality is to develop the technical targets for each of the technical requirements. The values are developed based on the technical experience, importance, difficulty, and competitor values for each of the requirements. If your technical requirements have conflicting customer requirements, this is where the tools such as Design of Experiments, or DOE, could be used to create targets for those technical requirements. With technical requirements, the values that have the highest technical importance or difficulty are selected for further analysis in the new matrix. This is where the team uses a matrix to determine those technical values for the technical requirements, and to identify the areas that require further improvement. Now let's go return to the manufacturer of dental surgical supplies to see how their QFD team analyzed the matrix to develop technical targets. The engineering team worked with the quality function deployment team to understand the relationships between the technical requirements and to make sure that these were addressed in setting the technical targets. When the team started looking at the relationships between each of the requirements, they decided to increase the carbon content relative to the chromium content in order to strengthen the tool. They did this despite the negative effect on the carbon on the corrosion protection, but they were able to do it because sulfur is present in the tool, which helps prevent corrosion, despite its effects on the required Rockwell hardness. By having the cross-functional QFD team working closely with engineering, they could address the different trade-offs between each of the technical requirements to make sure they develop the best possible products and set the most appropriate technical targets. Project management involves the planning, organizing, and motivating of different resources that are involved in accomplishing a specific task or working toward a common project goal. With Six Sigma, there are various types of projects, but each of these projects typically includes a team of 6 to 8 people. These projects can range from something within a specific department to projects that involve multiple departments. Six Sigma projects typically last between 4 to 6 months. Therefore, it's important to tie in project management aspects to Six Sigma, because you have varying types of projects that might take into account different departments, and you may also have multiple team members that are involved. So it's a fairly large project, and you need to make sure it stays on track and that you're meeting your deliverables and deadlines. The project charter is a tool that's used in the define phase of the DMAIC methodology to give the team and the organization an idea of what's involved in the project. There are several key elements of the project charter: the business case, problem statement, project scope, goal statement, key deliverables, required resources, and roles and responsibilities. The project charter helps the team establish what the team should be working toward, and it also gives everyone on the team a common understanding of the focus of that project. One of the first aspects of the project charter is the business case. This is where the team provides the rationale for the project. This is also where the value that this project has on the organization should be clearly delineated. You're trying to answer the question, why should you do this project? For example, a business case statement could be increasing our average sales per order by 8 to 10% will increase our gross revenues to a level at which we will be a clear market leader in the online automarket sales. The purpose of the problem statement is to describe the problem that you're trying to solve and also the impact that this problem has on your business. For example, a problem statement could be customer returns of our alkaline batteries at retail stores are well above the industry average of 0.5%, resulting in a direct loss of $350,000 and an indirect loss amounting to $500,000 per year. The next aspect of the project charter is the project scope. The project scope helps to provide a baseline of what should be included in your project and what should not be included in your project. It helps to set the stakeholder expectations of what exactly the project is focusing on and where they will see improvements. It also helps to answer certain questions, such as what processes are you addressing and at what level. And it also addresses what is not included in the project. For example, a project scope statement could be, the project will focus on help desk operations at the company's Toronto facility. The project team will review inbound customer support processes at all levels over the month of July to determine ways to reduce customer wait time. Hardware and software infrastructure and staffing schedules will not be examined. The next aspect of the project charter is the goal statement. This is where the team describes the anticipated results from the project improvement efforts. This is also where the team can outline the quality focus and really highlight what improvements from the quality aspect the team is trying to make. The goal statement answers questions such as, what results do you anticipate from completing this project? How will you measure the results? So, for example, the goal statement could be, the goal is to reduce the average cycle time to 5 days by March 30th. The project charter also includes key deliverables. These key deliverables help to provide the roadmap for the team and give an estimation of completion dates so that the team can see if they're on track or not. The roadmap and deliverables are typically aligned with the project phases, including define, measure, analyze, improve, and control. So you want to make sure that any of the key deliverables within those phases are also included on these deliverables with estimated completion dates. Doing this will help the team answer, what are the key activities, and when should those key activities take place? The next aspect of the project charter is including the team. It's important to address the resource roles and responsibilities that are required with your Lean Six Sigma project. When you provide a list of the team members, you should also include their roles and responsibilities, so everyone has a clear understanding of where they fit within the team. It's also important to include information on what the reporting relationship structure should be. The purpose of including the team members and their roles and responsibilities is to answer a few questions. First, you want to know who will be doing the work, and also which person is assigned to which tasks. And finally, you need to know who they will report that information to. In this topic, we're going to talk about project problem statements. The purpose of the problem statement in the project charter is to help describe the problem that the team is trying to solve. So it should reflect why the team is using continuous improvement and quality methodologies, and also describe the impact this problem has on the business. Providing this information to the team will help set meaningful goals for their process improvement efforts and focus their efforts on working on the right things. The problem statement helps answer a few questions for the team. It addresses how big the problem is, how it's being measured, and what it impacts. Let's examine an example of a problem statement. Our problem statement is, our current cycle time for order delivery is 8.6 days. This falls short of the customer requirement of 5 days. This shortfall has resulted in the loss of customers and $1.5 million in lost revenues every year. The key information that's included here provides quantifiable information stating that the cycle time is 8.6 days, how this falls short of the requirement of 5 days, and what the impact has on the business, which is the loss of customers and a loss of revenue. The purpose of your problem statement is to provide clear and concise information about the current business and the current situation. It should include quantifiable information about the problem itself and its impact on your customers. It's important that you also pay attention to what the problem statement should not do. The problem statement should not state an opinion about what's wrong. It should be based on quantifiable information. The problem statement should also not describe the cause of the problem. When you go through a Lean Six Sigma project, you want to make sure that you're using root cause analysis to drive down to the true cause of the problem. And you want to avoid leading people in one direction at the start of the project. It's also important that the problem statement should not describe broad issues. You want to be as specific as possible so that you get the team focusing on the same issues together. The problem statement should also not place any blame or responsibility for the problem. This goes back to Deming's philosophy that there are no bad people, there are only bad processes. You need to focus on improving the process and not placing blame. And finally, you need to make sure that the problem statement does not appear to be prescribing a solution. You want the team to go through the Lean Six Sigma methodology to determine the root causes, and then use this information to determine the most appropriate solutions. Now, let's consider an example to explore how you can define a problem statement to provide more information for the team. Before, the problem statement was that the average on-time delivery rate is falling short of customer expectations. That doesn't really give you much detail in terms of how much you're falling short, or what your current delivery rate is. You can take that information, which is fairly vague, and you can use it to further refine your problem statement to the following. We currently have an on-time delivery average of 65% for product A and 75% for product B, which falls short of our customer expectations of 100%. This provides much more specific information in terms of what the products are, where you're falling short of customer expectations, and by how much. The definition of the project scope within Six Sigma is the work that needs to be performed to fulfill the project's objectives. The purpose of the project scope is to let the team know exactly what is required and what is not required. It also provides the team with information on what areas and what levels in the organization the project expands to. This is basically the boundary around the project, so you know specifically what processes are included, what aspects of the project are included, and what are not. This will help the team focus on where they should prioritize their efforts. Scope creep happens when you start moving outside of the processes that you've targeted. Let's consider a Six Sigma project where you specify that the scope of the project includes a certain set of steps. What happens sometimes within Six Sigma is that you can start finding other areas that would be nice to work on, or things start expanding because you don't really understand what the project focus is. This is called scope creep. You need to be very careful when you start adding in additional deliverables or requirements or additional process steps. This lengthens the time it's going to take for your project to be completed. and it also adds in extra steps that may not be related to the process that you're working on. So this adds extra ambiguity to your process improvement efforts. There are two main causes that lead to scope creep. The first is that the team tackles a bigger issue than what they actually planned for, maybe as a result of not having an appropriate problem statement. As the team starts getting into the project itself, it can become a bigger issue. This is where the team needs to take a step back and see if the project should be split into two separate projects. The second cause is when the project champion expects too much. The project champion may not have a good understanding of what's really involved within the project and is expecting more deliverables. So it's important at this point for the project champion and the project team to go back to the project charter and look at the goals and objectives to come to a common agreement. Lean Six Sigma projects need to have the appropriate scope. You don't want your scope to be too narrow or too broad. When the scope is too narrow, you're typically looking at a subset of the process instead of looking at a wider range of the process. When that happens, you won't achieve the desired improvement goals because you will only be improving a small section of that process. In addition, since you're not looking at the breadth of the process that you need to, you may miss the root cause because it could be outside of that scope. On the other hand, if your scope is too broad, you might miss the root cause because you're trying to take in too much information, which doesn't really help you understand what the true root cause is. This could also impact your project completion because you're trying to improve too much at one time, so it will take longer. In addition, when you're trying to look at a process that's scoped out too broadly, this can overwhelm and frustrate the project team, because it will be more difficult to find root causes and understand every step of the process completely. There are 4 key management tools that are helpful in defining a project scope. The first are process maps. Process maps help you go step by step through each of the steps that are involved in the process that's under consideration. Doing this helps the team figure out the appropriate boundaries for the project. The second are Pareto charts. These are helpful because you can focus on the most important areas within your process or project that's under consideration. SIPOC diagrams, or suppliers, inputs, process, outputs, and customer diagrams, are useful because they document the process starting with the supplier all the way to the customer. So you can use this information to scope out your project by taking this information into consideration. Finally, the fourth management tool for your scope is the voice of the customer. It's useful because when you understand exactly what the customer is looking for in terms of process improvement, then you can use that information to scope the appropriate aspect of the process that's impacting those customer requirements. In this topic, we're going to talk about some of the aspects of a well-scoped project. First, the project scope should address the source of the problem, and it should focus only on one problem. If you're trying to focus on more than one problem, then you should deal with each problem in separate projects. Projects should also have achievable objectives. It needs to be realistic and not too broad. You want to make sure that you're setting the team up for success, but also make sure that they are aggressive and achievable goals. The project should also be scoped in a way that it's budgeted properly in terms of time, money, resources, and capability. Again, you need to make sure that you're providing these necessary resources so that the project can be accomplished and the team can be successful. And finally, a well-scoped project has consistent input from stakeholders. You need to make sure that you have frequent communication and feedback from your stakeholders, so you're able to meet the expectations and needs of your customers and your stakeholders. When you define your project scope, it's important that you think about your customers and try to understand their mindset. You need to understand what they see as value from your products and services. The key question you should ask yourself when defining your scope is, what will create the most value for our customers and stakeholders? This is where you can focus in on the area and determine the appropriate boundaries to scope your project. There are a few scoping best practices you should follow. The first is to look at other projects and determine if there is an impact that the project might have on your project. This will help make sure that there's no overlap or waste because there might be other projects that are already addressing items that you've included in your project scope. The second best practice is to set clear objectives. You do this by communicating frequently with your stakeholders and everyone that is involved in the team about the expectations, deliverables, and timelines. Another key area to focus on are the financial aspects. Your project goal should be achievable within the allocated financial resources. If it looks like your project is going to run over budget, then you may have scoped it too broadly. It's also important to try to prevent your project from crossing boundaries. When planning a project, you might encounter additional issues that could be addressed in associated projects. It's a good idea to establish procedures to track the different child projects to make sure that you're preventing your current project from overlapping with them. In addition, you need to be time conscious. Your project should have start and end points, and your project goal should be achievable within the available time. Any project overruns could be a sign that you've had an incorrect scoping of your project. And finally, it's important to write a precise and concise scope statement. Your scope statement should set out specifically what the project is expected to work on, and more importantly, what it should not be working on to avoid scope creep. Now, let's look at an example of implementing these best practices to scope your project. This example deals with a loan application process. After meeting with the champions of the other project teams, the team was able to discover that a separate project is already being performed that addresses loan transfer issues. Therefore, the team decides that they should remove this from their project scope. In addition, the project team leader has a set of very specific project definition, which includes deliverables, timelines, and clear expectations for the loan application project. The team also identified 2 potential side projects in scheduling and data input areas. These are going to be dealt with by other project teams, so this helps the team ensure that they don't cross over project boundaries with these other projects. The team is also conscious of the time and financial constraints that they have to work with, and they're making sure that they're scoping their project accordingly. The project needs to be completed by March 30th, within budget. Finally, the team's scope statement specifically details the processes covered by the project. It's the entire loan process, which begins with a call from the customer and ends with the acceptance or rejection letter being sent to the customer. In this topic, we're going to explore process maps. Process map is a way to help organizations understand the flow of information or products or processes. It's useful because it shows us information in a graphical form so that everyone can understand each of the steps in a process. The process map shows how the inputs, the outputs, and the tasks are all linked together. Within Six Sigma, process maps are useful in scoping your processes. So, for example, a project manager can use a process map to explain the project scope in a way that a wide variety of people can understand, and also show what needs to happen within this process and what the process boundaries are. The process map will display the steps of the process, the various inputs and outputs, and how everything is linked together, and it also has a clear start and stop to the process. There are several purposes for using a process map. The first is to identify any disconnected steps that you might have in a process, as the process map shows the linkages between each step in your process. You can also use the process map to identify and clarify any responsibilities and relationships by going through each step of the process to see who the owner is and how this step relates to other steps in the process. The process map is also useful for identifying non-value-added activities. You can go through each step of the process and determine if that step adds value to the customer or if it does not. Another purpose is to isolate process bottlenecks so you can understand where there is an interruption of the flow and where you're building up a queue of work in a process. This will help you discover opportunities for improvement by understanding where there is waste in your process and where there are bottlenecks or where you have disconnections. Then, based on your opportunities for improvement, you will be able to determine the corrective actions you should perform to maintain and enhance your system quality. In drawing a process map, there are several shapes that are generally acceptable to denote certain aspects of the process. So let's examine a very simplified version of a partial process for a product return. You start the map with an oval. This step represents the customer returning a product. You also want to end the map with an oval to mark the final step in the process. But again, here you're exploring a simplified version of the process. A circle is used for any activity that requires cooperation, and also for inspection points. In this step of the process, a team stops to assess the reason for the product rejection. Diamonds are used to show decision points in the process. At this point of the process, a team decides whether to accept or reject the customer's reason for returning the product. Then, finally, squares or rectangles are used to represent a particular step or activity in the process. In this case, depending on the outcome of your decision, whether or not you accept or reject it, the team will either return the product to the customer or rework the product. Another dimension that can be added to process maps is the concept of swim lanes. Swim lanes are horizontal bands that are added on top of the process map to show who has responsibility for each of the steps. You can use these in Six Sigma to help define the scope of your project by defining the stop and end points of processes, but they can also help show where you're crossing over different departmental or functional boundaries. The map of this example shows client, sales, and production. All of the client's activities are in the horizontal band or swim lane at the top of the map, so each of these steps are associated with the client. Then, all of the sales activities are in the center of the swim lane, right in the middle band. Finally, all the production team activities are aligned with a bottom row. This again helps to understand the boundaries of our process, ownership, and when you're crossing over different functional or department areas. Let's explore a useful tool for scoping your projects, the Pareto chart. The Pareto chart is a special type of bar chart where the values are plotted in descending order, and it's based off the Pareto principle, or the 80-20 concept. That is, that 80% of the effects come from 20% of the causes. For example, you could say that 80% of the value of your company's inventory comes from 20% of its stock, or that 80% of the failures in a system come from 20% of the defects. The Pareto principle is a reliable way to identify the sources within a process that create a disproportionate number of defects. Within Six Sigma and process improvement, these are known as the vital few sources of the area that you're trying to improve. The Pareto chart is useful for analyzing non-numerical data, such as the cause of a problem. With Six Sigma, you can use the Pareto chart and the 80-20 principle to determine what those vital few aspects or causes are, and then scope your project so that you're focusing in on these key areas. The Pareto chart is especially useful when, as a team, you're trying to identify factors that could be the most important for your project. These are those factors that are the vital few areas that have the greatest cumulative effect on your system. This helps your team discern value, or in other words, what's important and what's not important. Pareto charts are useful for categorizing problems. You can look at the problem from a business perspective, a product or a service, and categorize the problem that way. For example, Pareto charts are useful when you're trying to prioritize problems to determine which ones have the greatest impact. Then, based on that information, you can prioritize to determine which needs to be addressed first. Pareto charts can also be used to assess system changes by conducting a before and after comparison, or when you're analyzing data about the frequency of a problem. Finally, Pareto charts are useful when you're examining particular items within a broad analysis. Now let's examine the first two steps in creating a Pareto chart. The first step is to list all of the causes of the defects in descending order. You do this by categorizing the problems and counting the frequencies of each of those defects in the category. In the second step, you calculate the cumulative percentage of defects. For this, you start by determining the sum of all of the defects from all of the different causes. In this example, there are 3 different causes that create the defect. The first cause has 50 defects, the second has 30, and the third accounts for 10 of the defects. Therefore, the total sum of the defects is 90. The second part of step 2 is to find the percentage of defects that each cause contributes to the total number of defects. This is calculated by dividing the number of defects per cause by the sum. The first cause of errors accounted for 50 defects out of 90. Therefore, you would divide 50 by 90, and the result is 0.56, or 56%. You can perform the same calculation for the remaining 2 causes. The second cause contributes to 33% of the total defects, and the third cause contributes to 11% of the defects. The final part of step 2 is to accumulate the contributions of each cause, and you do this one by one. You start with 0% of the defects and then add in the contribution of each cause of the defect, starting with the most frequent cause. Since cause 1 had 50 errors, the cumulative percentage at this point is 56%. Cause 2 contributed 33% of the causes, so now you add 56 plus 33, and the cumulative percentage is 89. Then you add in cause 3, which was 11%. This brings the cumulative percentage to 100%. The last cause of the defect should always bring your cumulative percentage up to 100%. The third step in the process is to start building the actual Pareto chart. The first part of this is to add the axis and the numerical scale. If you go through and look at the scale, the first axis includes the number of defects. You want to make sure that your axis here will cover up to the highest number of defects that you have for each category. Then, in the second axis, you have the percentage. That ties into the cumulative percentage that you calculated previously. Then you would add bars and categories, in this case the defect categories, with the bars indicating how many defects you have for each category. The next step in creating the Pareto chart is to plot the cumulative frequency of defects. To do this, you start by drawing a scale on the right side of the chart, and that's going to be used to measure the cumulative percentage. Since it's a cumulative percentage, it should always run from 0 to 100%. The next step is to plot the data points to represent the cumulative percentage for each category. To do this, you need to make sure that you're aligning the data points with the right edge of the corresponding bars. Finally, you connect the points with the line, and this is known as the cumulative percentage line. The last step in creating a Pareto chart is to prioritize the vital few. There are two main methods within Pareto analysis to do this. The first is the fixed percent method. This is where you apply the 80% rule or the 80-20 rule. This is based on the philosophy that all defects that combine to cause 80% of the defects are the vital few. This is typically the most accurate methodology for determining what those vital few are. The second method is the change in slope method. This method uses a cumulative frequency line, and it's based on the philosophy that all causes to the left of the line break are the vital few. This methodology is the most visual of the two methods. So let's now examine two examples. With the fixed percentage method, you would find the point at 78.6, roughly 80%, and you would select the top two. With the change in slope method, you would also select the top two. As you work on your project charter and start to develop your own problem statement, and then move into goals and objectives, it's important that you understand what your project metrics are. Project metrics essentially tell you what you need to measure in your project. This should be something that's quantitative and important to the customer. So these metrics should relate back to the voice of the customer that you've gathered. At this point, you need to also understand how you're going to measure. You could use some tool such as a process flow diagram to determine where you should measure it. Metrics are important because you're going to use them to measure the progress of your continuous improvement efforts and then compare that progress against your final results to make sure that you're on target with your expectations. Metrics are also important because they help you identify problems within your processes and where you're falling short of meeting your goals. Then you can use this information to drive toward your root cause analysis. Now let's take a project that's focused on reducing customer order to delivery cycle time. The project has 3 project requirements. Let's explore how you can develop the appropriate corresponding metrics. The first requirement is to reduce the order to delivery time. The metric here could be cycle time, since it's a measure of time. The second requirement is to have correct customer addresses. So the metric here could be customer address errors. The third requirement is to streamline the process. So you could use lead time or value added time as your metric. It's important to note that when you have a requirement and you're developing metrics, each of the metrics needs to be quantitative and relate directly back to the specific requirement. In other words, there should be a clear linkage between the requirement and the metric. There are 2 types of metrics. The first are primary metrics. These are the metrics that could be directly observed, influenced, or changed. So this is something where you're going to actually get a reading, and you have quantitative data that's based on what you're changing or what you're observing. The primary metrics also directly relate to the project goal. There's a clear linkage between what you're measuring and what the project goal is. There are also tangible and objective results, which help to provide proof that there's been a change in the system or the project or the process. The second type of metrics are secondary metrics. These are metrics that influence the primary metrics. However, these are metrics you cannot directly measure yourself. They're used to track trends or other intangible aspects of a process or change. And since you don't have direct observation to measure this metric, you're going to have to use circumstantial evidence. Now, let's examine some primary metrics and secondary metrics. If you're trying to reduce the cycle time that it takes to order a product through your online retail store, the primary metric would be the order cycle time. Also, if you're trying to increase the traffic through your online store, you could use a primary metric such as the number of website visits. A secondary metric when you're talking about your online retail store could be the number of back orders. It is not directly related to your cycle time, but it would give you information that's related to cycle time. Also, in terms of trying to increase the number of customers that are visiting your online store, a secondary metric could be the customer satisfaction ratings, because this would be an indicator of customers that are satisfied with their delivery time. It's not a direct measure, so you would want to focus more on those primary metrics, because those are more related to your project goals. Let's explore a few other examples of primary and related secondary metrics. A primary metric could be returns or scraps, number of complaints, defects, and delivery time. Now let's consider their corresponding secondary metric. If you're looking at returns or scraps and trying to reduce your external defects, a secondary metric that you could use to address this is production costs. If you're looking at a primary metric of customer complaints and you're trying to improve customer satisfaction and reduce the number of complaints, a secondary metric could be your customer satisfaction scores. When you look at defects, you're trying to reduce the number of defects. So secondary metrics you could use include cost, customer satisfaction scores, or revenue. And if you're trying to improve your delivery lead time, the corresponding secondary metric could be cost, waste, or process steps. There is a third type of metric known as consequential metrics. These are the negative side effects that might result from making the planned improvements. For example, your primary metric might be that you have a higher input cost, or could be addressed by selecting a cheaper vendor. But then you might run the risk of reliability and quality issues. This would lead to consequential metrics such as an increased inventory, increased scrap, or increased defects in the final products. So it's important that you pay attention to these consequential metrics to ensure that you're realizing the overall gains from your improvement project. When you're developing the metrics for your projects, it's important to make sure that you look at all the requirements and then go back and look at the voice of the customer. There needs to be a clear linkage between what you're measuring and what you're trying to improve for the customer. For example, if you're trying to create a door, you should be asking several questions. You should start by asking what must fit through the door. What clearance is needed? Is the door meant to allow or deny easy access? Who will be using the door? What is the size and the ability of the person? And does the door require a lock or window? These should all be questions that you should be able to answer based on the voice of the customer and their key requirements. Project management and project planning are important in a Six Sigma project because they help you plan and monitor your projects. Planning tools are important especially at the early project planning phase because they can help you identify the activities that will be necessary to accomplish your final goal. They also help you to schedule appropriate activities to make sure that you're on target. Planning tools are also used during the project to help monitor the progress of your process improvement project and also detect where actuals vary from your planned values, so you can see where you're running behind or ahead of the projected target schedule. A Gantt chart is one of the tools that's used throughout the project to help you with planning and tracking your progress, and also controlling your performance. A Gantt chart lists each individual task and then provides a duration for each of those tasks. It lists the information based on how long the task will take, and it also shows the relationships or dependencies where one task must be completed before another task. You can also use this information to then monitor your progress based on a given date to see if you're on track or behind schedule. There are two additional planning tools that are used to help plan and monitor projects. The first is the Program Evaluation and Review Technique, also known as PERT. The PERT methodology analyzes and represents all of the tasks that are involved in a project and the time needed for each task. The goal here is to look at what is the minimum overall time. The Critical Path Method, or CPM, also looks at all of the activities that are required in the project, the time required for each task, and any dependencies within each step of the process. The difference between these two methods is that the CPM chart looks for the longest path and uses it to determine what is critical. The critical path is the sequence of activities with the longest duration. Planning tools are very useful for reporting the project status and performance to stakeholders. One of the key aspects of these planning tools is their graphical nature, which helps to simplify the reporting and gives the project status at a glance. Anyone that's involved with the project can clearly see the current status. In addition, if there are any issues where the project team is running ahead or behind, these variances are clearly marked on the project planning tools. Another useful aspect is that they can easily be emailed, uploaded, or shared. There are quite a few project management software tools available that make reporting within these tools very simple. You can easily create and share reports, which helps considerably with improving the communication within the team. One of the most commonly used project management tools for tracking and monitoring progress in a project is the Gantt chart. The Gantt chart was developed by Henry Gantt in 1910. It's a time-scaled activity list that includes different activities required in a project and the length of time it takes for each step of the process. It's a very easy to maintain chart. One of the key aspects of the Gantt chart is that it provides a very clear picture of the current status, because you can see what the different activities are, where they should be occurring, and if you're ahead or behind schedule. This helps the team develop those what-if scenarios. What if you're able to get this done ahead of time? Or what if it takes longer than you expected? That way the team can see the impact on the entire project. Most Gantt charts are created in project management software, and the information is presented in a table-like format. The Gantt chart provides specific information, such as task names and durations. For example, on the Gantt chart displayed, task A-1 has a duration of 3 days. Other information that's typically included are the resources that are required, and for each task, there is a taskbar. In the example, task A-1 should last 3 days, and according to the chart, the task has been completed. The bar is filled in to show the amount of work that's been completed on that task. There's also information on dependencies. From the example, you can see that task B-1 is dependent on task A-2 being complete. There's also a red dotted line that shows the current status. This would be the current date, and anything to the left of that line should represent what has been completed by this time, and anything to the right of that line is what still needs to be completed. As work is being carried out, the Gantt chart is updated with the actual finish dates. In addition, some Gantt charts show the percentage that's been completed for the activities that are in progress. You can also see this information based on each of the progress bars. For example, in the current example, task B2 should take 2 days to complete. The duration for B-2 is 2 days, but you can see that only part of it is filled in. This represents the work that's been done to date. This gives the team a good picture of what's been done and what still needs to be done and what the current status is. Let's explore how a Six Sigma team would use a Gantt chart and how they would interpret it. Let's start by considering all of the different tasks that are required for the Six Sigma project. In this example, tasks A through J are needed to install power to the new server. Alan and Inez have been assigned ownership for these tasks, and the duration for each of the tasks has been estimated. Using this information, you can tell the order in which these activities need to take place. You can also see project milestones, such as task I, where you've got a triangle indicating that it's one of the major milestones. In addition, you can look at the project and all of the task durations. This tells you how much time is required and the overall time it's going to take. So this project starts at 8 o'clock a.m. and will last until 4 o'clock p.m. It is also important to note where there is potential slack time within the process. In this example, there's some slack time in task D, around 45 minutes, which means the task ends before it's needed for the next task, task E. In project management, the critical path is defined as the longest task sequence from start to finish. It's important for Six Sigma project teams to understand the critical path, because these are the tasks that must be completed on time in order for the entire project to be completed on time. The critical path doesn't have any flexibility. Therefore, it's important that you make sure that the project always stays on time, because any critical task duration increase means that the project will be pushed out past the final completion date. Let's look at an example to see how a critical path is developed on a Gantt chart. First, pay attention to the activity bars. When you have overlapping activity bars, such as you do for B and C, these are tasks that can be done concurrently with others. They're not necessarily a critical task, but you have to go back and look to see which is the longest. On this chart, the critical path would be A, B, D, and F. Critical path analysis is useful because it provides teams with warning about delays that could potentially affect their project completion date. It also shows the shortest time that's required to complete the project, which is different than the critical path. Critical path analysis also helps to identify those activities that are critical to maintaining the schedule and the interrelationships and problem areas between the different tasks. There are 4 key steps to finding the critical path. The first is to break the project into specific activities that are required to complete the project. Once the team understands what activities are involved, they can arrange these activities into a logical sequence. This allows the team to see the relationships between the different activities, any dependencies between the different activities, and also any activities that could be done concurrently. Then, for each activity, the team should estimate the duration, how long it's going to take to accomplish that activity. Finally, the team plots a path from start to finish to determine what the critical path is. In an activity network diagram, each event or activity is represented by a symbol. This could be a square or a circle, and each step, each activity, is also given a letter or number as a designation. Each of the arrows connects a symbol and indicates the order of precedence of those activities that should be sequential. In addition, the duration of each activity is indicated in each circle, and to be included in the path, there must be an arrow that connects each activity. In this example, when you start with A, there are 2 paths to get to the final aspect, or step I, which is the finish. You could determine the critical path in the activity network diagram by determining the sequence of activities that takes the longest cumulative time. This is what's going to set the critical path and become the overall lead time for the project. So to determine the critical path, you add up all of the tasks for each path. The path that takes the longest time is the critical path. If you examine this system with 9 events, the first path would be A, B, E, F, H, and I, and that path equals 23 minutes. The second path is A, C, D, E, F, H, and I, and that path is 24 minutes. Therefore, since this path is the longest, it becomes the critical path for the project. In this topic, we'll explore a project planning tool called the Program Evaluation and Review Technique, otherwise known as PERT. The PERT technique uses charts to sequence different activities. Similar to the critical path method, it shows tasks, durations, and dependencies. These activities are time-scaled to indicate approximately how long each activity lasts. The PERT chart and CPM both follow the same steps and use network diagrams to plan and schedule individual activities necessary for a project. Even though they're both useful in determining the earliest and latest start and finish times for each activity, there are a few differences between the two. The CPM chart is more deterministic. It presents estimates of activity duration that are based on historical data or information, whereas the PERT chart is more probabilistic. It uses estimates based on uncertainty. Therefore, it typically uses ranges to represent the probability that an activity will fall into that range. On a PERT chart, each activity node provides information on the duration of that activity. In this example, the number on the left side of the top row is the earliest point at which the activity could start. The middle number is the duration, expressed in days, hours, minutes, or seconds, or really whatever is relevant to your project. And the right-hand side indicates the earliest point in which the activity could finish. Additional information is included in the bottom row of the activity node. So in this example, the number on the bottom row on the left side is the latest start point. The number in the middle is any available slack time for that activity. And finally, the number on the bottom row on the right side is the latest possible finish point. The activity nodes are then joined together by arrows, and these arrows indicate any dependencies between these specific activities. When developing the PERT chart, a key aspect of it are the time estimates. The team would develop this information to establish duration values. Typically, PERT charts are used on projects that are non-recurring or non-frequent, so you may not have sufficient historical data to determine exact values. Therefore, the PERT chart uses probabilistic estimates. You're trying to find the probability that the duration will fall within a specific range. PERT charts use 3-point estimates. The first is the pessimistic time, which is the maximum possible time that would be required to accomplish a task, assuming that everything goes wrong. The most probable time, or most likely duration, is the best estimate of time required to accomplish a task, assuming that everything proceeds as you would expect it to. And the optimistic time is the minimum time that would be required to accomplish a task, assuming that everything goes better than you would normally expect it to. Finally, there's a fourth time, which is the expected time. This is the best estimate of the time that will be required to accomplish a task, and accounts for things not always going as expected, but realizing that some things could go a little better. The expected duration in a PERT chart is calculated by adding the optimistic duration estimate and the most likely duration. The value of m is then multiplied by 4, because these are 4 times more likely to happen than the others. The pessimistic duration estimate is then added to this value, and then the result is divided by 6 to get the weighted average of the time estimates. Now, let's explore how you would calculate the expected duration to complete the design phase of a project. If there are no delays, the project will take no more than 6 weeks. However, based on past projects, the most probable estimate is 10 weeks, so you multiply that by 4. Then, considering all the things that could go really wrong, you determine the pessimistic estimate to be 18 weeks. The top-line formula gives you a value of 64 weeks. In order to get the weighted average, you then divide that amount by a value of 6. So the estimated duration of the project is 10.67 weeks. Strong documentation is an important aspect of Six Sigma. As you move forward with a project, you need to understand the changes that have occurred within the process so that team members in other departments can replicate the same changes. Documentation is also helpful to track specifically what those changes are and what their impact was. Different documents are used in Six Sigma projects. Base documents help you understand what's going on with the process. Your ongoing project lifecycle documents track what specifically has been done within the project, so they provide your project-related information. Good documentation provides numerous benefits within a Six Sigma project. First, it helps provide the common understanding of the goals and the objectives for your project. It can also help to manage the process because you can see what's been done and what still needs to be done. As you're making process improvements, the documentation contains evidence of compliance with certain standards that are required for your organization and for your processes, and it could also be used to trace the system path of the defects. Another key benefit of good documentation is that it helps to demonstrate due diligence, because you're showing what you've tried and what worked and what didn't work. Good documentation also shows all of the different possible paths of what the team has tried to implement for process improvement, and contains lessons learned for future projects. This helps other teams look at the process documentation for this project to determine what they could also implement within their areas, and what should be done differently to help improve the next project. When starting a Six Sigma project, the project managers need to determine what amount of documentation is appropriate based on what the project needs are. If you have too much documentation, this can create an overload from a bureaucratic standpoint, as you try to keep track of it all. You can also get buried in information as you try to figure out what you need. All this can lead team members to wasted time and wasted effort. On the other hand, if you have too little information, your project could be faced with scope creep, as you have to go further out and look for the information that you need. In turn, this can also lead to miscommunication and performance gaps, as the team may not understand or have clear documentation on where the project stands and where it needs to be. Too little documentation can also lead to duplication of effort, and finally to system failure, because you don't have all of the information that you need. It's important to strike a balance when it comes to having the right amount of documentation for a project. There are a few simple questions you can ask to determine if a document is necessary. The first is, does the document have a distinct purpose? Does it further the goals and objectives of the project or the organization as a whole? Is it valuable? And the final question is, does it support other documentation? There are 4 main document categories. The first is status reports. Status reports provide a glimpse of the health of the project and any plan versus performance criteria. In a status report, you're trying to identify potential problems, risks, or threats. The second document category is management reviews. These are typically from a higher level, system-level performance so that you can understand what is going on within the organization and get perspective for different improvement opportunities. These are typically conducted by higher-level senior management. The third category is budget reviews. This is where you analyze resource utilization and cost performance, and any deviation or risk based on these factors. Then the final document category is customer audits. This is where you determine whether you're conforming to the agreed-upon requirements with your customers and meeting your contractual obligations. By paying careful attention to this area, you can limit your exposure to any liability. Stakeholders also require timely information. Therefore, there are several key types of documents that stakeholders need. The first are progress reports and status updates. These could be with respect to schedule and budget. Stakeholders also need a current inventory list, cost variances, earned value reports, and change requests. Providing all of this documentation, it helps make sure that the stakeholders have the appropriate information that they need on a timely basis, and also helps ensure your team receives appropriate and timely feedback from the stakeholders. Throughout a process improvement project, it's important to document the necessary project steps and to communicate what's been happening within the project. One way to do this is with a storyboard. A storyboard is typically something that is represented either in a software program such as Microsoft PowerPoint, or is created in an actual physical display board. A storyboard presents different types of information throughout each phase of the project to further communicate what's been going on with the project, not only to the team, but to other people that might be involved with that aspect of the process as well. You could use the define, measure, analyze, improve, and control phases and their key aspects to show the story. When you look at the define phase, you could show the problem and goal statements, the business case, project schedule, and a SIPOC diagram. With the measure phase, you might want to start showing more of the information that's specific to the process, such as maps and Pareto diagrams. You could also include any data collection and then any graphical presentation of that data, and potentially fishbone diagrams. In the analyze phase, you've started to understand the key factors in your process. So here you could show information such as correlation charts or any of the theory testing that you're doing. In the improve phase, you're starting to make improvements based on those key variables. You could show information such as experimental designs, the payoff matrix, or how you're implementing solutions and what those roadmaps look like. And then finally, in the control phase, once you've made your improvements, you could show things such as information tracking, project results and performance, and any lessons learned that you might have. This provides good information to the team and anybody else that has been working on accomplishing the improvements. Throughout your Six Sigma projects, you're going to encounter several types of risks. Some of these risks could be technical, operational, financial, environmental, or issues that involve personnel or the process. As you move through your Six Sigma projects as a Six Sigma team, you need to understand what kind of risk could impact your project. Risk analysis involves identifying and assessing any risk factors that could impact your process or project. Once you've identified potential risk factors, you want to determine what their probability of occurrence is, because you can use that probability of reoccurrence to identify assets that you need to protect. If there's a high probability of reoccurrence, then you need to focus more on those areas to prevent them from happening. Risk analysis help identify the necessary and appropriate preventative measures based on what could go wrong, what the risk factor is, and its probability. This is where you balance the impact of the risk versus the cost of prevention. You want to make sure that you're taking appropriate, cost-effective measures to reduce the impact of the risk factors on your project. The risk register is a useful tool to record the risk that you've identified, and then also perform a risk analysis. It's important that you don't confuse the risk register with a failure mode and effect analysis, or FMEA. FMEA looks at the failure of a specific process, but the risk register records different factors that will affect the ability to meet the project or organizational goals. Let's explore a brief example to demonstrate the column headings you might find in a typical risk register. The register starts with a tracking number that uniquely identifies each recorded risk, and this helps the team reference and monitor that risk. Then you cross-reference this risk to other related risks in the work breakdown structure. This helps the team monitor each task that might be affected by that risk. The third column is the date that the risk was identified, or when it was added to the risk register. These first three columns help the team track each risk in its context throughout the entire project lifecycle. The next column contains a brief and concise description of the risk. Next, the cause of the risk should be added to the risk register. Next information is the expected impact of the risk on the project outcomes. This part of the register might be further divided so that you can detail the impact of each risk on specific project outcomes. The next aspect is the severity. This could also be considered the extent to which each risk could impact the project. You also include the likelihood of the risk occurring. You could use low, medium, or high to qualify the severity of the likelihood. The final column contains the responses that will be taken by the project manager or the team if the risk happens to occur. These responses may include accepting it as a risk if it's outside of the management team's control, or adjusting the project plan to lessen the impact of the risk on the project. Now let's examine a brief scenario to understand what risk analysis looks like in a Six Sigma project. In the current situation, the customer satisfaction rates are much lower than the company would like them to be. This is negatively impacting repeat business. Therefore, the goal of this project is to improve customer satisfaction while maintaining a planned fee increase. The team uncovers a risk that they need to interview frontline customer service representatives to examine current customer-facing processes. The purpose of a Six Sigma team performing a risk probability and impact assessment is to assign a combined probability impact rating for each of the risks identified in the project. The assessment is typically performed by a team that's made up of people that are familiar with the risk categories. These individuals should also have experience with recent similar projects or be responsible for planning and managing those specific project areas that might be impacted by the risk. In order to make sure that there are standard measures of probability and impact, the team should use a scale that's predefined, typically in the risk management plan, or one that's already available in the organization. This helps to make sure that everything is measured equally across all of the risks. The scales can either be ordinal, which are low, medium, or high, or cardinal, which is a scale that usually ranges 0 to 1. Most teams use the numeric scale because it's easier to calculate and quantify the scores using the numbers. The risk score is calculated by multiplying the likelihood that the risk will occur, which is the probability, times the effect on the project objectives, which is the impact. Therefore, the risk is equal to the probability times the impact. If you're using an ordinal scale, then the risk would be in terms of low, medium, or high. For example, the probability would be medium and the impact would be high. If you're using a cardinal scale, you're going to multiply the value of medium that the team ranked the risk as times the impact, which could be 0.9 in this case. A priority matrix can then be used to determine the overall priority based on the probability and impact scores. Let's consider an example. If the probability of the risk was medium and the impact was high, that means that the priority rating would be high. If you look at it from a numerical score, though, the probability might be 0.5, which is medium, and the impact might be 0.9, which is high. That gives a score of 0.45, which means that the overall priority should be high. Each project has a defined life cycle, and it's the project manager that's ultimately responsible for completing the project. The last stage of a project is the project closure. Project closure occurs when all of the defined project tasks have been completed. The customer's accepted all of the deliverables, and they've signed off with approval. Project closure also includes documenting the final outcomes of the project in terms of the output and the fulfillment of the customer requirements. The project closure also ensures that all of the stakeholders have reached an agreement on the fulfillment of the predetermined project specifications. In order to close the project manager has to perform several tasks. The first task is to make sure that all of the final products and services are delivered. In addition, the project results should be reported internally and to the customer, if appropriate. Also, any of the open project contracts should be closed at this point. Now that the project is closing, the project team should be released from this responsibility, and any open financial issues need to be finalized. In addition, the lessons learned from the project should be documented as a learning experience to make sure that other teams can benefit from this team's lessons. Finally, any ongoing documentation needs to be completed and finalized to close out the project. Before a project can officially be closed, it needs to go through a final review. In a Six Sigma project, the last phase is known as project validation. In this phase, the project activities and resulting benefits are reviewed and documented. At this point, you also need to perform an analysis of what went well and what went wrong, and why that happened. Project validation is a valuable learning tool used to ensure that you can repeat successes and avoid making the same mistakes in the future. This also leads you into determining improvement opportunities for future projects. So it's important to document those here. The closure is also completed using an official document. The final document of the project is typically called the project closure document. The project closure document is actually validated once you have the signatures of the key stakeholders. This allows the project to be formally terminated, as it marks the official end of the project. It also passes the responsibility for maintaining the process improvement to the customer or to the functional department within the organization. The affinity diagram is a way of organizing a large number of ideas based on their natural relationships. Typically, when a team does brainstorming, they come up with a large list of ideas. But that's not a natural way to organize them. This is where the affinity diagram comes into play. Affinity diagrams are typically done by a team. It's a silent process where each team member puts ideas on sticky notes, and then they move these different ideas around until they fall into categories. This is when natural relationships become evident. Affinity diagrams are very useful in several applications. First, they can be used in all stages of the DMAIC process, anytime there's a brainstorming activity to develop possible solutions or to start determining different causes or problems associated with the process. This is useful because it helps the team then organize these different ideas into categories. Affinity diagrams are particularly useful when organizing large volumes of data, where those common themes may not be as easy to see initially. This is where the team can move the different ideas around to form categories, so that these themes start becoming more prevalent. Using affinity diagrams can also help to sort out unclear or complex problems, especially when there are large volumes of ideas. This way, the team can work on developing what the common themes are. Affinity diagrams are also helpful in developing group consensus, because everyone in the team is involved in developing the affinity diagram. Also, based on the nature of the exercise, creating an affinity diagram helps to stimulate creativity and use right brain thinking. And finally, it helps the team look at what may be a familiar problem, but see it in a new way by taking the ideas that were brainstormed and grouping them together in categories. Affinity diagrams may be more appropriate or more useful than other tools. For instance, affinity diagrams start with details and then they work up. So you start with various ideas and then you build upon them to find common themes, rather than working down. Affinity diagrams are also very useful when the problem is not understood. It gives the team the opportunity to work together in a brainstorming session and come up with ideas. And finally, affinity diagrams make it easy for the team to see how the details relate to the whole and to each other, based on the different natural relationships they discover while grouping the ideas into different categories. So let's look at an example of an affinity diagram. Let's say a Six Sigma team at a retail bank is working on a project to address the variability in the loan processing time at various branches. The team decides to use the affinity diagram to organize a list of potential factors that affect the loan processing time and group them into categories. This team conducts a brainstorming session to come up with various ideas and places them on sticky notes. The team then moves the different sticky notes around, and they're able to develop specific categories. One of the major categories is loan-specific factors, and in that category, they group ideas such as the nature and category of loan applied for, the completeness of the application, whether it was done through the online or offline application, and the amount of the loan applied for by the customer. The team also finds that organizational factors are important for this project, so they create the category and group items such as the choice of processing partners and the availability of infrastructure and resources under it. Using the affinity diagram, the team was able to document all of the possible sources of variability around loan processing time, and then group them by common themes. This topic will explore some of the tips and best practices for getting started when your team is creating an affinity diagram, and how to actually create one. To begin, you should form a team of 4 to 7 members, preferably from various areas in your company. This cross-functional team will allow you to bring a wide variety of ideas to the table as you brainstorm and group the different ideas into categories. Another benefit of this cross-functional team is that you'll have a good balance of ideas, which will allow you to examine and resolve the problem from multiple perspectives. Team members who are working on creating an affinity diagram should have a few important qualities. First, each team member should have a basic understanding of the problem. Having team members aware of the problem at hand will help the team develop a list of relevant ideas and subsequently group them into categories to help solve the problem. Team members who are able to think outside the box are also a great asset to your team, because you want to have a solid brainstorming session to develop a comprehensive list of possible ideas, and then evaluate the problem from multiple perspectives. This will help ensure that you're creating the affinity diagram in a way that's going to be helpful to the team and to the project. The first step in creating the affinity diagram is to write down the problem statement. A good problem statement clearly defines the problem, and while you want to be as specific as possible, you also want to make sure that the way you write your problem statement isn't leading or confining. The team has to be able to understand the problem, but they also need to think freely about what you're trying to solve. So let's explore an example. A Greenbelt is working on a Six Sigma project with the design department of a crystal figurine manufacturer. The team is trying to create a new product line, and as they start creating the affinity diagram, they come up with the problem statement, "We need to improve the product design process." As the team moves forward, their next step is to create the affinity diagram with the goal of developing ideas for improving the product design process. The team starts brainstorming ideas, writing them down on sticky notes, and then randomly placing them up on a board. Several of the ideas include things such as do a failure mode and effect analysis, and do a process analysis using SIPOC. At this point, the ideas are just placed on the board in no particular order. The next step of the process is to sort the ideas into groups. The team does this by placing the ideas into similar groups. This is a silent exercise where the team members move each sticky note around the board to start developing natural relationships between the ideas. The finished diagram has the ideas grouped under the headings. The team then has to examine each group of sticky notes, developing the common theme for the group, and then label that heading. The finished affinity diagram has all of the various ideas under different headings, with the problem statement located at the top of the diagram. Every time you create an affinity diagram, you need to keep in mind what will make the diagram effective and what won't. First, the ideas need to be easy to see from a distance, so they need to be large enough. Typically, the team will use fairly large sticky notes and a dark pen or marker to make sure the ideas are easy to read. It's also important to allow your team plenty of time for this exercise. In some cases, especially if you're dealing with a big project, it could take several days to complete this activity. You want to make sure that the team has enough time to properly brainstorm and come up with enough ideas. It's also important to use intuition and gut reactions. So allow your team members to develop their ideas freely. Once you have several groups of ideas, you might want to use superheadings to combine groups. This will help start grouping some of the ideas together. Now, in terms of what you don't want to do, don't determine the categories in advance because that will limit what the team will be able to develop. Don't deliberate or criticize during the brainstorming process. You don't want people to be afraid of suggesting different things or ideas. Also, remind the team that it's important to conduct this exercise silently, so we don't talk, especially while the ideas are being sorted. This silence will allow your team members to think on their own and not be led by the rest of the group. Don't order the ideas before they are placed in groups. You want those natural relationships and that natural order to come out of this process. And finally, don't over-consolidate ideas. You want to discover natural relationships. The goal is not to get down to the fewest number of categories as possible. The goal is to find the natural relationships between the ideas so you can group them appropriately. Interrelationship diagrams show the cause and effect relationships between multiple ideas, so teams can use them to create a relationship diagram and organize the different ideas based on their natural links. They're also useful between different aspects of a very complex situation, so the team can use these diagrams to first develop multiple ideas and then determine the relationships between those ideas. As the team goes through this process, they should ask themselves, does this idea cause or influence any other idea? This is where all of the arrows are added in. The team draws an arrow from each idea to the one that causes or influences it. After that, the team should look at the total number of arrows that are going into and out of a particular area to see which ideas have primary outgoing arrows or incoming arrows. The ones with primarily outgoing arrows are usually the basic causes of the issue that's being explored. Performing this exercise will help the team figure out what the leading issue is. The ideas that primarily have arrows coming into them will be considered the final effects and will be critical for the team to address as well. Another benefit of interrelationship diagrams is that they help the team explore the root cause of the problem. By looking at the relationship between the ideas, the team is able to understand the cause and effect relationships and determine what the main causes of the problem are. The team is also able to discover what the influencing factors are and what causes those effects to happen. Then the team can use this information to evaluate relationships between the ideas by looking at how many arrows are coming into each idea and how many arrows are going out. This is particularly useful when there are multiple cause and effect relationships and the team is trying to understand what is happening within the process and what those relationships are. You will typically use the interrelationship diagrams during the define and analyze phase of your projects because in these phases you're trying to find what the key factors and influential relationships are. So let's explore an example. The problem statement is displayed at the very top of the interrelationship diagram. Why are dispatches being delayed? The team identified 4 common issues: poor customer order scheduling, lack of communication with the shipping department, non-automated scheduling practices, and poor logistics schedules. Then the team added in the arrows to see which factors influenced other factors, based on how they have documented that relationship. Once that process was completed, the team began to analyze the pattern of arrows going between the boxes in the interrelationship diagram. Their analysis revealed that the non-automated scheduling practices had a significant impact on the causes of poor logistics scheduling and lack of communication with the shipping department. This is shown by the 2 arrows that are leaving the non-automated scheduling practices box and going to the other ideas. The team concluded that the non-automated scheduling practices was the cause with the most number of arrows going out. So this is where they should begin working to improve the automated scheduling practices, and by doing so, have an impact on the other factors of the process as well. Let's explore how to create an interrelationship diagram. The first step to create an interrelationship diagram is to determine what the problem is. You want to make sure that the team thoroughly understands the problem statement and that it's clearly visible for the team. Once the team understands what the problem statement is, they start writing down their ideas on cards. This is where the team can use tools such as brainstorming to make sure that they have a wide variety of ideas of what's causing the problem. Then the team takes those cards and arranges them so that they can start identifying what the relationships are. Now, it's important to have the ideas spread out as much as possible so that you can clearly analyze the relationships between them. This will help the team identify those relationships. As they do this, they add arrows to indicate the causes and influences between the ideas. The proper way to add in the arrows is to place them from the idea that's the cause to the idea that it influences. There are a few tips for creating interrelationship diagrams. The first is to make sure that you have a spacious work area. If you have a large number of ideas, you want to ensure that these are spread out so that you can look at each of the ideas and draw arrows throughout all of the various relationships. It's also important to ensure that the cards are easily visible to each team member. Another aspect of creating the interrelationship diagram is that you should establish team ground rules. Some of those team ground rules should include being respectful of each other's ideas and avoiding criticism and negativity. This is a team activity where everyone is trying to focus on the problem itself and working productively towards solving that problem. You can also take ideas from another session or event that use an affinity diagram and use that information to understand the relationships between the issues identified by the team. As you draw the interrelationship diagram, you have each of the ideas on a sticky note. You go through each of the ideas and compare them to all of the other ideas on the table to understand what that relationship is. This is where a circular format is very useful because you want to make sure that you can draw arrows appropriately. Once you have drawn the arrows signaling the existing relationships, you can then understand the relationships. You can do this by capturing how many arrows are going into that idea and how many arrows are going out of that idea. You can then use this information to understand what the most critical areas are to address. The ideas that have the most outgoing arrows are the causes, and in this example, there are 3 different areas that are causes. After establishing that, you can examine how many ideas have the most incoming arrows. These are the key effects, or things that the customer would see. It's important to understand what are the key causes and what are the key effects. Some of the key causes are the ideas that have the most number of outgoing arrows. These are the ones that you need to go after and work on fixing because they have a big impact on the rest of the ideas. The key effects, on the other hand, are the ideas that have the most arrows coming into them. These are typically what the customer sees, so this is where you can measure the impact based on what the customer is experiencing. In this topic, we're going to talk about the tree diagram. Tree diagrams are useful tools for the Six Sigma team and are used to break down different ideas or problems into finer detail. Essentially, the tree diagram gets its name because of its structure. It starts with the higher level problem that's then broken down into categories. These categories are further broken down into finer and finer levels of detail. Each of these levels are known as branches. And as you create this diagram, it begins to look like a tree structure. There are other names that people might use to call similar diagrams, such as a systematic diagram, tree analysis, analytical tree use, or hierarchy diagrams. This is because of the hierarchy structure, depending on if you're looking at it vertically or horizontally. However, no matter what the name, a tree diagram is a great tool because it allows the team to go through all the ideas, understand the problem statement, and move forward step by step from general ideas into much more specific and detailed information. There are also different types of tree structures. There is a convergent diagram, which is essentially the reverse of the tree diagram. It starts with the detailed information and then groups that into more general information. So it moves in the opposite way to converge on that higher level area. The second type of tree structure that's also commonly used is a circular structure. It takes a circular approach to breaking down ideas. When you work with this tree structure, you start in the middle and break down the idea. Then you create different categories or branches that are broken down into other ideas. The branches form more of a circular shape, which can be useful when you're breaking off initially into 2 or 3 different categories. Now, let's explore an example of a tree diagram. The first thing you need to do is to present your statement. How can we reduce breakages in transit? Then you break this down into 2 categories, which represent ways you can accomplish your goal. In this case, you can reduce breakages in transit by improving your packaging and improving your delivery process. The question then becomes, how do we improve our packaging? You can do this by employing skilled packers and changing packaging materials. You can then continue to ask this question as you keep moving to the right of the diagram. Next, as you focus on improving your delivery process, you realize you can do this by changing your transport mode and by hiring skilled drivers. There are several key benefits of using tree diagrams within your Six Sigma projects. First, these diagrams are very easy to use, read, and interpret. This is very helpful when you're trying to get everyone on the team on the same page, and you're able to show the team the relationships between the different parts of the diagram. Tree diagrams also provide a very effective way of checking details. You can go through each step of the process to understand how the process works, and then the relationship between those steps. Using tree diagrams also promotes step-by-step thinking. As you examine each of the branches, you begin to understand each level of the diagram and how the steps are connected. You can also figure out the relationships between the steps, as in, for this to happen, what else needs to occur? Tree diagrams also highlight the complexity of the issue at hand as you examine the number of branches and contemplate how all aspects of the diagram are related to each other. Finally, tree diagrams are very useful tools within the define phase. They help everyone on the Six Sigma team understand what's involved in the project and what steps are required for moving forward with the problem at hand. This enables the entire Six Sigma team to have a basic understanding of the process that they're trying to improve. In this topic, we're going to explore the steps you need to take when creating a tree diagram. The first step is to define the problem statement at the top of the diagram. This helps ensure that everyone on the team understands the purpose of this exercise. Also, more importantly, the problem statement tells the team what they should focus on. In this example, the goal is to identify the factors that cause variation in the loan processing time. Having a clear problem statement will allow everyone on the team to focus on working toward the common goal. The next step is to take that information and break it down into the next level to start identifying key issues. During this step, you start creating branches within the diagram to understand the relationships between factors that cause them. In this example, there are 3 key issues. The first is the completeness of the loan application. The second one is the amount of the loan. And the third key issue is the training involved in loan processing. The third step in the creation of a tree diagram is to further break down the diagram into subsequent levels. Here you can start to identify the causes of factors for the key issues. For example, you could further break down the key issue of completeness of the application into 2 causes. The first cause is the number of entries, and the second cause is the operation timeouts. When you analyze the key issue of the amount of the loan, you can also further branch this off into 2 categories. The first one being multiple approval procedures, and the second, several loan categories. Finally, in terms of the last key issue identified, type of training, you can also have two branches. The first is hours per year, and the second type is training. This helps the team to identify on that top-level statement what those key issues are, and then further break them down into their causes or factors. As you begin developing your tree diagram, there are a few tips for conducting a good tree diagramming session. The first is to clearly define the process for breaking down the details. The person that's leading this event should have a short training session on what a tree diagram is and how the process works. The training should also cover how you're going to break down from that high-level problem statement into each of those further branches. As a team, you also need to define the criteria that you will use to understand and determine when you have reached that lowest level. The goal is to break down the tree diagram into the key factors that the team can work on and improve to reach your process improvement goals. Another key tip is to have no more than 4 items at any of the levels. Typically, when you have more than 4 items, that means you're getting too far into the details. In addition, you need to make sure that the groups or levels do not merge. If this happens, it will be a lot harder for the team to break down the structure and have clear and direct relationships. Once you have completed your tree diagram, it's also important for the team to go back and review it. You want to make sure that everything adds up from the higher levels to the lower levels and also backwards. You need to verify that those lower level items add up to the higher level items, and also check for consistencies. Finally, you will also want to look for ways that you can improve your diagram if there's anything that's missing or unclear. Another useful tool within Six Sigma projects is the prioritization matrix. The prioritization matrix is a quality tool that takes in different and diverse items and helps the team prioritize them based on very specific criteria. Then, using this criteria, the team ranks and determines the total value of each of those items. With Six Sigma, the prioritization matrix is very useful. For example, if you have several projects that you're trying to select from, or when you have different activities or process improvement ideas that you want to focus on within a project. But you need to decide where you should focus your efforts first. So let's examine an example of how this would work. In your current project, you have 4 different designs. Your goal is to determine which design you should select. You decide that you could prioritize the designs based on 4 different criteria: customer satisfaction, ease of implementation, impact on scheduling, and least additional training cost. The team ranks the designs and adds up the total for each. The highest ranking design, in this case, Design 1, will be the one where you will focus your priorities. The prioritization matrix is a useful tool, partially because it's very easy to use. The team can develop the criteria they consider important based on the voice of the customer, and then use this to prioritize 2 different alternatives. The prioritization matrix is also useful in facilitating analysis because you have very specific criteria that the team has agreed upon. The prioritization matrix takes this information and displays it in a very easy-to-read table format that helps the team reach consensus. The prioritization matrix should be used when you're deciding on the next steps for your project. Once you have brainstormed a list of potential areas to focus on, you will have a quantitative way for the team to decide what those next steps should be. It's also useful when you have complex or unclear issues, because the team can further prioritize where you should focus your efforts. The prioritization matrix also links everything back to the specific criteria that you're working with. Another benefit of using a prioritization matrix is that it allows the team to achieve consensus on where the priority should be, because everyone on the team is involved in ranking each of those different possibilities based on the criteria. The prioritization matrix is typically used in the define and improve stages of a project. During the define phase, you determine what the project should be, while during the improve phase, you're trying to determine which improvement actions the team should take. There are 5 key steps in creating a prioritization matrix. The first step is identifying the items and the criteria. You want to make sure that the team has mutually agreed upon criteria for how you're going to measure and prioritize each of these items. The second step is to list the items on the vertical axis. These are the items that you're going to be evaluating against the criteria, and then prioritizing based on your results. The third step is to list the criteria on the horizontal axis. This is what you're going to be evaluating each of the different items against. The fourth step is to then score each item per criteria and add a weight associated to the importance of each criteria. Finally, the fifth step is the total scores for each item. Now, let's examine an example of a loan application process. The Six Sigma financial team that's looking at the variability in the loan processing time worked together and discussed each of the categories it had listed. After their discussion, they developed a consolidated list of the 6 most important potential factors affecting the loan application process. The team then listed the factors in the prioritization matrix. They include completeness of the application, the loan amount, training, availability of resources, choice of processing partners, and volume of applications. The next step is to add the criteria to the table as column headers. These criteria should reflect the qualities and the solutions that are required to address the issues. In this case, these are ease, cost, effectiveness, and support. The next step in the process is to add the weight of each criteria, because some of the criteria are more significant in terms of corporate priorities. For example, if you consider low cost, this is an important factor to the corporate priorities. So it's rated fairly high, since keeping the cost low relates directly to a corporate goal. The weights you assign should represent percentages and will be taken into account when you talk about the base score. The next step in the process is to score each value. The scoring becomes the base value, which is then multiplied by the weight to give the weighted value. Each team scores each factor and multiplies the factor by the weight assigned to it. Then, both values are added to the table. For example, for availability of resources, the base value is 3, which is multiplied by the weight of 0.5, resulting in a weighted value of 1.5. The team then totals the scores for each factor to identify the top 3. In the case of this example, the top 3 factors are the completeness of the application, the amount of the loan, and the volume of application. It's important to realize that you can combine your tools. For example, if you look at what you developed while creating the tree diagram, you have identified the problem and expressed it in the problem statement to identify the factors causing variation in the loan processing time. Then you created 4 branches or categories that were broken off at a higher level in the tree diagram. These 4 categories can be used as different items to prioritize, and so they become inputs to the prioritization matrix. By using these 2 tools together, you can take this information and prioritize it to determine where you should focus your efforts, based on the criteria that's important to the team, the organization, and the customers. Another useful Six Sigma tool is the matrix diagram. The matrix diagram is a quality tool that shows the relationship between 2, 3, or 4 items or types of information. It's very useful because it's easy to create. You can use symbols, numbers, or letters to show the relationships between each of the categories that you're trying to analyze. So let's examine an example of how a matrix diagram would be created. A matrix diagram has 3 sections: header row, row headers, and body. In this example, there's a management team in an airport that wants to determine why certain flights are constantly being delayed. They enter the different flight numbers as the column headers of the matrix diagram. Then they list the possible causes as the row headers in the matrix diagram. The causes include insufficient staff, poor staff training, queues at the stand, ATC delays, and security delays. The body of the matrix displays the relationships that you're trying to understand and the factors that contribute to the flights being delayed. Here the team assigns a symbol or numeric weighting to the intersection point of the rows and the columns to indicate what factors are contributing most to the problem. In this example, the team decided to use a simple check mark to show the relationship between the specific flight and the causes of the delays. You can use matrix diagrams in several instances. First is when you're trying to assign project tasks. Using a matrix diagram will show the relationship between the project tasks and perhaps the person with the appropriate expertise assigned to that specific task. The matrix diagram is also useful when you're determining causes and effects of problems, because you can show the relationship between the issues or factors and also the strength of that relationship. Matrix diagrams can also be used when you're combining two tree diagrams into a single matrix. In that case, you're highlighting the relationships between those two tree diagrams. Matrix diagrams are typically used in the define and improve phases of Six Sigma projects. In the define phase, you use a matrix diagram to show relationships between the role and what's going to occur in the project itself. In the improve phase, you would use this kind of matrix when you're trying to show what processes or improvements could be taken, and where it's going to be helpful within the process. There are three types of matrix diagrams. The first is the T-shaped diagram. The T-shaped matrix is used when you have three groups of items. However, you use this type of matrix only when you're trying to measure the relationships between two of the groups and one group. The assumption here is that those two groups are not related, and you're evaluating those groups of items against the same group. In other words, you're looking for the relationship between those and not the relationship between the two. The second type of matrix is the Y-shaped matrix diagram. It's used to relate three groups of items where each group is related to the other two groups. So you're doing this more in a circular fashion to show the relationships between those groups. The difference between the Y-shaped and T-shaped matrix diagrams is that you're assuming there is a relationship between each of the three groups. So you're able to measure the relationship between each of those three groups. The next type is the C-shaped matrix. It's used to simultaneously relate three groups of items. This tool is helpful because it shows the information in a 3D format. There are various symbols you can use to show relationships in a matrix diagram. For example, you can show relationships that go from a strong positive to a strong negative using various symbols. You can also use symbols to show roles and responsibilities. For example, you can look at your suppliers, your customers, the people who are going to do the activity, and the people who own the activity. In a matrix diagram, you can also use a Likert scale to rate issues from least important to most important, giving them a rating ranging from 1 to 5. In this topic, we're going to discuss how to create a matrix diagram. The first step is to define the objective and the items to be related. You want to make sure that the team clearly understands the purpose of creating the matrix diagram and what information you're going to use to try to relate the items to each other. The next step is to choose the matrix type. This depends on the type of information and how many types of information you're trying to relate to each other. The third step is to determine how the relationships will be depicted. To accomplish this, you can use symbols or different ratings. The fourth step is to complete the matrix diagram as a team. When you perform this step, you're documenting the different relationships between the issues. The final step is to analyze the matrix diagram. The first step when you create a matrix diagram is to define the objective. So let's explore this through an example. Your customer, a national hospital corporation, has recently noted an increase in patient wait times for surgery. The first step you need to take is to define the objective. In this case, reduce wait times. You also have to determine the items that you're going to relate. Your team determines that in order to meet the objective of reducing wait times, they need to know which factors are contributing to the problem, and which actions a corporation can take to make the biggest improvement. The next step you need to perform is to determine the most appropriate matrix type to use. In this step, the team needs to know which contributing factors they should work on eliminating or which they should focus on improving first. Considering that the team only needs to relate two groups of information, the causes and also the inputs from the surgical units about the importance of each cause, they decide to use an L-shaped matrix. Next, the team needs to decide which symbols they should use to depict the relationships. In this example, the team decides that the relationship between the causes and the long wait times at each surgical unit will be defined using a scale that ranges from 1 to 10 to indicate severity. Now, using this information, the team creates an L-shaped matrix. The team then goes through using the various relationships and ratings and ranks each of the items based on the established criteria. This allows them to review the matrix and establish the highest rating is associated with insufficient staff. The team needs to analyze the efforts required to increase the staff number, because this will have the greatest impact on solving the issue of long wait times at the hospital. The next key finding was around the lack of communication with physicians. This received the second highest rating. The team knows that improving communications between the surgical team and the patient's referring physician will have a significant and positive impact on the objective of reducing patient wait times for surgery. As you develop matrix diagrams for your projects, there are a few important things you should keep in mind. The first is that you need to consider what does not need to be known. Focus on those key important relationships that you're trying to solve. This is going to help you determine the appropriate matrix to use for your project. It's also important that you clearly define the symbols you're using, and in some cases, you may even want to make up your own. By using symbols in your matrix diagrams, you will be able to quantify where you should focus your efforts, and then use this information for prioritizing issues. Also, remember that you're focusing on the key issues only. So, linking that back to the symbols and rankings you use, you will be able to focus on where your team's highest priorities should be. Finally, you can use these rankings to understand the patterns and the relationships between issues, and then, as a team, you can further investigate any interesting findings from your matrix diagram. The Process Decision Program chart is a very useful tool for systematically identifying what could go wrong in your Six Sigma project. Six Sigma teams can use this tool to develop countermeasures to prevent or offset any potential problems that could go wrong. Your Six Sigma team can also use the Process Decision Program chart to revise their process improvement plan so that they can mitigate any risk or be ready with countermeasures in case something does go wrong. The team starts by identifying their Six Sigma project objective and also the main activities involved with the project. Once they've done this, they can discover the potential risk associated with each step in the project activities. The Process Decision Program chart can help the team identify those risks and then develop the appropriate countermeasures to mitigate them. So let's examine a sample Process Decision Program chart, or PDPC. This chart shows a Six Sigma team that's working at an automotive parts manufacturer. The team wants to develop a new process of their line of anti-lock braking systems, or ABS. The Six Sigma team uses the Process Decision Program chart to identify and assess the risks to develop countermeasures. For example, with this new process, the team identifies a lack of knowledge as one of the potential risk areas. As a countermeasure, the team decides to incorporate training, simulation, and external consultation. Doing this will help the team mitigate any risk caused by the lack of knowledge in the new process, and ensure that the new ABS process will move forward without any problems. The Process Decision Program chart is very useful in several instances. First, as you start planning your Six Sigma projects, you can use this tool to conduct a risk analysis and have countermeasures in place to mitigate the risks. You can also use a Process Decision Program chart to identify alternatives in case something does happen, which will enable you to be more prepared and plan the appropriate contingencies in case the risks do occur. The Process Design Program chart is also very useful when your time constraints are very tight. If something goes wrong during your project, you don't have the time to go back and make changes. Therefore, planning ahead and having contingency plans already in place will allow you to move on to the alternative plan quickly, without having a tremendous impact on your project timeline. Finally, the PDPC is very useful during the analyze and improve phases of the DMAIC process, because these are the phases where you're spending most of your time, implementing actions for your process improvement. In this topic, we're going to look at how to create a Process Decision Program chart. The first step in the process is to clearly define your project's objective, in other words, what you're trying to accomplish. Then, based on what you're trying to accomplish, you will have specific activities that need to occur to make sure that you can reach your objective. You want to look at those high-level key activities in your project. Let's explore an example. You're leading a project team for an online education provider that wants to improve the learning process for all of its learners. The objective of this project, then, is to improve the learning experience. The team works together to brainstorm 3 different activities that could help meet this objective. These activities include identify better resource materials, provide interactivity, and improve delivery. The next step of the PDPC is to identify the potential problems or risks associated with each of these activities. What you want to ask here is, what could go wrong? Or, those what-if type questions, to identify the potential risks that are associated with each main activity. Let's continue our scenario of our online education provider. The team went through and identified the risk associated with each activity. In terms of identifying better resource materials, the team identified increased ramp-up time as the activity's risk. In terms of providing interactivity, the team identified two potential risks. The first one is how to measure the risk, and the second, interactivity may be different for each student. Finally, in terms of improved delivery, the risk that teachers could resist the change. The next step in the process then is to determine what the appropriate countermeasures or contingencies for each problem or risk are. For each risk, your team should develop and determine those countermeasures. The purpose of this step is for the team to examine each action and determine the practicality level of each countermeasure. The team could eliminate or replace countermeasures that are not feasible. So you could potentially have areas where the countermeasure is not feasible, and your team will have to focus only on the feasible countermeasures. So let's consider our example of the online education provider once again. In terms of increasing ramp-up time, the team decides that they should add prep time to the schedule. In terms of measuring interactivity, the team determines that they need new performance objectives. And since interactivity is different for each student, they also determined that they should have individual performance objectives. Finally, in terms of potential teacher resistance, the team decides that an appropriate countermeasure would be to conduct workshops. When you're developing PDPCs, there are a few tips to make sure that they're effective. The first is to make sure that the team works in an environment that fosters respect. Each team member needs to collaborate during the brainstorming session. It's important to make sure that everyone feels they can contribute. As you're going through and looking at the potential risk for your project, keep asking those what-if questions. This will help drive down the potential risk and then also help to determine the appropriate actions to mitigate those risks. If there are any insignificant risks, instead of having solid lines in your PDPCs, you could also incorporate dashed lines. These would indicate that those risks don't pose a big threat to the project. In addition, the team could use symbols for rating the countermeasures, which also help prioritize the countermeasures. Then finally, when you analyze the countermeasures, you should also make sure that you use good evaluation criteria, such as time or cost. An activity network diagram is a quality tool that's used to show the required order of specific tasks needed in a project or process. When you show the necessary steps that are required in your project or process, the team is able to determine the best schedule for the entire project, and also show any potential scheduling or resource problems. This, in turn, can lead the team to develop solutions. You can use the activity network diagram to identify your project's critical path and help your team understand the risk associated with missing any potential deadlines. You can also use this type of diagram if there are any delays in your project, and help the team understand how those delays will impact the entire project. Let's consider an example of an activity network diagram for a gaming software company that's trying to develop a new game. The team starts the process with a strategic planning activity that takes 2 weeks. From there are 3 concurrent activities that are involved. The product design that takes 2 weeks, the material procurement that takes 3 weeks, and then the software development that takes 2 weeks. Moving forward, other product development activities need to take place for a total of 10 weeks. This time is dependent upon the product design being completed and the team having the material procurement in place. Once those activities are completed, the process moves into sales and dispatching. For the sales and dispatching to be complete, the team also has to have the marketing and distribution arrangements already established. That part of the process takes 5 weeks and is dependent on the software development. These are all the necessary activities for the project to be finished. By putting all the different processes in place and identifying what must take place before the next step can occur, the team is able to identify all the possible associated risks and the overall lead time for the project. There are several advantages of developing an activity network diagram. First, by showing all of the different steps that are required, this type of diagram communicates quite a bit of information at a glance. The diagram also shows the sequence of tasks so that everyone can understand what each step is and what is to be accomplished before other activities can start. An activity network diagram shows concurrent tasks, so that you can understand the different tasks that are happening at the same time, and any steps that are interdependent upon each other. The activity network diagram also makes it easier to determine what the critical path is, by looking at how long it takes for each step and what's required. In addition, it shows the duration for each task. The activity network diagram can be used to determine ways to get the project done sooner by understanding the tasks that can be done concurrently. You can also use activity network diagrams to describe the flow of activities within a process. Doing this helps the team understand the sequence of activities necessary for the process to occur. In addition, this type of diagram can be used to communicate plans and risks to the project stakeholders. An activity network diagram is typically used during the define phase to document the entire project and the steps that are necessary to accomplish the project's goals. And it's also used during the improve phase as a way for the team to identify appropriate process improvement steps. Now, let's explore another process to identify each of the required steps. In this example, the start is signaled by step A, and the finish is signaled by step I. There are two paths your project can take to reach the finish. The first path takes 10 days, and the second path takes a total of 8 days. Each of these paths are necessary to get to the finish. The critical path would be the top loop, as it takes the longest time to complete. In order for your project to be successful, you need to make sure that any tasks or activities that are occurring on this critical path stay within their allotted time frames. Otherwise, the total lead time to get to the final step will take longer. There are 5 key steps involved in creating an activity network diagram. The first step is to gather information. In this step, you would need to understand the critical information about what you're trying to diagram. For example, you should know the scope of the project. Where does it start and where does it end? Once you have that information, you can move on to the second step, which is to identify the activities in the project. After identifying the activities, you move on to the third step, which involves sequencing those activities so you can understand your project step by step. The next step in the process involves concurrent activities. In other words, these are activities that can happen at the same time. Any activities that can happen at the same time should be stacked so that you can highlight their relationship. The fifth and final step is to add network lines to show the sequence of events and how these steps relate to each other. Now let's examine an example. We're trying to design an electronic device. The team identifies 13 tasks surrounding updating software that need to be done to accomplish the project. In this case, the team has identified each task and indicated the duration of each task in days. Remember, it's important to be consistent with metrics when you're dealing with task duration. You should avoid mixing hours, days, and weeks. In this example, task duration is expressed using days. Once this information is collected, the team starts to sequence each of the events to understand what must be done before the next step can happen. The team should also consider whether there are parallel paths that can be done concurrently, or whether certain tasks have to be done before others. Doing this can greatly help reduce overall lead time for your project. The next step is to network your activities by adding arrows that show the relationships between the activities. While you're doing this, remember to also check the network by working backwards from the end to the start to make sure that every activity is in the right order. As you perform each task, confirm which task must be completed before the next one can begin, thus verifying the relationships in your process. As you move forward with this project, the team is now able to calculate the critical path. In this example, the activity network diagram has 4 potential paths. Based on their calculations, the team determines that the critical path is the bottom path, which takes 212 days to complete. It's the longest path, so it's the critical path. If this process takes 212 days, you need to know if it's going to extend beyond what you have contracted as your completion date. If that is the case, then you will need to shorten the duration of the software-related activities, which include writing software. That task alone takes 135 days. It's the longest duration task within the entire activity network diagram. You could figure out a way to reduce that time. For example, you could add a programmer to help write the software, and that could potentially reduce the duration of the task and impact the overall lead time of your project. If you can't or don't measure something, then you can't improve it. This is where process performance metrics come into play. It's important that as you are going through and improving your processes with Six Sigma, that you're trying to reduce defects and reduce your variation. You need performance metrics to help with this. Performance metrics are used initially in the define phase, so that as a team, you can determine what the goal of the process improvement effort is and what metric to use for measuring the improvement. This is critical for the team so that they can understand what the objective is and what the problem they're trying to solve is. In addition, as you go through the rest of the DMAIC methodology, you will be using process performance metrics to track your project and to figure out whether or not you're making improvements in the right direction or not. This will also help drive your project decisions. Now, it's important to note that there is a misconception that these metrics are only useful in manufacturing. Process performance metrics are critical within any type of Six Sigma process improvement effort. For example, you could use performance metrics in banking if you're trying to improve customer service or reducing errors. Also, in information technology, you could look at how you're improving your coding process. In terms of customer service, you could also look at how you're trying to increase your customer service satisfaction. Within healthcare, your metric could be reducing defects and any patient adverse effects. Therefore, it's important to have performance metrics no matter what industry you're performing your project in. Sigma level is the number of standard deviations, which is represented by sigma, that you can fit between the mean of your process and the closest specification limit. When your process is capable of Six Sigma, that means you can fit 6 standard deviations between the mean of the process and the closest specification limit. What this also means is that with the distribution of your data, the tails of your distribution outside of the specification limits are the defects. At a Six Sigma level, this means that 99.997% of your data fits within the specification limits, or, in other words, that equates to 3.4 defects per million opportunities. The core of Six Sigma is to reduce the number of defects and reduce the percent defective. You can accomplish this by reducing the variation as you strive for that nearly perfect process. Within Six Sigma, there are several performance metrics that are commonly used. The purpose of using these metrics is to help you define your problem. For example, you might have a particular process with a high level of defects. Therefore, the Sigma level would be low. This would require an improvement project to improve the poor quality of your process. Some of the key commonly used metrics include defects per unit, defects per million opportunities, first-time yield, rolled throughput yield, process capability indices such as CP and CPK, and cost of poor quality. Cost of poor quality, for example, is a metric that translates defects in terms of how much they cost your organization. There are 2 different approaches to measuring process performance. Both of them result in a sigma value. The first approach is counting defects. Defects are defined by the customer. You should know from the voice of the customer what your customer's expectations are. If you fail to meet those customer specifications, you now have a defect. That's any nonconformity to what those customers' requirements are as specified by the voice of the customer. Potential causes of defects are faulty processes, inferior inputs, or defective machinery. An example of a service defect could be putting the wrong oil in a car during an oil change. In manufacturing, a defect could be a loose circuit in a computer, which prevents the device from working all the time because the connection is not made every single time. You can use this information to then calculate the sigma level. The easy part about counting defects is that it works with any type of data, whether it's discrete or continuous. All you need to know is whether or not your product or service meets your customer's expectations. You do this by examining the output of your process. If the output doesn't meet your customer's expectations, then you have a defect. Counting defects works best with discrete data. However, so rather than always having an actual reading or measurement on a particular aspect of your product or service, you can use information just stating whether it's good or bad. This is discrete data. Then, you can use this type of information to calculate defects per unit, defects per million opportunities, rolled throughput yield, and sigma value. The second way to measure process performance is to measure variability of the process directly. You do this by looking at your process variability and using information on the mean and standard deviation. You can then compare these values to your specification limits. In order to understand your process variability, you need to have continuous data that is normal distribution. You use this information to calculate your process capabilities, the CP and CPK. Then, the information you gather from your CP and CPK values can be converted into a process sigma using a table. One of the most commonly used metrics in Six Sigma is defects per unit, or DPU. DPU is a metric that provides a ratio of the number of defects divided by the number of units. This ratio gives you a good understanding of where you currently are with your process and the ratio of defects that you have. DPU helps to provide a common benchmark when you're trying to understand your current situation. It also gives you a baseline of where you currently are with your percentage or ratio of defects. In addition, when you're evaluating your current processes, DPU gives you an idea of where you should focus your efforts, because you want to prioritize your process improvement efforts on the process with the highest DPU. This also helps you identify future improvement activities so that you can understand what a defect is before you make your calculation. Then, based on that defect in your current baseline, you can determine what type of improvement activities you need to perform. In addition, by understanding what a defect is based on the voice of the customer, you will be able to identify what your current nonconformances are. The defect per unit formula is calculated using two elements: the number of defects observed and the number of units inspected. Before you do the calculation, it's important that you understand what your customer requirements are based on the voice of the customer. Then, based on that, what constitutes a defect. The defects per unit calculation is the number of defects observed divided by the number of units inspected. Now, let's examine an example using a bottling facility. The team suspects that there's an increasing number of bottles that are coming off the production line with caps that don't seal properly. The team also knows that in order to properly calculate the DPU, they need to know exactly what they should consider to be a defect. The team determines that a defect is a cap that won't seal. They also determine that a unit is each individual bottle. Based on this information, the team's able to go through and count the number of defects out of the sample that they're pulling. In this case, they find 19 defects in a sample of 200 bottles. They can use this information to calculate the defects per unit. They divide the number of defects observed, 19, by the number of units inspected, 200, which gives a defects per unit of 0.095. Now, let's examine another example and how this relates to measuring performance by calculating parts per million. Parts per million is a related measure to defects per million and to defects per unit. Parts per million is calculated by dividing the number of defects observed by the number of units inspected. This is the same as defects per unit, but now these values are multiplied by 1 million. So let's consider an example of a fast food restaurant. The requirement or expectation is that customers should wait no longer than 3 minutes for service. The manager observes that 15 of 100 customers waited more than 3 minutes for their service. Therefore, the parts per million, or ppm, for this process is calculated by dividing 15 by 100, and then multiplying that value times 1 million. Therefore, the parts per million for this process is 150,000. What this means is that 150,000 out of 1 million customers wait more than 3 minutes for their service. A commonly used metric in Six Sigma is defects per million opportunities, or DPMO, and it's built off the DPU and ppm calculations. The difference with DPMO is that you're calculating the mathematical possibility that the process will be defective. DPMO standardizes the defects at the opportunity level, which enables you to consider that there could be multiple aspects of the product or service that are defective, rather than just the entire product or service. This allows you to compare your process at different levels of complexities, because you can take into account a more complex product or service that might have 30, 40, 50, or 60 or more different characteristics, and each of those aspects of the product or service is an opportunity to be defective. Let's consider the example of a pizza to understand the difference between defects and defectives. In the case of a home delivery pizza company, there are different qualities that could cause the pizza to be defective. These could be temperature, toppings, and the pizza size. The first opportunity for a defect is the temperature. This could be defective because the pizza might be too hot or too cold. The second opportunity for a pizza to be defective could be the fact that the wrong toppings are used. Finally, the third opportunity for defectives could mean the pizza is bigger or smaller than what the customer ordered. This is the difference between defects and defectives. When exploring defects per million opportunities, you have multiple opportunities for defects, so you want to capture those opportunities in your calculation. If you consider your defects per million opportunities, you can relate those specifically to a sigma level. A 3 sigma process, which used to be considered good enough before Six Sigma was invented in the mid-1980s, indicates a defect per million opportunities of 66,800. As you move toward a sigma level of 6, your defects per million opportunities drops drastically. When you reach a 6 sigma level, your defects per million opportunities is 3.4. You can also compare other metrics to determine what your 6 sigma level is. In this example, you have your process yields, defects per million opportunities, process capability, sigma level, and cost of poor quality. If you consider a sigma level of 3.55, then you have 20,000 defects per million opportunities, a CP of 1.18, and a cost of poor quality of 20%. When you get to the point where you are at a 6 sigma level, your yield is running at 99.997%. The defects per million opportunities is 3.4, and the process capability index, or CP, is 2.0. The calculation of defects per million opportunities, or DPMO, examines the opportunities for defects within units that result in products or services that did not meet customers' requirements or their performance standards. There are 3 main components in the defects per million opportunities calculation. The first aspect is the defect. This is a measurable failure where you fail to meet the customer requirements based on the information you collected through the voice of the customer. The second aspect is the unit itself. This is that final product or service that's given to the customer. The third and final component is the opportunity. Within each unit, you could have multiple opportunities. This means that within each opportunity, there is a measurable attribute that could result in a defect. Defects per million opportunities is calculated by dividing the number of defects in a sample by the total defect opportunities in the sample. This value is then multiplied by 1 million. To put this ratio in terms of how many defects will occur within 1 million opportunities. An alternative to this formula is a change in the denominator. Instead of dividing the number of defects in the sample by the total defect opportunities in the sample, you could also divide by the sample size, multiplied by the defect opportunities per unit. You can then multiply this ratio by 1 million to give you the defects per million opportunities. Now, let's examine an example to show how these calculations work. You're a greenbelt at a stationery company. Each customer stationery order could have 4 possible defects. The order could be incorrect, it could contain a typo, it could be damaged, or it could be incomplete. Therefore, you have 4 opportunities for defect. You randomly select and inspect 50 orders and find several defects. From these 50 orders, there are 2 orders that are incomplete, 1 order that is both damaged and incorrect, so it has 2 defects, and there are 3 orders that have typos. Therefore, you have 7 defects. In terms of your total number of opportunities, since you had 4 opportunities, and you had 50 orders that were randomly sampled, the true number of opportunities is 200 opportunities. Therefore, to calculate your defects per million opportunities, you divide 7 defects by the 200 opportunities, and then multiply this number by 1 million. This results in a defects per million opportunities of 35,000. That means that when you produce 1 million orders, you will have 35,000 defects. An important measure within Six Sigma is yield. Yield is a percentage of error-free product. It's an important metric to use, particularly when you're trying to analyze your processes and identify problems. Using yield allows you to calculate how many products you start with and how many good products there are at the end of the entire process. Yield can also be calculated using first-time yield or rolled throughput yield. The first-time yield typically concerns one specific process, whereas a rolled throughput yield considers multiple processes. Let's examine first-time yield. It's also commonly referred to as first-pass yield. In this example, you have 1,000 units going into your process. Out of those 1,000 units, you have 100 that are scrap. So at the end of the process, you only have 900 units. This means the first-pass yield is 90%, or in other words, 90% of the products that come into your process leave the process defect-free. First-time yield is typically used for processes or sub-processes that are made up of only one single operation or step. When you're considering multiple steps, you will need to use rolled throughput yield. You need certain information in order to calculate rolled throughput yield. You need to know the total number of process steps and the first-time yield and reworked units for each process step, because you're going to multiply the resulting yields by each other. For example, you have 1,000 units coming into your process, again with 100 defects in the first step of the operation. This gives you a yield of 90%. Therefore, since you had 100 scraps, you now only have 900 parts that are moving into step number 2. Out of step 2, you had 90 units that were scrap. Therefore, you only have 810 parts that are still good at this point of the process. Since you have 810 parts coming out of the process, this gives you a rolled throughput yield of 81%. You would probably have other multiple processes within this entire process. For example, when you get to step 10, you may have only 350 units that are coming out of that process that are good. So if you consider the entire process, you started with 1,000 units, and now only have 350 that are good at the end of the process. Let's examine another example of how rolled throughput yield would be used to give you the information you need to improve your process. In this example, you have 3 steps, each of them with its own yield. If you look at those numbers, initially the yields were well over 90%. So you would expect to have a fairly good rolled throughput yield. However, based on how these steps play out, you will see that it's actually much worse. When you have 100 parts coming into your first step, there are 5 that are scrap. This means that only 95 are going on to your second step, and your yield for step 1 is 95%. Out of the 95 going into step 2, 7 are scrap, which gives you a yield of 92.6%. Now you only have 88 parts that are good coming out of step 2. Of those 88 parts, you have 3 that are scrap, which gives you 85 parts that are good at the end of step 3 of the process. Step 3 has a yield of 96.6%. In order to calculate your rolled throughput yield, you would multiply 95% times 92.6% times 96.6%, which gives you 85%, and therefore your rolled throughput yield is 85%, which is the final percentage of products that are good out of the 100 that you had at the beginning of the process. In this topic, we're going to talk about how to calculate first-time yield, or FTY, and rolled throughput yield, or RTY, in detail. First-time yield is calculated by dividing the units with no defects by the total number of units inspected, and then multiplying this number by 100. The reason it's multiplied by 100 is because first-time yield is generally expressed as a percentage. So now let's explore an example calculation for first-time yield. A book production involves several processes, including manuscript writing, editing, designing, printing, cover designing, and binding. In the book binding process, you find that there are 2,230 that pass the first test out of the 2,500 books that were printed. This means that there were 270 books with defects. To calculate the first-time yield, you divide the number of books that were good, 2,230 units, by the total number of books, 2,500, and multiply that times 100. This gives you a first-time yield of 89.2%. In other words, that means that approximately 89% of the books were defect-free. Now, let's examine the rolled throughput yield calculation. The rolled throughput yield is different from the first-time yield because you're looking at multiple sub-processes or multiple steps within the process. Therefore, to calculate rolled throughput yield, you multiply the first-time yield for several processes by each other. So let's look at an example. A jewelry manufacturer does rhodium plating. The manufacturer wants to calculate the rolled throughput yield for a sub-process in the plating operation. The plating operation has 3 steps. The first-time yield for the first step in the plating operation is 98.7%, or 0.987. The first-time yield for the second step in the process is 0.958, and the first-time yield for the third step in the process is 0.996. When these 3 values are multiplied by each other, the manufacturer gets a rolled throughput yield of 0.9420, or 94.2%. Now, you can use yield information to calculate the probability of a defect. When you talk about yield is a percentage of the product that has no defect. When you want to understand the probability of having a defect, you take 1 minus the yield, and that gives you the percentage that is defective, or the probability that there is a defect. Then you can use that information because there's a relationship between the yield and the sigma level. If you use the Z distribution table, you can find the corresponding sigma value. So let's explore an example from this table. If you had a yield of 90.49%, when you take the 1 minus 0.9049, you get the probability of a defect of 0.0951. When you look at that value on your Z distribution table and follow it over to your Z value of 1.3 and follow it up the column, you get a value of 0.01. This is your sigma value, or sigma level, and so this process has a sigma level of 1.3. Now you can determine what your yield values are as it relates to defects per million opportunities and the sigma level. If you determine your sigma level to be 3.0, that equates to a yield of 93.3% and defects per million opportunities of 66,800. You should improve your processes so they reach a sigma level of 6, which means that you're reducing your defects per million opportunities to 3.4, and your yield becomes 99.9997%. Process capability is a metric used to measure the variability and the output of a process. There are 2 main components involved in process capability analysis: specification limits and process spread. The first component, specification limits, should be given to you from the voice of the customer based on your customer's requirements. The second component is the process spread or process variation. This is basically the voice of your process that provides your process limits. With process capability, you're trying to understand how a process fits within specification limits and also how it relates to a target. In the first scenario, your process is on target. The target and the mean are equal to each other, and the variation or process spread is within the specification limits. In the second example, the specification limits have been reduced. While the process mean is still on target, the variation now is outside the specification limits. Therefore, the process spread is wider than the specification limits. In this example, the mean of the process x bar is not in line with the target. However, the variation of the process spread, is still within the specification limits, so the process is just off-center. Finally, the mean of the process, x bar, is not centered within the target, and the distribution or process spread is outside of the specification limits. There are 2 main indices in process capability, CP and CPK. CP is the ratio of the specification spread to the actual process spread. Because CP is a ratio, the higher the CP value, the better the process fits within the specification limits. For example, if your process width is half the width of your specification limits, then the CP value is 2. CPK is the ratio of the same element, but unlike CP, CPK takes into adjustment whether or not the process is centered. You want to understand if you have a non-centered distribution of your data. The higher the CPK value, the better the fit for the process within the specification limits. This also means that the process mean is closer to the middle of the specification limit, or closer to the target. Now, let's explore an example of cars in a parking lot to show what CP and CPK values are. In this example, the center of the process, or the center of the car, is in the center of the specification limits. Therefore, the process is centered, and you have little variation within your process. You have a high CP and a high CPK. In the second example, the target is falling on the low side, where the center of the car is not in line with the target. So, therefore, the processes are off-center. This means that you have a high CP value, but the CPK value is low because the process is off-center. In the final example, the car is wider than the parking space. Therefore, the process is too wide. In this case, both the CP and the CPK values are low. Since the process is too wide, even though CPK takes into account centering, and the mean and the target are equal, you still have a low CPK. You can use the information from the process capability along with your Z distribution table to combine the CPK value into a single metric for both short and long-term values. For example, if you consider a Z value of 3, that means your sigma level is 3. It also means that there are 2,700 parts per million, and the CPK value is 1. If you're at a level of 6 sigma, the sigma level is 6, which is the same as the Z value. In that instance, the parts per million are 0.002, and the CPK value is 2. In order to have a 6 sigma process, you must have a CP value of 2, a CPK value of 1.5, and the defects per million opportunities should be less than or equal to 3.4. And your yield becomes 99.9997%. There are two conditions that must be in place before you calculate process capability indices. The first is that the process must be stable over time. In other words, the mean and the standard deviation are consistent and do not shift over time. The second aspect is that the data must fit a normal distribution. Process capability is calculated by subtracting the lowest specification limit from the upper specification limit, and then dividing by 6 times sigma, which is the standard deviation. Standard deviation is a measure of the process width. The ratio tells you how much of your specification width is being taken up by your process width. There are no specific standards for a good CP value. However, most organizations require a CP value of 1.33 or above. This value means that the process comfortably meets its specification limits and also corresponds to 64 parts per million. If you consider a process where the CP value is between 1 and 1.33, and you're operating under tight control, then your process is considered capable. However, if you think about a CP value of 1, this means that your process width equals your specification width. Therefore, if you have any slight movement off the mean due to variation, then a portion of your process will fall outside of the specification limits. In other words, processes that are close to 1 must be closely monitored. If you have a CP value of less than 1, this means that your process is not capable. Essentially, this means that your process width is greater than your specification width. Therefore, a portion of your distribution will fall outside of the specification limits. CPK is a long-term measure of process capability. The calculation is very similar to the CP calculation. However, now you're taking into account the centering within the data. Therefore, your calculation takes into account the mean of the data, and then each half of the equation is half the previous denominator, which is why the denominator is now 3 sigma. When you're calculating CPK, you're trying to measure how the mean of the process relates to the target of the process, and how close it is to each specification limit, which is why you're taking the minimum of those values. Industry standards for process capability are higher now than they were in the past. It used to be that the minimum CPK value was 1.33, which corresponded to a value of 4 sigma. With the introduction of 6 sigma in the mid-1980s, that value has risen, and now the common accepted values for CPK are 1.67, which corresponds to 5 sigma or 2.0, which corresponds to a 6 sigma process. Within the practice of Six Sigma, it's important to understand the cost of poor quality metric. Cost of poor quality is the cost of the product or service when it doesn't meet customers' expectations. These are costs associated with products or services that are of low quality and come from activities or processes that do not meet expected outcomes in terms of the voice of the customer and the customer's expectations. Typically, these costs are related to inefficiencies, whether they are within your processes or as a result of not understanding what your customer's expectations truly are. Cost of poor quality is calculated as the actual cost of the product or service minus the minimum cost. Therefore, when calculating this cost, you're taking into account the costs that are directly related to not meeting the initial customer expectations. When you consider the cost of poor quality, you're capturing direct and indirect costs. There are specific costs that are easy to capture, such as rejections at your customer site, rework, and repair and testing costs. There are other indirect costs that are a bit more difficult to capture. For example, if you think about the idea of an iceberg, there are certain things that are easier to see and capture. But then there are other things that are harder to see that are below the surface. These are typically your indirect costs. These are items such as loss of reputation in the market, confusion, loss of motivation, late penalties, urgent or hurried deliveries, and decreased customer satisfaction. It is much harder to capture these costs and determine their specific issues, but they are all derived from not providing a product or a service that meets customer expectation. Let's examine some cost of poor quality statistics. Costs are generally very high in a non-Six Sigma process. If you consider how this relates to Sigma levels, a 4 Sigma process equates to about 20% of sales revenues that are lost. A 5 Sigma process equates to about 10% of sales revenues that are lost. When put into perspective, this means that larger companies typically have about 8 to 12 billion per year in cost of poor quality. So no matter what size your organization is, it's safe to say that understanding the cost of poor quality is definitely worth figuring out. You use the value you determined as your cost of poor quality as a baseline to develop your goal for reducing the cost of poor quality, and also in the project charter you developed during the define phase of the DMAIC methodology. Then as you move forward through the other phases of the DMAIC methodology, you can use the cost of poor quality to track your benefits. After you've completed your projects, you can use this information to determine the improvements that you have accomplished. Finally, cost of poor quality is a good metric, as it helps you develop the criteria you will use to select future Six Sigma projects. Cost of poor quality is associated with the cost of not providing a service or product exactly as requested by the customer. The concept of cost of poor quality is different for each organization, and therefore, the cost of quality will be a little bit different in each case. However, there are 3 general classifications of quality costs that are consistent across most organizations. The first is prevention costs. These are costs such as education and training before releasing a new product. The second is appraisal cost. For example, this could be testing or inspecting a new service to make sure it meets the customer's requirements. Finally, there are 2 costs associated with failure cost, internal and external cost. Internal costs are scrap and rework that are internal to the organization, whereas external costs would be external to the organization, such as a sales return. Let's briefly explore examples of the different costs of poor quality under each category. Examples of prevention include aspects within your quality planning, such as pre-production reviews, developing specifications, performing preventative maintenance, and housekeeping within the organization. Examples of appraisal include tests and inspection, and performing tasks such as quality systems audits. Other examples could include safety checks or security checks. The category of failures can be divided into internal and external failures. Internal failures are internal to the organization, such as substandard products or engineering changes that have to occur because of mistakes, supplier problems, or absenteeism. In terms of external cost of poor quality, these could include such things as product recalls or products that are returned, and also late payments. You also need to consider hidden cost of quality. Hidden costs of quality are more difficult to quantify, but they still have a significant impact on your organization. Examples of hidden cost of quality could include unhappy customers. In terms of the impact on your business, these are customers that potentially will not return, so it's lost revenue for the organization. Another source of hidden cost of quality are unhappy employees. Having unhappy employees impacts how the organization operates and typically results in a high turnover rate. In addition, you could have inadequate service. This is typically a result of unhappy employees or a lack of training and education, and that inadequate service results in unhappy customers and customers that are not going to return. In addition, you could have internal problems. Each of these four sources are difficult to quantify, but they have a significant impact on the cost of poor quality for your organization. Now, let's examine how your cost of poor quality equates to other conventional Six Sigma metrics. If, for example, your cost of poor quality is 30%, that equates to a sigma level of 3.10, a CP value of just over 1, and a yield of less than 95%. When your cost of poor quality drops down to 20%, your sigma level increases to 3.55. Your defects per million opportunities drop to 20,000, and your yield also increases to 98%. At 10%, your sigma level jumps up again to 4.6. The CP value is 1.53. The defects per million opportunities drop significantly to 1,000, and your yield increases to 99.9%. When you cut your cost of poor quality in half, from 10% to 5%, your sigma level jumps to almost 5, and your CP value increases to 1.66. And your defects per million opportunities is cut by 75% down to 250, and your yield increases to 99.975%. So what does it all mean? Well, it means that every single aspect of the cost of poor quality translates into real impact across your business. Therefore, the lower your COPQ, the better the quality levels you'll achieve in your processes.